Black holes are these really fascinating and mysterious objects that live in our universe and were hypothesized for the first time by Einstein's general relativity theory. We know that they exist because we have been able to look at the matter in their surroundings, and in particular 4 or 5 years ago, if I'm not wrong, we've been able to take pictures of two different black holes. One of those is the one that is in the center of the Milky Way. And we've been able to look at the dark disk and the accretion disk in the outer region that would be the result of the hot matter that is highly attracted to the center due to the strong gravitational field, of course. So, what do we know about black holes? First of all, we know that they are the result of the implosion of heavy stars with a mass of 10 or more solar masses. We know that there are huge ones in the center of the galaxies. These are the so-called active galactic nuclei, which actually we have observed that evolve with a law that looks quite similar to the one that describes the evolution of the galaxies in which they live in. And so it looks like there has to be some kind of relation between the active galactic nuclei and the galaxies they live in, but still we have not been able to understand which kind of relation should hold. And finally, we know that there should be primordial black holes that should have formed in the early universe due to the density fluctuations. So they are not the result of the implosion of stars. Talking about the mathematics that is behind a black hole, we know that 3 parameters are needed to describe a black hole, and no more than that. And these are the mass, the electric charge, and the angular momentum. So here it comes the no-air theorem by John Wheeler that states that a black hole has no air. That means that every other physical quantity would be radiated away either during the implosion of the star or or in the early stage of a black hole, would be radiated away in some form of radiation, of course. And so, for example, in the early stage of the black hole, I would say that every deformity would be just radiated away in the form of gravitational waves, for example. So since 3 parameters are needed to describe a black hole, of course, I can talk about different kind of black holes based on these 3 parameters. So I will start with this case, which is that one in which the mass is non-vanishing, is different from 0, and the other 2 quantities, which are the electrical charge and the angular momentum, they are equal to 0. Okay, this is the so-called Schwarzschild black hole. So, first of all, we have that the Schwarzschild solution that describes the black hole with non-vanishing mass and no electric charge and no angular momentum was found by Schwarzschild when he wanted to describe the metric solution outside of a spherical symmetrical source such as a star, for example. So due to the Birkhoff's theorem, one has that outside of a spherical symmetrical source, the Einstein's equation in the vacuum will have static solution. So in the hypothesis of staticity and spherical symmetry, the solution for the metric was found as d s squared equal 1 minus 2 m over r dt squared minus 1 minus 2 m over r to the minus 1 dr squared minus r squared d omega squared. Okay, so this is the Schwarzschild metric. So we have that in the weak field limit we want this metric to recover the Newtonian gravity, because in that kind of regime, of course, Newtonian gravity works well. And so we have that by asking this, we find that this m has to be equal to capital M times G. and then what else? We have that looking at this metric, of course, we find that mg over c squared, okay, where in natural units c is equal to 1, so that's why I wrote mg before. Okay, and we have that this solution is found as the solution outside of a spherical symmetrical source. Okay, due to Birkhoff's theorem we have staticity. So if the star oscillates, pulses, conserving its spherical symmetry, the solution won't change. The solution outside of the source won't change. It will stay like this. And we have that the oscillations of quadruples, they actually change the metric, and in that case we would have gravitational waves. We would have some metric that depends on the time, and so gravitational waves in the linearized theory. Okay, so looking at this metric, we can see that there are two singularities. The first one is that one in r equal to 0 here, and the second one is that one in r equal to 2m in here. So we want to understand which is the nature of these two singularities. We will see that r equal to 0 describes a physical singularity, while r equal to 2m describes a coordinate singularity. So we will be able to remove this singularity just by working on some appropriate extension of the metric, in which the metric is non-singular, of course. Okay, first of all, we have to say that most of the astrophysical objects in the universe, they do not show these two singularities because they have a radius that is bigger than 2m, and so the problem won't hold. Actually, in the neutron star case, we do already have some problems, because in that case we have that the radius is a little bit greater than 2m, but still we already can discuss some particular features. And then in the case of the black holes, of course, the two singularities, these two singularities would exist, and so we need to talk about them. Okay, so let me already show some suggestions, some hint of the fact that this is not a physical singularity but just a coordinate one. And let me show that if I consider the proper radial distance between some point at a distance that is equal to capital R from the center of the system, so from R equals 0, and the horizon, the proper distance will be ds squared, that is taken, of course, at t tan phi constant as t tan phi because it is radial. Okay, so the squared equal to minus 1 minus 2m over r to the minus 1 dr squared. Okay, such that dl is equal to dl squared is equal to minus t squared, and so in the end we find that L is equal to the integral of dr over the square root of 1 minus 2m over r in the range 2m r. And we have that this integral, it is finite. So we have that if the proper distance is finite, probably actually we have that if the proper distance is finite, it means that the proper time that is needed to travel this proper distance is finite as well. And so this is already a suggestion of the fact that the 2m singularity is just a coordinate singularity. Okay, then let's consider an observer moving on a geodesic with some affine parameter that is equal to s. Okay, and it would look like this. We have that its coordinate is x mu of s. Okay, the geodesic equation, it is equal to the squared, the second derivative of x mu with respect to s, plus gamma mu alpha beta the x alpha in the s times the x beta in the S equals to 0. Okay, so we have that in principle from this equation, using the fact that since we are considering a geodesic, a sine has to be equal to 0 and a sine has to be equal to minus u3, which are the two killing energies associated to the killing time vector and to the spherical symmetry. Okay, so in principle we would be able to find r dot equation using this free constraint, this equation and these two constraints. But there is another way to proceed, and it is that to consider the two killing energies plus the relation umu equal to 1, which corresponds to the normalization of the for velocity plus the condition, of course, of the trajectory being a physical one, and that's why we have that this is greater than 0, this is time-like, okay? And so we find that this would mean that e sine squared over f minus r dot squared over f, of course it comes from the calcula, minus L sine squared over r squared is equal to 1. Okay, that can be written as well as r dot squared plus v effective equal to e sine squared, where v effective is equal to 1 plus L sine over r squared times times 1 minus 2m over r. Okay, so this is the effective potential that we find in the case of Schwarzschild. That is given by 4 terms. The first one is just a constant, and it is 1. Okay, then we have minus 2m over r. Then we have the term in the 1 over r squared, is this one. And finally we have a term that is in 1 over 3 squared, that is 2m L sine squared, okay, over r to the third. Okay, so we have that this would be the Newtonian potential. So we can see that the difference between the Schwarzschild potential and the Newtonian one is in this constant and this term. The constant, it is just a shift, so it is not so important, but this term actually makes the whole difference, because as r gets close to 0, this term wins over this, and so it determines a different behavior from the Newtonian case. Let me show that. We have that in the Newtonian case we would have something like this. This is r, this is the potential, okay? As L is equal to 0 in the Newtonian case, we find that this would be our potential. It would be negative, it would have some shape like this, and so particles coming from infinity with energy greater than 0, of course, they would get to the r equals 0, there is this one, okay, and bounce back to infinity. So it is possible to go towards the r equals 0, and it is possible from r equals 0 to go to infinity. While in the case where L is greater than 0, in the Newtonian case we would find that as r tends to infinity, this tends to 0, so the shape would be something like this, okay? And so we would have that particles coming from infinity with energy greater than 0, they cannot reach the r equal to 0, but they bounce back at a different value of the radius, and so we would have some potential wall in here that would make it impossible to reach the r equal to 0. Okay, and so this is what we find in the Newtonian case. In the Schwarzschild case, we have that, first of all, as r tends to infinity, the effective potential tends to 1. Okay, and so if this is 1, we have that this potential asymptotically has to go to 1. Okay, we have that when L is minor than 12 m, when L squared is minor than 12m squared, we find that the potential has a shape like this. Okay, so it looks like the Newtonian case when L is equal to 0. It doesn't show any maximum or any local maximum or minimum. It just goes to 1 asymptotically. So this means that particles coming from infinity with energy greater than 1, they do have the same behavior that we've seen in the Newtonian case, while particles with energy minor than 1, they would be bounded between some value of the radius and the zero of the system. Okay, but in the case when L squared is greater than 12m squared, the things change. Actually, they get interesting because we have that the shape of the potential would be something like this. Okay, so we would have that there is a local maximum in here and a local minimum in here. Okay, so two circular orbits exist, with this being the unstable circular orbit and this being the stable one. Then we would have that particles with energy greater than the one of the local maximum, they can go towards the r equals 0, or either they can go from r equal to 0 to infinity. Particles with energy that is greater than 1 and minor than the one in the local maximum, they will come from infinity and bounce back at infinity, as there is this potential barrier. And for values of energy bounded between the one in the local minimum and 1, we would have bounded orbits, and actually we would also find a stable circular orbit, as already said. And then for values of r minor than 2m, we are not able to describe the orbits because we would have negative energies. Okay, and so this is the picture we have for the effective Schwarzschild potential, that of course is very different from the Newtonian case. Let me also show what we would have in the case of light, since in the case of light we would have that this relation has to be changed in this way. We would have that mu has to be equal to 0. Okay, and so the effective potential would look like this. Okay, and so what we find in here, it is that in the case of Newtonian gravity, light can just go straight, so coming from infinity it reaches r equal to 0, and from r equal to 0 it can go to infinity. While in the Schwarzschild case we find something very interesting. When L is equal to 0, we have the same behavior, but when L is different from 0, actually we have that the shape of the potential looks like this. Let me show. Okay, there is a local maximum and then it goes down to 0 asymptotically. Okay, and so this means that actually in the Schwarzschild case, light has a circular orbit. It is unstable, but still it is circular, and it corresponds to the values of to the value of radius of r equal to 3m. So we talk about the so-called photonic sphere. In this case, so we have that light can move in circular orbit, so in circular orbits, and that's because in the case of general relativity theory, light just follows the geodesics. So the geodesics, they are curved because the space-time it is curved in the presence of a mass, and so light can move following a path that is not straight. Okay, so now we go back to this case. Do we? Yes. Okay, so now I want to show that the proper time for an observer falling free falling into the r equal to m horizon, it is finite. To show that, I will take r dot from here. Okay, I have that r dot, it is equal to minus the square root of e squared minus v effective. We took the minus sign because we are considering an observer that is falling. Okay, and so we have that r dot, it is equal to dr in ds. Okay, and so we find that we can invert the relation and find that ds is equal to dr over r dot, such that as there is the proper time, it is equal to minus dr over the square root of e sine squared minus v effective, that is this stuff, okay, from between r and 2m, and we find that this is finite. So a finite amount of proper time is needed, is measured by the free falling observer to fall from r to 2m. Okay, now we have a look at what happens to the Schwarzschild time t. We have that r dot, it is equal to dr in ds, and it is equal to, of course, it is equal to dr in dt times dt in ds. Okay, we have that dt in ds, it is equal to u0 with 0 up, and so we have that u0, it would be equal to g0 u0, okay, that is equal to e signed from here over g00, that is equal to f, 1 over f. Okay, and so if I plug this inside of this, I find that dr in dt squared times e sine squared over f squared plus 1 plus L sine squared over r squared times 1 minus 2m over r equal to e sine squared will take us to dr in dt squared equal to f squared, that is equal to, maybe I can already take the square root. Okay, I have that this would be equal to 1 minus 2m over r squared times 1 over e sine squared times e sine squared minus 1 plus L sine squared over r squared times 1 minus 2m over r. Okay, and so I have that from here, I get that dt in dt, so I can already integrate. I have that t, it is equal to minus the integral in dr of is signed over 1 minus 2n over r square root E sine squared minus 1 plus L sine squared over R squared times 1 minus 2m over R. Okay, and we have that actually as t tends to 2m, while this quantity did not diverge as r tends to 2m. Okay, in this case we have that this quantity diverges when r tends to 2m, and so because of this term, and so what we get is that the Schwarzschild time goes to infinity as r tends to 2m. Now we have to understand what's the physical meaning of this thing. So we have to understand what the Schwarzschild time is physically. It is quite easy to show. We have that if we consider a static observer, so with r, theta and phi const, we have that ds for a static observer, it is equal to 1 minus 2m over r dt squared, and so as r tends to infinity, ds squared, is equal to dt squared. That means that the Schwarzschild time, it is the proper time of a static observer at infinity. So this means that as the observer free falls towards r equal to m in a finite proper amount of time, the asymptotical flat observer, the asymptotical static observer, won't be able to see the free falling observer reach the r equal to m singularity. Okay, and so looking at this, we can already see that something weird happens when r gets to m. We have that d squared is equal to 0. That is something that is found for light, so it looks like the only static observer, the only possible static observer in r equal to 2m, it is the light, and as r is minor than 2m, this becomes negative, so it means that no static observer can exist for r minor than 2m, but this will be better shown later. Okay, so let me erase. Okay, so if you make a measurement that is non-local, you will experiment the so-called tidal forces. So these are the result of the non-local measurement, as I just said, and they are proportional to the Riemann tensor. So if we consider two particles that move along two different radial geodesic towards the r equals 0, we get that they have a relative acceleration between them that is measured in terms of the Riemann tensor, and we can see that this kind of force it diverges when r tends to 0, so we have no divergence in r equal to 2m. Moreover, if we consider the tidal forces on the radial direction, we have that if we have an extended object falling along a radial geodesic, the gravitational field will be stronger closer to the horizon, and will be of course weaker farther from the horizon, farther from the source, I'm sorry. And so this means that an extended object that falls towards the black hole, it gets stretched in the radial direction and squeezed in the direction that is orthogonal to the radial one. And this kind of divergence, the divergence of the tidal forces, it is measured just in r equal to 0. This means that dr equal to m singularity, it is just a coordinate singularity. So we finally found what we wanted to observe. Okay, so before we go and try and remove the r equal to m singularity, okay, let me show what happens to the static observer near to the Schwarzschild horizon, to the r equal to m horizon. So let me consider a static observer in this metric that is given by so a static observer in this metric, there are some velocity mu that is equal to u0, 0. We have that the normalization condition holds such that mu has to be equal to 1, and so u0 has to be equal to 1 over the square root of g00, so 1 over the square root of 1 minus 2m over r. Okay, we have that the acceleration, okay, the acceleration, it is the covariant derivative of mu with respect to s affine parameter along the geodesic. Okay, and we have that this can be written as d mu in ds plus gamma mu, this is the Christoffel symbol, times the times, yes it is the x alpha in ds, but we can write it as u alpha times u beta. Okay, so we have that the mu in ds is equal to 0 because this does not depend on s, and of course all the other components they are equal to 0, so this is equal to 0. While in here we would have that the only non-vanishing element, it would be that one in alpha equal to 0 and beta equal to 0. So this means that we are only interested in the gamma mu 0, 0 Christoffel symbol, that would be 1 over 2 g mu nu times g0 nu 0 plus g0 nu 0 minus g00 nu, but we have that the metric it is static, so these two elements they have to be equal to 0, while this one it would be, we have that nu has to be equal to r in order to have a non-vanishing element in here. So this means that as nu is equal to r, mu has to be equal to r because the metric has a diagonal form. Okay, and so we find that the only non-vanishing Christoffel symbol it is gamma r tt, that is equal to 1 over 2 gtt, that is equal to minus, the minus gets away with this one, the inverse of this, that is 1 minus 2m over r, times the derivative of g0 with respect to r, and so minus plus yes 2m over r squared. Okay, then we have that as the only non-vanishing Christoffel symbol it is that one for mu equal to r, the only non-vanishing element of the acceleration it is that one in mu equal to 1, so to r. This means that a1 or ar it is equal, it is given by gamma 1 0 0 u0 squared, that is u0 squared it is g00. Okay, let me see if I did everything in the right way. Okay, there is something that is off, I would say. No, okay, I'm sorry. Yes, of course, u0 squared would give a 1 over g00 that would cancel with this, and so we find that a1 it is equal to 1 over 2, so this 2 it goes away, so m over r squared. This is what we find. Is right? Yes. Such that a mu it is given by 0 m over r squared 0 0, and so we have that a mu it is equal to minus 1 minus 2 m over r times m squared over r to the fourth. Okay, because it would be yes, g11 times a1 squared, and we have that, of course, as r tends to 2m, this diverges. This goes to infinity. And so this means that an infinite acceleration is needed to be static on the horizon. So, of course, this means that no physical observer can be static on the r equal to m horizon, and so that's why we found that only light can be static, but we will see what this means. We'll better see that later. Okay, and so now we want to go back to the Schwarzschild metric and try and find some extension in which the extension of the metric in which the r equal to m singularity does not exist. It is not shown, since it is just a coordinate singularity, as we said. While the r equals 0 singularity, it is a physical singularity, so it won't be possible to remove that. Okay. So, is it possible to find is it possible to find a reference frame without the r equal to m singularity? Of course it is. We have to perform some singular coordinate transformation that brings the metric to a non-singular one. The fact that the coordinate transformation is singular won't be a problem, it's not a problem, because in principle the fact that a non-singular metric exists is already sufficient for that metric to be a solution of the problem. In fact, we have that general relativity is a covariant theory, so it does not depend on the coordinates that we choose, and so we could have found the non-singular solution as the first solution of our problem, and then moving with a singular coordinate transformation we would have found the Schwarzschild solution. So we are perfectly fine with that. There are two ways to proceed. We can either go and find the so-called null coordinates and then build and then find a matrix defined on the null coordinates. We will see that we will be able to remove the r equal to m singularity, or we can work with time-like geodesics and find the so-called Penleve metric. The second approach, it was actually the one that was performed that was performed first, but we will start with the approach with the null coordinates, because it will make us easier to discuss various things. We will see that the discussion will be very very large in that case. Okay, so first of all, let me show how we would build how we would find a metric built on the null coordinates in the case of Minkowski. So we have that in the Minkowski case, ds squared is equal to dt squared minus dx squared minus dy squared minus dz squared. That can be written as well as dt squared minus dr squared minus r squared d omega squared in spherical coordinates. Okay, so I want to find radial null geodesics, and those are found just by asking the s squared equal to 0 and theta and phi constant. Okay, and from here I get that dt in dr is equal to plus minus 1. I get it from here. So this means that t minus r is equal to a constant and t plus r is equal to a constant. These are the geodesics of light in Minkowski, and these are the outgoing geodesics, and these are the ingoing geodesics. So if I call this u and if I call this v, I found the two null coordinates, where u is defined as the retarded coordinate and v is defined as the advanced coordinate. Once we have those, we have that we're able to switch from dt to du, and so dt would be equal to du plus dr, while in here we would have that dt would be equal to dv minus dr. Okay, and so we can plug those inside of the metric and find that, okay, and find that ds squared is equal to dv squared minus 2 dv dr minus r squared d omega squared, or du squared minus plus 2 du dr minus r squared d omega squared. The calcula, they are very simple. I won't do it again because I did it a lot of times. So now of course I just remember the result, but we will be able to find this. This is the so-called advanced Minkowski metric, and this is the retarded Minkowski metric. Okay, then from here we can also see that t is defined as v plus u over 2 and r is defined as v minus u over 2, so that using this parameterization in this metric, we can find the double null metric that is given by ds squared equal to du dv minus r squared d omega squared, where of course now r is just a function of u and v. Okay, and this is the double null metric. Now let me define the induced metric, because we will need that in our discussions, in our later discussions. And I have that the induced metric, it is the metric that is given on some surface sigma given by a function of the coordinate equal to 0. So I have a constraint on my coordinates. This constraint gives me some hypersurface sigma, and the metric on the surface, it is called induced metric. So when the metric is in the diagonal form, it is very easy to show what the induced metric would look like. So for example, in Minkowski, we have that the sigma given by t const, okay, as an induced metric that is ds squared induced equal to minus dr squared minus r squared d omega squared. So the signature is minus minus minus. This means that this hypersurface, it is space-like, while the sigma given by r const, it has an induced metric that is equal to dt squared minus r squared d omega squared. So the signature is plus minus minus. Okay, so the hypersurface, it is space-like, while in the u and v constant case, we get that ds squared is equal to minus r squared d omega squared, the signature 0 minus minus. So this is a null surface, and actually in the u case we have that it is an expanding to sphere, a sphere that expands at the speed of light. And in the v case, in the v const case, we have that it is a two-sphere that is contracting at the speed of light. Okay, there is another way to find the nature of the sigma surface, and it is that to consider the normal vectors to the surface. So we have that given 2 points P and Q associated to some coordinates. So for example, P is associated to some x of alpha and Q to some x of alpha plus the x of alpha. As P and Q belong to the hypersurface sigma, one finds that f of x alpha has to be equal to 0, while f as Q belongs to the sigma surface as well, f of x alpha plus the x alpha has to be equal to 0. But this can be expressed as s of x alpha plus the derivative of f of x alpha of f s of x alpha, doesn't matter, with respect to x alpha times the x alpha. Okay, this is equal to 0 by hypothesis. This has to be equal to 0 because Q belongs to the hypersurface, and so this means that the derivative of f with respect to x alpha and x alpha, they have to be orthogonal. But the x alpha is a vector that lives on the surface sigma because it moves the point, it moves from P to Q. Okay, and so this means that the derivative of f with respect to x alpha, it is orthogonal to the hypersurface. So the most general vector, the most general orthogonal vector to the hypersurface, it is given by u alpha equal to some lambda of x times the derivative of f with respect to x alpha. Okay, so now we can study this vector and see if in the different cases when given some condition, given some function f, and see what's the nature of this vector to understand what's the nature of the hypersurface. So for example, if we take back all the examples that we have shown before, we have that sigma defined by f of r equal to 0. Oops. Okay. So for example, if our surface sigma is defined by r const, so with our function of x being some r minus constant equal to 0, this means that u alpha has to be equal to, first of all, we have that the derivative of the function with respect to x alpha is equal to 0, 1, 0, 0. Okay, and so this means that u alpha it is equal to minus lambda squared. That of course is negative, and so this means that u alpha it is a space-like vector and r const is a time-like hypersurface. Then we have that in the t const case, the derivative of f with respect to x alpha it is equal to 1, 0, 0, 0, such that u alpha it is equal to lambda squared, and so the u alpha orthogonal vector it is time-like, and this means that the t const hypersurface it is space-like. And of course we find that in the u and v case the u alpha would be equal to 0, and so the orthogonal vector it is null, and so the hypersurface it is null. Okay, this means that in Minkowski eventually being at constant r, everything will be known, and this makes sense with the fact that the light cones in Minkowski they look like this. Okay, given some point p in the Minkowski space, the light cones they look like this. They are these two lines at 45 degrees, and so for infinite time we have that everything falls inside of this light cone, of the past light cone, and everything of course at infinity it is inside of the future light cone. Okay, so we finished our discussion on Minkowski. Now we're able to look at Schwarzschild. So we want to do the same stuff in Schwarzschild. We want to find the null coordinates in Schwarzschild in order to be able to remove the r equal to m singularity in some appropriate extension of the metric. So let me erase the board. Okay, so as we did before, we want to study the radial null geodesics. So ds squared has to be equal to 0 and d and phi they have to be constant. Okay, in this way one finds that dt in dr it is equal to plus minus 1 minus 2m over r to the minus 1. Okay, so what does this mean? That as r tends to infinity, the light cones they are as in Minkowski. When r is equal to 2m, the light cones they shrink into a straight line, so they collapse into a straight line. And as r is minor than 2m, they actually flip. So we get that this would be the picture. This is 2m, this is 0, this is r, okay, and this is t. Okay, so light cones at infinity they would look like this at r equal infinity. Then we can see that they shrink as we get closer to r equal to m. They collapse into the straight line, and then in this region they flip like this. So inside of the r minor than 2m region we have that the space becomes a time and the time becomes a space. This is very weird, but it's something that we find from by looking at the metric. Okay, so we want to we want to find the null coordinates, and so we want to find some dt in the r equal to plus minus 1 as we did before, and to do so we define the so-called Tartwas coordinate r star that is equal to r plus 2m times logarithm of r over 2m minus 1, okay, such that dr star is equal to dr times 1 minus 2m over r to the minus 1. It is actually quite easy to show, to compute, but I won't do it, of course, because I have a lot of stuff to say. And so I get to dt in dr star equal to plus minus 1. Okay, so this means that t minus r star is constant and t plus r star is constant. So in these new coordinates with the Tartwas coordinate r star defined in this way, we find that the null geodesics they are given by t minus r star constant and t plus r constant, where this can be called u, t minus r star is equal to u, and this can be called v. This is the so-called retarded Eddington-Finkelstein coordinate, and this is the so-called advanced Eddington-Finkelstein coordinate. So now we are able to replace dt in the Schwarzschild metric with dv or du and find the advanced and retarded Eddington-Finkelstein metric. So the first one, the advanced, it would look like ds squared equal to 1 minus 2m over r dv squared minus 2 dv dr minus r squared d omega squared. And the second one, it would be ds squared equal to 1 minus 2m over r du squared minus plus 2 du dr minus r squared d omega squared. Again, all the calcula, I won't do it because I already did them lots of times, but they are not very difficult. You just have to plug this parameterization in the metric. Okay, and of course then I will be able to go to the double null metric, but that we will do it later. So this is the advanced Eddington-Finkelstein metric. This is the retarded Eddington-Finkelstein metric. Let me consider. We can see that in both of the metrics there is no more any irregularity in r equal to 2m. So we are perfectly fine with these. With these two metrics, but now let me study the two metrics and show the differences. and then we will see that we will further need to work on the extension of the metric. In fact, we have that if I take the first one, the advanced metric, I have that the radial null geodesics, they're given by ds squared equal to 0 and theta and phi constant. Okay, that means that dv times 1 minus 2m over r dv minus 2 dr has to be equal to 0. And so the two solutions that one finds are dv equal to 0, so v constant, and that of course is trivial because we have that v is a null coordinate. Okay, and so this is the first null geodesic that we find, and the second one, it would be given by dv in dr equal to 2 over 1 minus 2m over r. Okay, so if we don't want to work with the null coordinate, we can do another thing. We can consider the so-called Eddington-Finkelstein time that is defined as t equals to v minus r, t prime equals to v minus r, and so of course we have that as v is equal to t plus r star, this means that the Eddington-Finkelstein time, it is equal to t minus 2m times the logarithm of this stuff. Okay, and so we get that from here dt prime is equal to dv minus dr, so dv is equal to dt prime plus dr. We plug it inside of the metric, and we get that ds squared is equal to 1 minus 2 m over r. Then dt prime squared plus 1 minus 2 m over r dr squared. Okay, plus 1 minus 2 m over r, and then we have the double product of dr and dt, so 2 dt 2 dv no 2 dt prime, sorry, dr, okay, minus 2 dv dr, so dt prime dr minus 2 dr squared, okay, minus r squared d omega squared. So we have that 2 dt prime dr, it cancels with this one, okay, then this minus 2 dr squared enters this, okay, and one finds that this can be written as 1 minus 2 m over r dt prime squared minus 1 plus 2 m over r dr squared minus 4m over r dt prime dr minus r squared d omega squared is equal to ds squared. Okay, and so this would be the advanced metric in the Eddington-Finkelstein advanced time, in the Eddington-Finkelstein time. Okay, so now we study the null geodesics in this metric, and we have that ds squared is equal to 0, theta and phi, they are constant. So we find that 1 minus 2m over r dt prime in dr squared minus 4m over r dt prime in dr minus 1 plus 2m over r, it has to be equal to 0. Okay, and so the solution for dt prime in dr in this equation, we find two solutions. The first one, it would be given by dt prime in dr equal to minus 1, and that this would correspond to the v const. Okay, and then the second one would be, the second solution would be dt prime in dr equal to 1 plus 2m over r over 1 minus 2m over r, such that dr in dt prime it is equal to 1 minus 2m over r over 1 plus 2m over r. There is greater than 0 as r is greater than 2m, equal to 0 as r is equal to 2m, and minor than 0 as r is minor than 2m. Okay, so we're finally able to draw the graph that is associated to this metric, and we would have that as this is r and this is t prime Eddington-Finkelstein time, if this is 2m, we have that these geodesics, these geodesics, they would look like this. In r equal to m, it is in r equal to m, we find a straight line going up. Then for r greater than 2m, the shape would be something like this. Okay, and in r minor than 2m, we would find something like this. Okay, while dt prime in dr equal to minus 1, we said that it is v constant, so we have this. Okay, so these geodesics, they would correspond to the ingoing null geodesics, while these geodesics, they would correspond to the outgoing ones. We can see that outside of r equal to 2m, the outgoing geodesics, they actually leave the source, they go outwards. Okay, and we can see that outside of the r equal to m region, we find that the light cones, they look like this. Okay, and so we have that in this region the future light cones, they do include the r minor than 2m region in the future, but not in the past. While inside of this region, for r minor than 2m, we find that the light cones, they do not include this region in their future, and actually all the trajectories, even the trajectories of light, they have to go towards the r equals 0 singularity. Okay, so what we just found, it is called a black hole. This defines two regions that are not causally connected. We have that nothing from inside of a black hole can escape the black hole, because all the trajectories, they go to r equal to 0. Okay, so now we can better understand what we found earlier, for example, for the Schwarzschild time, because we can see that as an observer falls along some physical trajectory to the r equal to 2m. For example, let's say that this is a time-like geodesic. Okay, so the observer follows this geodesic and falls towards the r equal to 2m. Let's say that the observer emits some photons. Okay, as the observer goes deeper and deeper towards the r equal to m, we can see that the light follows these lines that actually spread out. So we have that the time that is measured asymptotically, the time interval, it spreads out it gets bigger and bigger. These intervals, they get bigger and bigger, and eventually they go to infinity. And no, and moreover, we have that not only the time interval for these light signals to reach us gets infinite at a certain point, and so it would become unphysical because it would not be measurable, but also it gets redshifted. The light gets redshifted as the observer falls towards the r equal to m surface. Okay, and let me show this last assumption. So let me erase the board. Okay. So let's consider an observer that is falling towards the r equal to m singularity. Okay. So it is free falling, so it is moving along a geodesic, a time-like geodesic. Let's say that it emits some photon with a momentum p mu, while the velocity of the free falling observer is u mu f. So we have that, and then we have a static observer. Okay, that measures the photon. So we have that for the static observer, one finds that u mu s is equal to u0 s 0 with u0 squared that will be equal to 1 over g00 due to the normalization condition, u mu equal to 1, because the static observer outside of the r equal to m region, of course, it is physical. So we have that u0 would be equal to 1 over the square root of g00 in rs, I would say. u0s is equal to 1 over the square root of g00 in rs, that is the radius of the radius of the static observer. Then we consider the free falling one, and we have that in this case one finds that u mu ff it is equal to u ff0 u ffr, and then if we consider a radial motion, we have that these two components they are equal to 0. Something that I forgot to mention earlier, it is that okay, very important thing, that when I talk about Schwarzschild, I always consider u theta equal to 0 and theta equal to pi over 2 without any loss of generality, because due to the spherical symmetry I'm able to study the motion on a plane. So that's why, for example, when we saw the potential, I only had 3 terms from the scalar product of u mu with itself. Okay, so this is we get this from the hypothesis, and we get this 0 because we are actually saying that the observer is falling radially, and so the angular momentum L, of course, is equal to 0. Okay, and so we have that u f0 would be equal to some E sin, okay, while u okay, it doesn't matter, we don't matter about the third component because we said that we ask it to be equal to 0. Okay, so from the normalization condition we find that u ff mu times u mu ff has to be equal to 1, such that E sin squared over f, that is 1 minus 2m over r, as always, minus u r squared over f has to be equal to 1, such that this is ff, okay, such that uff of r, it is equal to, we take the solution with the minus sign because the observer is falling, so minus the square root of e sine squared minus f. Okay, finally we have that for the light one finds that P0 it is equal to E. Let me see, okay. So from here we have that uff0 it is equal to E sine over f. So I want to keep all the velocities with the I index. Okay, so okay, perfect. Then P0 is equal to E because light of course moving along a geodesic, the null geodesic, so we have that there is this killing energy. And then we have that from the P mu equal to 0 condition that holds for light, we find that E squared over f minus PR squared over f has to be equal to 0. That means that as the light is outgoing, because it is emitted to escape the black hole, the attraction of the black hole. Okay, we have that this would be equal to, we would find PR equal to E. Am I right? Yes, PR equal to E. That means that PR low index, it is equal to GRR PR, so minus E over F. Okay, and so finally we are able to find the local energy that is measured as the scalar product between P mu and O mu, and so we have that the local energy for the static observer, the local energy the static observer measures for the photon, it is given by P0 U0s, because that's the only non-vanishing component, so it would be E over the square root of G00 in Rs. Okay, and this would be equal to H nu s, because that's what we have for light, that E is equal to H nu. And for the free falling observer one would find that the local energy that is measured, it is equal to E over F times E signed. Okay, then we have this minus sign with this, so plus the square root of E sine squared minus F. Let me see if this is right. So at this point we found that the local energy for the measured by the static observer is this one, and the local energy measured by the free falling observer is this one. Of course, the local energy measured by the free falling observer would correspond to the actual energy of the photon, because the free falling observer, it is the one that is emitting the photon. So at this point we have that nu s is equal to nu ff times 1 minus 2m over rs, where rs it's not this one, we say or even better, we can say just r. It will be the radius of the observer that is free falling, okay, divided by the square root of 1 minus 2m over r0, where r0 this time it is the radius of the static observer, and then we have to divide by all of this stuff. So E sine squared no, e signed, plus the square root of e signed squared minus 1 minus 2m over r. Sorry if I'm writing like shit, but I have to be fast. Okay, and so what we see from here, it is that as r0 is fixed because the observer is static, there is no problem with this, of course, as long as the observer is not on the, as long as the static observer is not on the horizon, on the r equal to m horizon. Okay, while we can see that as the free falling observer gets to m, this clearly goes to 0. So nu s goes to 0 as r tends to m. Okay, and so we actually proved we just proved the redshift. Okay. Now we want to study again the yes, we want to study again the Schwarzschild metric, but this time in the retarded Eddington-Finkelstein coordinate. So we will do the same stuff that we did for the advanced one, okay, but we will get to different conclusions. That's the important thing. And so, of course, at that point we will need to further work on the extension of the metric to get to some conclusion. Conclusion? I don't know. Okay, so the retarded Eddington-Finkelstein metric, it looks like 1 minus 2 m over r du squared plus 2 du dr minus r squared d omega squared. Okay, and we have that as ds squared is equal to 0 and theta and phi are constant, we find the radial null geodesics. So as always we get that du has to be equal to 0 and du in dr it is equal to minus 2 over 1 minus 2m over r. Okay, but as we did before, we want to okay, sorry, just looking for something. Okay, perfect. We want to work with Eddington-Finkelstein time because then we'll be able to draw the graph in a clear way. And so I have that Eddington-Finkelstein time that this time I call t at. It is equal to u that is equal to t minus r plus r, such that it will be equal to t plus 2m times the logarithm of r over 2m minus 1. And so I have that in this way I find that du it is equal to dt at minus dr, and if I plug this inside of the metric I find that ds squared is equal to 1 minus 2m over r d t at squared, okay, plus 1 minus 2m over r dr squared, okay, plus 2 okay, so minus 2 1 minus 2m over r dt at dr plus 2 dt at dr minus 2 dr squared minus r squared d omega squared. And so we have that this goes away with this one, and so we are left with 1 minus 2m over r times dt at squared minus 1 plus 2m over r dr squared plus 4m over r, because before it was a minus, if I'm not wrong, dt at dr minus r squared d omega squared equal to ds squared. So we found that this is the retarded Eddington-Finkelstein metric in the Eddington-Finkelstein time. At this point, as before, we have that ds squared equal to 0 and theta and phi const. They will give two different solutions. The first one, it is dt at in dr equal to 1. There is u constant. And the second one is dt at in dr equal to minus 1 plus 2m over r over 1 minus 2m over r, such that this time dr in the t it is minor than 0 as r is greater than 2m, equal to 0 as r is equal to 2m, and greater than 0 as r is minor than 2m. Okay, now we are able to draw the graph again, and we have that in this case, I will draw it here. Okay, I'm sorry if this part of the board it is not very visible. Okay, and so I have that this is r, this is t at, and so this is r equal to 2m, and this is, we start by drawing these geodesics. So in r equal to 2m we would find something like this, because as r is equal to 2m this would be 0 exactly. So dt prime in dr it would be equal to minus infinity. Okay, and then I would find that this would be the ingoing geodesics, because these are the outgoing ones. Okay, and then I go on and find this. Okay, while the outgoing geodesics are given by the u const, they look like this. Okay, so what do we see from here? In this graph we have that the light cones in the region for r greater than 2m, they do not include the r minor than 2m region in their future, okay, but include it in their past, while inside of the r minor than 2m region, the light cones, they do include this region in their future, but not in their past. And moreover, we have that inside of this region, light can only move, cannot go to r equal to 0, to the r equal to 0 singularity, but it can only leave the region or go to r equal to m. But in this case, we have that the light can either go to r equal to m or can either go to r equal to m or move outwards, just leave the just go to infinity. Okay, and so what we find in here, it is called a white hole. Nothing can reach the singularity, everything is expelled. And if we look at the if we look at what happens if we make the same discussion that we did for the redshift in the case of a black hole, here we would find a blue shift. So we would find that this object would be extremely unstable, because a little perturbations, they would just be blue shifted. And so now we ask ourselves, what's the physical solution? Is it the black hole or is it the white hole? Because it looks like none of the two can describe the effective potential that we had in the Schwarzschild case. Because let me just draw the effective potential very quickly. We have to keep in mind that the effective potential showed some behavior like this. This was 1, okay. This is r, okay. So it looks like particles can come from infinity and go to r equals 0, and this would be the case of a black hole. but can also go from r equals 0 to infinity, and this would be the case of the white hole. They cannot be verified both at the same time in the two descriptions that we found, while all the other cases they are not relevant. In here we don't have any description. Okay, so we want to understand what kind of object does the Schwarzschild metric describe. And to do so, we have to go to double null coordinates and then to Kruskal, because because at this point it is clear that the two metrics, even though they are not singular in R equal to 2m, they are not complete. They do not describe the entire space-time manifold. Okay, and so let me go to the double null metric. It is very easy. We have that T is defined as V plus U over 2 and R is defined as V minus U over 2. So we just plug that inside of the metric and find that 1 minus 2m over R du dv minus r squared d omega squared, it is equal to ds squared. We remember that r star it is equal to r plus 2m times the logarithm of r over 2m minus 1. Okay, but also we have that this is equal to v minus u over 2. Okay, of course, before I said r equal to v minus u over 2, but that was not true. It is r star that satisfies that kind of relation, because we had to define the Dartois coordinate to find the null coordinate. Okay, and so now we are able to have some relation like this: v minus u over 2 minus r. Okay, we can divide by 2m, and so in here we would have 4m, and in here we would have divided by 2m equals to the logarithm of r over 2m minus 1. Then we take the exponential, and we have that this would be e to the v minus u over 4m times e to the minus r over 2m equals to r over 2m minus 1. That is equal to r over 2m times 2m over times 1 minus 2m over r. Okay, and so we are able to plug this inside of this and find that ds squared is equal to 2m over r times e to the v minus u over 4m times e to the minus r over 2m. Okay, times du dv minus r squared d omega squared. Okay, and so okay, at this point we can define the so-called Kruskal coordinates, such that capital U is given by minus 4m times e to the minus u over 4m, and capital V is defined as 4m times e to the v over 4m, and so we have that du it is equal to e to the minus u over 4m times du, and dv it is equal to e to the v over 4m dv, so that e to the v minus u over 4m du dv it is equal to d capital U d capital V. Okay, and so we can plug this in here and find that ds squared in the Kruskal coordinates, it is given by 2m over r times e to the minus r over 2m times du dv minus r squared, where r of course now is a function of u and v, times d omega squared. Okay, we can and this metric as double null, they are not irregular in r equal to m, so we're perfectly fine with this metric. Okay, let me see if I'm forgetting something. No. Okay, now I can define the Kruskal-Sekers coordinates, where t, capital T, is equal to v plus u over 2, and capital X it is equal to v minus u over 2. Okay, so from here I get that v is equal to t plus x, and u is equal to t minus x. Okay, yes, okay, and so dv du it is equal to dt squared minus dx squared. Okay, and so I finally find the Kruskal-Zecker matrix. There is ds squared equal to 2m over r times e to the minus r over 2m times dt squared minus d capital X squared minus r squared d omega squared. Okay, so this is the Kruskal-Zecker matrix. It is regular in r equal to m, so there is no more the r equal to m singularity, but we still have the r equal to 0 singularity, of course. And now we need to understand how we could draw this metric in these new coordinates. So first of all, let me have a look at the null geodesics, the radial null geodesics. We have that the s squared has to be equal to 0 and theta and phi have to be constant, and one finds that these two assumptions dt squared minus dx squared has to be equal to 0, and so we find the Minkowski light cons dt in the x equal to plus minus 1. So we have that in Kruskal-Zeckers the light cons they are, as in Minkowski, two lines at 45 degrees. Okay, but as the light cons could be trivial, we have that the physical interpretation of the coordinates it is not the physical interpretation. So yeah, the interpretation of the coordinates it is not. Let me work on this. No, on this. So I will keep the Kruskal-Zecker matrix here. Okay, we can work on this relation, and we have that e to the v minus u over 4m it will be equal to minus uv, okay, times over 16m squared. Okay, so here there is a minus, equal to e to the r over 2m times r over 2m minus 1. Okay, then we have that the product between u and v it is equal to t squared minus x squared, so the signs are flipped because of the minus. We get x squared minus t squared equal to 16m squared times e to the r over 2m without the brackets, e to the r over 2m times r over 2m minus 1. Okay, and so we can see that as r is equal to 2m, this is equal to 0, so x squared minus t squared equal to 0 means that we found the two 45 degrees lines. Okay, then we get that as r is equal to 0, this will be equal to minus 1 if the 16m squared is reabsorbed into the coordinates, and so we would have two hyperbole. We would have two branches of hyperbole. Okay, and then we have that as r is constant, this equation describes hyperbole. Okay, and so yes, okay, I can already draw the graph. We have that as this is x, capital X, and this is capital T. Okay, this is, oops, these two lines going through the origin, they are they would be u and v, and they are they would correspond to r equal to m. Okay, we say that this is the so-called h plus horizon, so the future horizon, and this is the so-called h minus horizon. Then we have that for r const we find hyperbole. Okay, for r greater than 2m, the hyperbole they are given in this way, in these parts of the plane, while for r minor than 2m we find hyperbole in this part, in these two parts of the plane, and as r is equal to 0 we find the hyperbole like this. Okay, and what else should I show? Okay, that as the time is equal to v plus u over 2, okay, we have that minus v over u, it will be equal to minus v over u would be equal to e to the v plus u over 4n. Okay, then we have that v over u, it would correspond to t plus x over t minus x. We have that the minus flips the sign, so x minus t. Okay, and so from here we get that the logarithm of t plus x over x minus t is equal to v plus u over 4m, and so t over 2m. This means that the time in the graph it is represented by straight lines going through the origin with t minus infinity that would correspond to the v line, okay, and so to the past horizon, and t plus infinity that would correspond to the future horizon. So this means that we finally have a complete description of the space-time with two parallel universes that are given by the region 1 and the region 3, in which if we take some point in the space, the light cones are represented by this by the Minkowski light cones, and so one can move and stay at r const, or either move in increasing and decreasing values of r while going forward in time, because in here time goes from minus infinity to plus infinity in this way as the future light cones points up. Okay, this would be minus infinity as we said. In here we would have that the discussion, it is the same, but this time the Schwarzschild time does not go in the same direction of the Kruskal-Seger time, okay, because in here the time goes from minus infinity in here to plus infinity in here. Okay, and then we found also these two regions. With this there is the region 2, and this there is the region 4. Okay, where we can see that it is not possible to stay at r equal const, because the future light const they point towards increasing values of r, as r const is given by this hyperbole. Okay, and so this is a black hole, because the radius has to decrease from r equal to 2m to r equal to 0, so eventually all the physical trajectories they will fall into the singularity, and this would be the opposite. It would be a white hole, because in this case we would have that all the physical trajectories they have to leave this region, because the light cone points upwards, and so to increasing values of r. Okay, and so this was the Kruskal-Seger's diagram. Okay, so at this point we're able to understand and discuss what would be the physical solution to the Schwarzschild metric, because this is a complete description of the space-time, the Schwarzschild space-time, that in principle would show two parallel universes, a black hole and a white hole, but we have that as a star collapses, the trajectory it will be something like this, going to the singularity, to the r equal to 0 singularity, and we have that the Schwarzschild metric, it is found as a solution outside of the star. Inside of the star, the metric solution, it is different because there is some matter content. So we have that everything there is inside of this region, it is not physical because the solution holds for r bigger than the radius of the star as the star collapses. So the physical solution to Schwarzschild, it looks like the black hole, and we are perfectly fine with this because the white hole would show some problems. It would be unstable, there would be blue shift, we already saw that. Okay, so now we want to explicitly build the local inertial reference frame on the H plus horizon and on the H minus horizon, to see what kind of coordinates describe the local inertial observer on the two horizons, and to discuss the results. Okay, so first of all we have to understand, to see what would be the relation between the local inertial reference frame and the most general reference frame, and so how to move from one to the other. So let's say that first of all, due to the principle of equivalence, it is always possible to find a local inertial reference frame in some point of the space-time, and we have that in that reference frame the second derivative of xi alpha with respect to s, it has to be equal to 0. This means that the derivative with respect to s of the derivative of xi alpha with respect to s has to be equal to 0. Now we change the coordinates. Okay, we have that the derivative with respect to s of this can be expressed as the derivative of xi alpha with respect to x mu times the derivative of x mu with respect to s equal to 0, and then we can use the Leibniz rule to find that it would be the derivative of a product. Okay, so we find that this would be the second derivative of xi alpha with respect to x mu times the derivative with respect to x mu and x nu. Sorry. So let me. Okay. Times the x mu in the s, the x nu in the s. Okay, plus the derivative of xi alpha with respect to x mu times the second derivative of x mu with respect to s equal to 0. Now we multiply for the inverse of this, and we find that the derivative of x of lambda with respect to xi alpha times the second derivative of xi alpha with respect to x mu and x nu times the x mu in the s times the x nu in the s plus the second derivative of x lambda with respect to s, it has to be equal to 0. And of course this is just the geodesic equation where this is gamma lambda mu nu. So we have that we find this kind of equation, derivative of xi beta with respect to x lambda times gamma lambda mu nu equals the second derivative of xi beta with respect to x mu x nu. Okay, and we can solve the second order differential equation, then expand in Taylor to find that xi of beta, with beta there is in the brackets because it is a Lorentz index, equal to a of beta plus b beta expanding in Taylor mu x minus capital X mu plus 1 over 2 1 over 2 beta 1 over 2 b beta lambda gamma lambda mu nu x mu minus capital X mu x nu minus capital X nu plus other infinite terms, of course, because this is a Taylor expansion. And so we have that in here a beta, it would be equal to c beta in x, okay, while b beta, it would be equal to b beta mu, it would be equal to the derivative of xi beta with respect to x mu in x. Okay, and so we have that this object in principle would have 16 independent components, because we have 4 values for beta and 4 values for mu, but there is a relation between the matrix that would read g mu nu equals to the derivative of xi alpha with respect to x mu times the derivative of xi beta with respect to x nu times eta alpha beta, that of course holds in x as well, okay, such that from this condition we find that the independent components in here are just 6, and so this transforms well under the Lorentz transformations, because we have that the Lorentz group is described by just 6 parameters. Okay, and so this equation and this equation, these are the two equations that we need to keep in mind to go and solve and find the relation between the most general reference frame and the local inertial one. So now we consider the advanced metric. Okay, we have that in the advanced metric ds squared is equal to 1 minus 2m over r times dv squared minus 2 dv dr minus r squared d omega squared. And we also have shown that the graph in the Eddington-Finkelstein time, it would look like this. So this is 2m, these are the outgoing geodesics that here are just ingoing, and then we have the v const that looks like this. Okay, so we place our we want to build our local inertial coordinate frame in here on the horizon, where x mu is equal to v0, 2m, theta 0 and phi 0. Okay, the local inertial reference frame would look something like this squared inertial equal to the xi0 squared minus the xi1 squared, and going to null coordinates with xi plus 3 is equal to xi0 plus xi1 and xi minus equal to xi0 minus xi1, we would find that the squared inertial would be equal to the xi plus times the xi minus. Of course, again, this that is very easy to find, to prove. And so we have that we would have that eta plus plus is equal to 0, eta minus minus is equal to 0, and eta plus minus it is equal to 1 over 2. Then when it comes to the G monometric, we have that G okay, we will study just the 2D metric. We are not interested in the angular part, and that's why we were writing the local inertial reference frame in just 2 coordinates. Okay, and so we have that GVV would be equal to 1 minus 2m over r, GRR is equal to 0, and GVR it is equal to minus 1. We can see it from here. So now we have that we've seen that G mu nu has to be equal to B alpha mu B beta nu eta alpha beta, but we have that the only non-vanishing component for eta alpha beta would be that one in alpha equal to plus and beta equal to minus, or vice versa, so that one finds that this is equal to 1 over 2 beta mu plus beta nu minus plus beta mu minus beta nu plus. Okay, then we have that G VV in x it is equal to 0, because r is equal to 2m, so 1 minus 1 is equal to 0, of course, and this would be equal to b v plus bv minus. Okay, and from here we get that bv minus is equal to 0, we choose that bv minus is equal to 0. Then we have that grr is equal to 0, So from here we get that br plus br minus is equal to 0. That means that br plus is equal to 0. And finally we have that 1 over 2. No, I'm sorry. We have that minus 1 is equal to GVR in x. Okay. And this would be equal to 1 over 2 b v plus br minus plus bv minus br plus. Okay, so this is 0 because bv minus and br plus, they are equal to 0, and so we are left with this one. Okay, so in principle we could choose bv plus to be equal to 0 and br minus to be equal to 0. The important thing is that in order to recover that this is equal to minus 1, we can't have both br plus and bv plus equal to 0 at the same time, or br minus and bv minus equal to 0 at the same time. So we have this. Okay, and we find that, let me write it here, bv plus br minus, it is equal to minus 2. Okay, so this is a result that we want to keep in mind. Then we go on. Okay, and we have that xi beta, it is equal to a beta, that we can set equal to 0 because it is a constant. So a beta, but we send it, we impose it equal to 0, plus b, okay, plus b beta mu times x mu minus capital X mu plus 1 over 2 b beta lambda gamma lambda mu nu x mu minus capital X mu times x nu minus capital X nu plus a little of 3. Okay, so terms of the third order. Okay, so what can we see in here? We have that okay, we want to have a look at the Christoffel symbols. Okay, so we have that gamma, we start for example from gamma VB. Okay, it would be equal to 1 over 2 g v alpha, g v alpha derived with respect to v, plus g v alpha derived with respect to v, minus g v v derived with respect to alpha. Okay, let's see. We have that this is always 0. None of the matrix elements depend on v, and so they would be equal to 0, while this would be different from 0 if alpha is equal to r. This derivative would not be equal to 0, as well as this one GVR, it is not equal to 0. So we have that this is equal to 1 over 2. We have the minus from here that cancels off with this minus, and so we are left with the derivative of GVV with respect to r. There is 2m over r squared, so we are left with m over r squared, and we have that in x this would be equal to m over 4m squared, and so 1 over 4m. Fun fact, this is the surface gravity in Schwarzschild. Okay, then we have that gamma v r is equal to gamma v rv, and it is equal to 0. It is quite easy to show that, because we would find in the case in the r case, we would find that this that would be the only non-vanishing term, because these terms of course they are 0, because none of the matrix element, as I said, depends on v. This term of course would be 0 since grr is equal to 0, and in the same way we find that gvr when derived with respect to v or with respect to r, it is equal to 0 as well. So this is what we find, and we can plug this result in here. Gamma VV is equal to 1 over 4m, while in the R case we have that gamma RR is equal to 1 over 2 G R alpha, G R alpha derived with respect to R plus G R alpha derived with respect to R minus G R R derived with respect to alpha. Okay, and so of course this is 0, and the same holds for gamma R VB, while the gamma R VB VR, it is not equal to 0, it is 1 over 2 G R alpha, G V alpha derived with respect to R plus G R alpha derived with respect to V minus G VR derived with respect to alpha. So this would be equal to 0 in both cases, alpha equal to V or alpha equal to R. This would be equal to 0 in both cases as well, and this can be different from 0 when alpha is equal to V. So we're left with 1 over 2 G R V G V V derived with respect to R. That means that we get the opposite result, so minus 1 over 4m. So these are the Christoffel symbols that do not vanish. Okay, and now we can plug them inside of these and find that. Let me see. Okay, we are here, perfect. And so we find that in the C plus it is equal to B plus, we have that the only non-vanishing mu when beta is equal to plus, it is R, okay, times x mu, there is R minus m, okay. Am I right? We have that C plus it is equal to B plus R, okay, R minus m, minus 2m, okay, plus 1 over 2 B, again, R plus gamma R VR plus gamma R RV, so we can remove this 1 over 2, and then we have R minus 2m times V minus V0 plus a little O of 3, okay, and this is the C plus, while no, there is something that is not working. Okay, yeah, of course. We have, okay, sorry, I was mistaken. BR plus is equal to 0, so we have that this has to be BB plus. Okay, so now we go and plug, okay, now we can plug these things inside of the exhibit equations, and in particular we find that C plus it is equal to B plus, and then we have to put V minus V0 plus 1 over 2 B V plus, so here we have to put a V, and so we have that the only non-vanishing gamma would be gamma VVV, so here we would have V minus V0 squared, okay, plus a little O of 3, so terms of the third order, while C minus it would be equal to B R minus 2m plus 1 over 2 B R minus gamma R VR plus gamma r rv, but we know that the Christoffel symbols, in the absence of torsion, there is one of the hypotheses of general relativity, is symmetric, so they are symmetric, so we have that we can just remove this 1 over 2. Okay, and then we would find v minus v0 times r minus 2m plus terms of the third order. Okay, so we are not interested in this. We continue our discussion on this, and we find that we can bring okay, gamma vvv, it was equal to 1 over 4m, so this means that in here we would have 1 over 8m bv plus okay. If I get a form m bv plus outside of everything, I find v minus v0 over, I don't know why I wrote it like this. Okay, so I would have v minus v0 over 4m plus 1 over 32m squared v minus v0 squared plus terms of the third order. Okay, but we see that this is just e to the v minus v0 over 4m minus 1, because we can expand e to the v minus v0 over 4m and find that this would be the expansion. And so we have that this is 4m bv plus e to the v minus v0 over 4m minus 1, okay, that is equal to 4m bv plus e to the minus v0 over 4m e to the v over 4m minus e to the v0 over 4m. Okay, and so what did we find? We have that since bv plus it is arbitrary, it has just to respect this equation. So of course, if we choose bv plus in a certain way, br plus has to as a constraint. Okay, so we have that we can choose bv plus to be equal to e to the v0 over 4m and find that this would be 4m times e to the v over 4m minus e to the v0 over 4m. Okay, and we have that they would be the Kruskal coordinates v minus v0. Okay, so we found that on the h plus horizon, one of the two local inertial coordinates, it is the Kruskal coordinate b. And we could find, doing the same calcula, that in the h minus horizon, one of the two local inertial coordinates, it is the Kruskal coordinate u. So we have that the two Kruskal coordinates u and v, they are both local inertial coordinates at the same time, just when the horizons cross in the Kruskal-Szekeres diagram. Now I want to go back to what I said earlier about the fact that it is possible to try two different ways to remove the coordinate singularity r equal to 2m from the Schwarzschild metric, proceeding with the null geodesics or with the time-like geodesics. So we already discussed about the first method that brings null coordinates into the metric, and now I want to show how to derive the pan-level metric starting from time-like geodesics. So we have that in this case we have some Killing energy is signed equal to u0 and Killing energy is signed that is equal to minus u3. We consider radial infalling time-like geodesics such that L signed is equal to 0, and we have that umu has to be equal to 1, and this is the normalization condition such that we find that E signed of squared over f minus r dot squared over f is equal to 1. Okay, so from here we get that r dot it is equal to minus the square root of e squared minus f, if I'm not wrong. Okay, and so we have that umu, it would look like e sine over f and minus the square root of e sine squared minus f, and then 0 and 0. Okay, so we want to impose some constraint on e side. We have that okay, we have that u0 is equal to e sine over f. Okay, and we have that f it is 1 minus 2m over r, such that as r tends to infinity f is equal to 1. So as r tends to infinity u0 is equal to e sine. But we also have that as r tends to infinity the metric is Minkowski, and so as r tends to infinity umu is described as gamma times 1 v as in special relativity. So this means that u0 as r tends to infinity is equal to gamma, but gamma is equal to 1 over the square root of 1 minus v, okay, squared. And so if we impose the initial velocity of the particle that is following this time-like geodesic to be equal to 0, we have that as r is equal to infinity, gamma is equal to 1, and so e sine is equal to 1. Then of course e sine it is conserved along the geodesic because it is a killing energy. We will better see later why. And so we finally find that umu is equal to 1 over f minus the square root of 1 minus f, 0 and 0. Okay, so we can lower the index and find that umu it is equal to g mu mu umu, so it is equal to f times 1 over f, 1. Okay, then this times minus 1 over f, and so square root of 1 minus f over f, then 0 and 0. Okay, now we want to define this umu as the fourth gradient of some function capital T. Okay, and this means that capital T has to be equal to little t plus the integral of the square root of 1 minus f over f dr in order to recover this. Okay, and so from this we find that the t is equal to the little t plus the square root of 1 minus f over f dr. Okay, and so we have that this can become our new time parameter. We can plug this inside of the Schwarzschild metric and find that ds squared is equal to 1 minus 2m over r dt squared. Let me write 1 minus 2m over r as f because our calcula will be easier. Okay, so f dt squared minus 1 minus f times 1 minus f over f squared dr squared, okay, minus double product, so 2f 1 square root of 1 minus f over f dt dr, and then we would have minus f to the minus 1 dr squared minus r squared d omega squared. Okay, and so we have that this f to the minus 1 dr squared, it goes away with this was a plus, so with this one. Okay, then we are left with f dt squared minus dr squared, because it would be f squared over f squared, okay, minus 2 square root of 1 minus f, where f is equal to 1 minus 2mr, so this is 2mr, okay, dt in dr, okay, minus r squared d omega squared. Okay, so this is the metric. We can write it in a simpler way as ds squared equal to dt squared minus dr plus the square root of 2m over r dt squared minus r squared d omega squared. This is the so-called pan-Levé metric. Okay, this is perfectly regular in r equal to 2m. Moreover, we have that the signature as okay, we have that as dt is equal to 0, ds squared is negative. Am I right? Okay, yes. So it is not possible to stay at t const. Okay, so this behaves well as a time. Okay, now we want to understand what could be the physical meaning of this thing, and that's quite easy to show. We take this, and we have that dt is equal to dt in ds times ds plus the square root of 1 minus f over f dr in ds times ds. Okay, we take dt in ds and dr in ds from here. We have that this would be 1 over f in ds, then minus 1 minus f over f in ds, and so this they would go away. We have minus minus plus, and so in the end we would get that dt is equal to ds. So we have that this capital T is just the proper time of the infalling particle. Okay, then we can define the square root of 2m over r as v. Okay. And we have that in that case ds squared is equal to dt squared minus dr plus v dt squared minus r squared d omega squared, and then looking at the radial analgeodesics we find s squared equal to 0, theta and phi constant. Okay, so dt squared equal to dr plus v dt squared. That means that plus minus dt is equal to dr plus v dt. Okay, and so dr in dt equal to plus minus 1 minus v. That has some classical interpretation, we would say. Looking at the Schwarzschild metric, we have that the time symmetry is manifest in the fact that none of the matrix elements of the metric depend on the Schwarzschild time t. But when we go to Kruskal, this symmetry is not so manifest anymore because we changed coordinates. So in principle, the dependence on t could be hidden in this kind of metric. And so we want to understand if there is, but of course this has to still have the same time symmetry because this is just an extension of this metric. So we want to understand if there is some covariant way to talk about symmetries, and actually there is, and it is that one to use the Killing vectors. So let me define the form variation. I have that given some function psi of x that transforms as psi prime of x that transforms as psi prime of x prime. Okay, the form variation, it will be delta 0 psi equal to psi prime of x prime minus psi of x. So we have that, for example, given some metric g mu nu of x, it transforms as g prime mu nu of x prime. We say that the metric it is form invariant if delta 0 g mu nu that is equal to g mu nu prime x prime minus g mu nu of x is equal to 0. So in this case we have an isometry. Now let's take into account infinitesimal transformations. Now before that let me show that g mu nu prime of x prime is given by the derivative of x alpha with respect to x prime of mu times the derivative of x beta with respect to x prime of nu times g alpha beta of x. Okay, we can invert the relation and find that g mu nu of x is equal to the derivative of xi prime of alpha with respect to x mu times the derivative of xi prime beta with respect to x nu times g prime alpha beta of x prime. Okay, so in the hypothesis of the forming invariance of the metric, this g prime alpha beta, it is equal to g, here there was a prime, okay, to g alpha beta of x prime, and so this can be rewritten as g alpha beta of x prime. Okay, so now we consider an infinitesimal transformation. So this is our starting point. We already hypothesized that we already asked our metric to be form invariant to have this relation. Okay, so now we take into account an infinitesimal transformation such that x goes to x prime that is equal to x prime of alpha that is equal to x alpha plus epsilon xi alpha. Okay, and we have that if we plug this inside of this, we find that g mu nu is equal to delta alpha mu plus epsilon times the derivative of xi alpha with respect to mu, okay, times the Kronecker delta of beta nu plus epsilon times the partial derivative of xi beta with respect to x nu, okay, times g alpha beta of x prime that can be expressed as g alpha beta of x plus epsilon times the derivative of g alpha beta with respect to x lambda times xi lambda. Okay, we just expanded considering this. Okay, and so now we can do some calcula and find that g mu nu is equal to, we just up to the terms in the third order of epsilon, so we would have g mu nu, okay, plus epsilon delta xi beta xi nu g mu beta plus epsilon delta xi alpha with respect to x mu g alpha nu, okay, plus epsilon derivative of g mu nu with respect to x lambda times xi lambda. Okay, so these they do cancel off, and so we find that this has to be equal to 0. Then we can of course just drop the epsilon, and we find that the derivative of xi beta with respect to x nu times g mu beta plus the derivative of xi alpha with respect to x mu times g alpha nu plus the derivative of g mu nu with respect to x lambda times xi lambda has to be equal to 0. Now we write this as xi beta g mu beta derived with respect to nu, okay, minus, okay, minus sì, yes, ok, minus xi beta times the derivative of g mu beta with respect to nu plus xi alpha times g alpha nu derived with respect to nu to mu minus xi alpha times g alpha nu derived with respect to nu, okay, plus xi lambda g mu nu derived with respect to lambda equal to 0. And so in here we have that this would be xi mu derived with respect to nu plus xi nu derived with respect to mu, okay, then we put we can change the indices beta and alpha because they are dummy indices to be lambda, and so we can write this as xi lambda, okay, and we can multiply and divide by 2 yes, by 2, and so we find minus 2 times 1 over 2 xi lambda, but xi lambda can be rewritten as xi rho times g rho lambda, okay, and then I have g mu lambda derived with respect to nu, okay, with the minus sign in front, okay, plus g lambda nu, so g nu lambda derived with respect to mu minus g mu nu derived with respect to lambda equal to 0. Okay, and so this would be equal to 2 times xi rho times the Christoffel symbol of rho mu nu, okay, and so in the end everything, all this equation can be rewritten as the covariant derivative of xi mu with respect to nu plus the covariant derivative of xi nu with respect to mu equal to 0, okay, because the covariant derivative of xi mu with respect to nu would be equal to xi mu derived with respect to nu minus the Christoffel symbol multiplying xi rho. Rho is a dummy index, so in principle it could be every index we like, and the same things would occur for this term. So in the end, this is what we find, and this is the so-called Killing equation. So we have that in the hypothesis of the form invariance of the metric, we have that the infinitesimal transformation is realized by a so-called Killing vector that satisfies this equation. So we have that given a Killing vector, there is a symmetry. Moreover, we have that given a Killing vector, the condition xi alpha equal to 0 defines the so-called Killing horizon. Okay, of course we don't always have a Killing horizon, but for example in Schwarzschild we do have a Killing horizon, because we would have that xi alpha would be equal to 1 minus 2m over r, and we have that the Killing horizon actually it coincides with the event horizon, with the Schwarzschild horizon, because in r equal to m this is equal to 0. We have that this is greater than 0 as r is greater than 2m, this is equal to 0 as r is equal to 2m, and this is minor than 0 as r is minor than 2m. So we have that the Killing vector becomes space-time, in this case inside of the Killing horizon, and of course this has some consequences that we want to study. In particular, we want to see what the sign of the Killing energy that is associated to the Killing time vector in Schwarzschild is like outside and inside of the horizon. So first of all, let me just discuss in the most general way what would be the sign of the scalar product between a time-like and a space-like vector, a time-like and a time-like vector, and time like a null, space like a null in Schwarzschild, because the property of being time like null or space like it is conserved between different coordinate frames, and the scalar product it is conserved as well. So we can put ourselves in a convenient reference frame, and it is that one of Minkowski, and we have that if our light cone looks like this, given some future pointing time like vector a mu and another future pointing time like vector b mu, okay, the scalar product between, so the fact that they are future pointing means that a0 and b0 they are greater than 0 and greater, since they are time like, than the modulus of the space part. Okay, so we will find something like this, and this means that a mu b mu it is equal in Minkowski to a0 b0 minus the modulus of a times the modulus of b times the cos of the angle, and of course this is always greater than 0 in this case. Then we consider the scalar product between a time like and future pointing vector and a space like and future pointing vector. So in this case we would have a0 greater than the modulus of a, but b0 minor than the modulus of b, and still greater than 0, of course. And so we have that in this case a mu b mu, looking at this, it can be greater than 0 when the cos of theta is minor than 0, and when the cos of theta is positive, the sign of the scalar product just depends on the features of the vectors. It can be either greater or minor than 0. So we say that we have both the possibilities. Then we consider a time like and future pointing vector and a null vector. In this case we have that a0 is greater than the modulus of a, as u0 is equal to the modulus of u. Okay, and so a mu u mu it is equal to u0 times a0 minus the modulus of a times cos of theta. And again, this is always positive. Okay, doesn't matter if this is negative or positive, this a0 will always be greater than this object. Okay, and finally we will look at the last case. That is when we have a future pointing and space like vector a mu, and then a null vector that can be parallel, such as u mu in this case, for example, or anti-parallel, such as b mu. So we have that we would have a0 minor than the modulus of a, u0 equal to the modulus of u, such as v0 equal to the modulus of v. And so we would find that a mu u mu is equal to u0 a0 minus modulus of a times cos of theta. We project, because we remember that this is the time and this is the space r. Okay, so we project on the space and we find that the cos of theta in this case it would be equal to 1, because u mu and a mu they are parallel. Okay, and so we would find that this would be negative in this case when a mu points to the right as u mu points to the right. And in the other case, as a mu points to the right and it is anti-parallel to v mu, we would find that the cos of theta would be minor than 0, so the minus and the minus they would cancel off, and we would find that the scalar product would be greater than 0. Okay, so now we have all the elements that we need to go and discuss about the sign of E outside and inside of the Schwarzschild horizon in the case of a black hole. So this is our horizon, this is the singularity, okay? We have that outside of the horizon, C alpha, it is time-like, U and V, they are time-like. Okay, this is our light cone. And so this means that the killing energy associated to the V or to the U photon, with the U photon there is the outgoing one and the V photon there is the ingoing one, it is positive in both cases, because it would be equal to the product between a time-like and sorry, this was not U vector, but of course U alpha and V alpha. Okay, so it would be the product between a time-like vector and a null vector. So this is greater than 0, and again C alpha, V alpha is greater than 0 as well. In the other case, inside of the horizon, we would have that C alpha is time-like and it is pointing towards the right, because we have that C alpha is still defined as 1, 0, 0, 0, and inside of the horizon the time goes from r minus infinity, there is here, from t minus infinity, there is here, to t plus infinity. So the time goes like this, and so this would be the direction, but it would be space-like, while U and V, they would be null. Okay, so we have that in this case C alpha, there is the time killing vector, it would be parallel to alpha and anti-parallel to V alpha. So the energy of the U photon would be minor than 0, and the energy of the V photon would be greater than 0. Okay, these results can be verified also looking at the fact that U0 is equal to E over F, okay, because E is equal to U0 with the low index, so we can raise the index and we get this 1 over F, and so this means that E is equal to U0 times F, that is 1 minus 2m over R. Okay, but inside, but outside of the horizon, this is always greater than 0, and U0 is always greater than 0. This U0 would parameterize this could be either U0 or V0. We're considering both the U case and the V case. Okay, so we would have that this is always greater than 0 because U and V, they point in the same direction of the time. The time goes up in this region of the plane, while inside of the horizon we would have that in the UK 1 minus 2m over r is always negative. In the UK is U0 would be pointing in the same direction of the time. You can see it in this way, so it would be greater than 0, and so we have that the energy has to be negative because it is the product of a positive quantity times a negative quantity. In the other case, in the case of V, we would find that V points in the opposite direction to the time, so V0 is negative, and this means that this quantity is negative, this quantity is negative, and so the killing energy is positive. So we found that the killing energy is always positive outside of the event horizon, but it can be either positive or negative inside of the horizon based on which photon we are looking at, if it is the U photon or the V photon. And we want to better understand what the physical meaning of this would be, because we have that asymptotically the killing energy, we can see it from here, would describe the local energy, the energy that one would measure in a laboratory. Okay, but we have that the local energy always has to be greater than 0, of course. So let me let me just do some calcula and show that the local energy inside and outside of the horizon is always positive, and then let's try to understand what would be the meaning of the killing energy and the fact that it can have both positive and negative sign. So we have that outside of the horizon we can consider a free falling observer with some for velocity mu of s. Okay, and then we have that this observer measures a photon that can be either u or v. We will have a look at both the cases. So we have that as the observer is free falling, mu and it is radially free falling, mu is given by u0 ff and ur ff, while the other components they would be equal to 0, with u0 ff that is equal to e over f, because u0 with the low index it would be equal to e, and then we would have that due to the normalization condition we would find that ur ff it is equal to minus the square root of e sine squared of e sine squared minus f. Okay, yes, then we have that for the photon p0 is greater to e, and due to the normalization condition we have that p r it is equal to plus or minus e, plus when the photon is outgoing and minus when the photon is ingoing, such that PR with low index it is equal to minus plus it would be GR so E over F. Okay, and so we have that the local energy outside of the horizon it would be given by P00, so E over F E signed, and then we have minus plus with this minus, so plus minus the square root of E sine squared minus 1 minus 2m over r. Okay, so we have that this is always positive because f is always greater than 0 outside of the horizon. This is always greater than 0 outside of the horizon, as I said, so this is always less than the square root of this object is always less than E signed, and so both in the plus or minus case we have that the argument of the bracket it is positive. Okay, and so in the end we have that this is greater than 0 both in the u case and in the v case. Now we have a look at what would happen inside of the horizon. Actually, all the discussion is quite identical, but we have to pay attention to one thing. We have that when we consider the plus E solution, actually, E, in the case of the U photon that takes the plus, is negative. So we can write this as minus the modulus of E, since then we have that in the other case the killing energy would be positive and it would take the minus sign. So we can write it in this way, and so we have that PR is equal to plus the modulus of E over F. So in the end we have that this is the local energy is E over F times E sine plus minus the modulus of E over E times this. Okay, and so let's have a look at the two different cases. We have that in the U case, of course, F is always minor than 0. So we already have that this is negative. We have that this is negative. Wait. This plus minus in here, it is wrong. We just have the minus. Okay. So this is negative, so this is always greater than e signed. The argument under the, yes, the square root will always be greater than e signed. Okay, and so we have that in the u case e is minor than 0, f is minor than 0, and so this is positive. Then we have that e signed is greater than 0 as the observed fold inside of the horizon. Okay, then we have that this in the u case it would be equal to -1, so this would be plus, this of course is positive, and so we find that the local energy it is greater than 0 in this case, in the u case, while in the v case we have that the local energy would be positive again because f is minor than 0 and e is positive. Then we have that this would be negative, this would be positive, so we would keep the minus sign. This is greater than e sign, and so all the argument in the brackets it is negative, and so we have negative, negative, positive. We get that this is greater than 0. Okay, so we found that the local energy is always positive, as we would have expected, but the killing energy can be either positive or negative inside of the horizon. What does this mean? Actually, we have that since the killing energy has to be conserved along the geodesics, it is impossible for a U particle that has positive killing energy outside of the horizon to go inside of a black hole, because it would have negative killing energy inside of the horizon, and so all the U photons inside of the black hole they are generated inside of the black hole, and this kind of law would hold for a black hole. T squared, that is the rate of transmission, times r squared, which is the rate of reflection, okay, equals to 1. Given a killing vector xi alpha with killing horizon that is determined by the xi alpha equal to 0, we have that the surface gravity is defined as the square root of L mu on H, that is the killing horizon, with L mu that is defined as the gradient of L, where L is the square root of xi alpha. Okay, so we have that in the Schwarzschild case we can take the killing time vector, and we can compute the surface gravity that is associated to the killing time. So we have that L would be equal to the, as T alpha is equal to 1, 0 vector in Schwarzschild, we have that L would be equal to the square root of 1 minus 2m over r. L mu would be equal to 0, 1 over 2, 1 minus 2m over r to the minus 1 over 2 times m over r squared, okay, 0, 0, and then I have that L mu will be equal to GRR LR, that is equal to 1 minus 2m over r times 1 minus 2m over r to the minus 1 times m squared over r to the fourth, and so it is minus m squared over r to the fourth, such that the surface gravity it is equal to m over r squared in h. We have that the killing horizon and the event horizon they coincide in the case of Schwarzschild, and so this is equal to 1 over 4m. And we have that this enters the coordinate in such a way that u is equal to 1 over k minus 1 over k e to the minus ku, and v is equal to 1 over k e to the kp. Okay, So now let me talk about the near horizon approximation, where the surface gravity is already set enters. Okay, let me consider that close to the horizon I can express r as 2m plus x squared over 8m, where x is much less than 2n. Okay, so I have that from here I get that dr is equal to 2x dx over 8m, that is equal to kx dx, and I have that 1 minus 2m over r is equal to r minus 2m over r, that is equal to x squared over 8m over, it would be 2m plus x squared over 8m, so 16m squared plus x squared over 8m, that is approximately equal to x squared over 16m squared. Okay, so we plug everything inside of the Schwarzschild metric and we find that ds squared is equal to kx squared dt squared minus dx squared minus 2m squared d omega squared. So in here we have a 2 sphere and this is a 2D metric. So now let me show what this 2D metric would represent. Let me go to Minkowski, where I have that ds squared is equal to dt squared minus dx squared, and let me choose a parametrization such that t is equal to x sin h of kt and x is equal to little x cosine h of kt. In this way one finds that dt is equal to dx sin h of kt plus kx cosine h of kt times dt, and dx it is equal to dx cos h of kt plus kx sin h of kt in dt. So dt squared minus dx squared, it will be equal to kx squared dt squared minus dx squared. So we found that this and this, they are equal, but this describes Minkowski. So we found that near close to the horizon the 2D metric will be some Minkowski space, and so now we want to understand what's the physical interpretation of this. In fact, let me show that if we are at r const, x of course has to be constant as well. So we consider a static observer and it has some for velocity that is equal to u0 0 as always, with u0 squared that will be equal to the normalization condition to 1 over g00, and so u0 is equal to 1 over the square root of g00. Okay, then I have that the mu in the s, that will be the acceleration, it will be d mu in ds plus gamma mu alpha beta u alpha u beta. Okay, but this of course is equal to 0 because u0 does not depend on s, and the other terms they are equal to 0, the other velocities, the other components of the velocity, they are equal to 0. And here we have that the only non-vanishing gamma, it is gamma mu 0 0. Okay, and in particular we have that gamma mu 0 0 is equal to 1 over 2 g mu nu g0 nu 0 plus g0 nu 0 minus g00 nu. Okay, the derivatives with respect to 0, they are equal to 0 because the metric is static, and so the derivative nu has to be equal to x because that's the only non-vanishing derivative, for G00, and so mu has to be equal to x as well. This means that lambda 1 0 0 is solely non-vanishing gamma symbol, and it is equal to minus, so plus, the minus comes from here, it would be the G11, 1 over 2 G00 derivative with respect to x, so it would be k squared to x, and so this would be k squared x. So I plug this in here and I find that the u1 in ds, that would be equal to a1, is equal to k squared x times u0 squared, which is 1 over the square root of, which is 1 over g00, but we just saw that g00 is equal to kx squared. Okay, so we would have that this is equal to k squared x over 1 times 1 over kx squared. Okay, and so we will get that it is equal to minus 1 over x. There has to be some minus that I forgot. Where is it? No, okay, no. There is no minus in here. Okay, so we found that a1 is equal to 1 over x. Then we have that a mu is equal to g 1 1 a1 and so it is equal to minus, okay, and here it comes the minus 1 over x squared. So it means that as r tends to 2m, x tends to 0, an infinite amount of acceleration is needed to be static close to the horizon. Okay, and so it looks like x would be in some way related to the acceleration. Let me show that it's actually like that. Let me show that a Minkowski spacetime appears in here because in this kind of reference frame x would describe accelerated observers, and so of course to the principle of equivalence we would have that an accelerated observer in a flat spacetime is equivalent to a static observer in a gravitational field. Okay, to do so, first of all, from this relation we shall see that in Minkowski that x squared minus t squared is equal to little x squared. That means that that x const is equivalent to hyperbole in Minkowski, and as x tends to 0 and as x is equal to 0, x squared minus t squared would describe two 45-degree lines. Okay, and so in Minkowski we have that an observer with x greater than 0 would feel such, okay, would eventually experiment kind of an horizon. There is this one, this is the H plus, while this would be the H minus, and so every light signal coming from this region could never receive the observer at x const. Okay, then for x greater than 0. Okay, then we have that given some physical trajectory in Minkowski, with for velocity, so given a particle that moves with for velocity u, we have that mu is equal to 1. This is the normalization condition, as always. It is easy to prove that the derivative of this object equal to 0 means that the product between the acceleration and the for velocity has to be equal to 0, and so that the for velocity is orthogonal to the acceleration. And actually maybe I will show that is that the derivative with respect to s of mu is equal to 0, because the derivative of 1 of course it has to be equal to 0. And so we have that using the Leibniz rule, the derivative with respect to s of mu low index times mu plus mu low index times the derivative of mu with respect to s has to be equal to 0, and this can be shown just by writing this as g mu nu okay, like this, g mu nu the unu in the s mu, g mu nu times mu, it is equal to unu with the low index, and so we found that 2 times d unu in the s times unu has to be equal to 0. So this is the acceleration, and we found what we just said in special relativity, of course. Okay, where the acceleration is defined as the derivative with respect to s of mu. Okay, and so we have that as the acceleration is orthogonal to the for velocity, we expect the acceleration to be space-like, because the for velocity is time-like, being of course that being the trajectory of the particle, a physical trajectory. And so we have that a0 squared minus a1 squared, because we are in Minkowski, has to be equal to minus g squared. It is negative because this has to be space-like. a0 u0 minus a1 u1 has to be equal to 0, because a and u, they are orthogonal. And finally u0 squared minus u1 squared has to be equal to 1. Okay, so from here we get that u0 squared is equal to 1 plus u1 squared. Okay, then we could say maybe it is better to work like this: u1 squared equal to u0 squared minus 1. Okay, then from here we have that a0 is equal to a1 u1 over u0. Okay, we plug this inside of this and we find that a1 squared u1 squared over u0 squared minus 1 is equal to minus g squared. But we have that u1 squared is equal to u0 squared minus 1, so this is 1 minus 1 u0 squared, and so in the end we have a1 squared okay, so we said u0 squared with the 1, it goes away, so 1 over u0 squared equal to g squared, because the two minus signs they cancel off, and so we get that a1 squared, it is equal to u0 squared times g squared. Okay, from this relation we find that a0 and so this means that a1 is equal to u0j, and from the first equation we find that in this way a0 is equal to u1g. Okay, then we derive with respect to s. Now we have that the second derivative of u1 with respect to s is equal to g times the derivative of u0 with respect to s, there is a0, and so it is equal to g squared u1, while the second derivative of u0 with respect to s is equal to g squared u0. Okay. So this means that u1 is equal to a to the e gs plus b to the e plus b times e to the minus gs, while u0, oh no, I'm sorry, let me, of course it is the same, but to be clear, let me just use u0 equal to this, and u1 equal to c times e to the gs plus d times e to the minus gs. Okay, we plug u0 and u1 in here. Okay, and we find that a has to be equal to c and b has to be equal to minus d. Okay, then we impose some initial conditions. In particular, we say that mu, since we are in Minkowski and so in special relativity, it is given by gamma 1b. Okay, so if if at s equal to 0, so at the beginning, the velocity v of the particle that we are considering for this trajectory is equal to 0, is imposed equal to 0, we find that u0 initial, it is equal to gamma equal to 1 over the square root of 1 minus v squared, and so it will be equal to 1, while u1 initial, of course, it will be equal to 0. Okay, and so we find that we plug this inside of this, given s equal to 0, so 1 is equal to a plus b, and 0 is equal to a minus b. This means that a is equal to b is equal to 1/2. Okay, and so finally we found that u0 is equal to 1 over 2 e to the gs plus 1 over 2 e to the minus gs, that is equal to the hyperbolic cosine of gs. Okay, while u1 would be equal to 1 over 2 e to the gs minus 1 over 2 e to the minus gs, which would be equal to the hyperbolic sine of gs. But we have that u0 is equal to dt in the s, and u1 it would be equal to the x in the s. So we have that from here we find that t is equal to g times the sin h of gs, and x is equal to g times the cos h, 1 over g, of course, cos h of gs. So what we find is x squared minus t squared equal to 1 over g squared. Okay, but we saw that x squared minus t squared is also equals to x squared. So what does this mean? That the hyperbole given by x const, they describe the trajectories of accelerated observers. Okay, and this is quite interesting because at this point we have that, if you consider Minkowski, we have that the accelerated observers are described by this hyperbole. Okay, like this. We have that as x is greater than 0 in this region, there is some sort of horizon. The observer in this region cannot be reached by every signal coming from this region, so he will feel an event horizon, and it is not due to the gravitational field, but it is just a consequence of the fact that it is accelerated, the observer is accelerated. Now I introduce a new coordinate sigma such that x is equal to 1 over k e to the k sigma. Okay, and at this point I have that my Rindler metric would become kx squared would be e to the 2k sigma dt squared, okay, minus the x it would be equal to e to the 2k sigma d sigma, so e to the 2k sigma d sigma squared. Okay, and then we would have the angular part, but we're not interested in that, so we would find e to the 2k sigma times dt squared minus d sigma squared. We can define the null coordinates u and v as, with u that is defined as t minus sigma, and v that is defined as t plus sigma, in such a way that dt squared minus d sigma squared, it is just equal to du times dv. Okay, and the sigma in here can be written as v minus u over 2. Okay, so let me see. Okay, of course sigma is a function of u and v, as I just said. Now in Minkowski the null coordinates, they are given by u equals to t minus x and v equal to t plus x. We plug this new parameterization inside of the t and x that are defined, we remember, as x sin h and x cosine h, so we get 1 over k e to the k sigma sin h of kt minus 1 over k e to the k sigma cosine h of kt. Okay, it is equal to 1 over k, and then we have e to the k sigma sin h of kt, it is equal to e to the kt minus e to the minus kt over 2, okay, minus cosine h, it is e to the kt plus e to the minus kt over 2. So this and this, they go away, and we're left with 1 over k e to the k sigma. Okay, we get a minus, then we have that the 2, it goes away with the fact that these are equal, and so e to the minus kt, that would be minus 1 over k e to the k t minus sigma, there is no minus t plus sigma, that is equal to minus u, Okay, and so we found that this look like this, while v it will look like 1 over k e to the kp. This is exactly the same kind of relation that holds between the Kruskal coordinates and the Schwarzschild, the Kruskal coordinates and the um, the advanced and retarded null coordinates in Schwarzschild. Yes, we can do an analogy, and we can say that as Schwarzschild doesn't cover the entire manifold and describes the static observer in a gravitational field, while Kruskal covers the entire Schwarzschild manifold, we have that Minkowski covers the entire flat space-time, and Rindler cannot cover the whole flat space-time and describes an accelerated observer. So what we did, we just found the equivalence principle. Okay, so we said that the near horizon metric is described by some metric that looks like this, with this being the Rindler metric that is associated to the flat space-time, but for accelerated observers, and this would be a two-sphere. So that's our starting point. We have that in the Rindler metric we have a manifest time symmetry. So time symmetry is manifest in the fact that no matrix elements of the metric depend on the time, but when we go to Minkowski, that time symmetry is not so manifest anymore. Of course, the time symmetry with respect to the Rindler time, and so but we know that it has to be coded in here, because of course they do describe the same metric. So we want to understand in what way would the Rindler time symmetry be coded into the Minkowski metric. So we have that the Killing vector that is associated to the time symmetry in Rindler, it is given by xi alpha Rindler equals to 1, 0, 0, 0. And of course we have that xi mu Minkowski, okay, it is equal to okay, it is given by the derivative of x mu Minkowski with respect to x nu Rindler times xi nu Rindler. Okay, so we have that the only non-vanishing component in the case of the Rindler killing time vector, it is the first one, and so we have that this has to be written as the derivative of x mu Minkowski with respect to the Rindler time, okay. Yes, times, yes, so this has to be written in this way as the derivative of x mu Minkowski with respect to the Rindler time. That means that the t coordinate is equal to, no, that means that c 0 Minkowski is equal to the derivative of capital T with respect to little t, that is equal to kx cosine h of kt, that is equal to k capital X, and c1 Minkowski, it is equal to the derivative of capital X with respect to t, that is equal to kx sin h of kt, that is equal to k capital T. So that the Killing vector in Minkowski, it would look like k x t 0 0 Okay, so we want to understand what kind of killing vector we found. Okay, to do so, let me have a look at the Lorentz transformations in the Minkowski case, okay, in the Minkowski spacetime, because we will see that this killing vector it is associated to the Lorentz transformations, in particular to the boosts along x. So and so we have that the time symmetry in Rindler it is coded into Minkowski into the invariance under the boosts. And so yeah, we have that given some yes, we have that a Lorentz transformation on x brings x to x prime equals to let's say that this is x prime of mu equal to delta mu nu plus epsilon mu nu x nu. We know that the Lorentz transformation leaves the Lorentz transformations they leave the metric invariants, and so they are performed by the transformation is performed by some killing vector, and so this can be expressed as x mu plus xi mu, where xi mu is equal to epsilon mu nu times x nu. Okay, so we have that eta mu nu lambda mu alpha lambda nu beta is equal to eta alpha beta, and so eta mu nu times delta mu alpha plus epsilon mu alpha times delta nu beta plus epsilon nu beta equals to eta alpha beta. So we stop at the first order of epsilon as always, and we find that eta alpha beta plus epsilon mu alpha eta mu beta plus epsilon nu beta eta alpha nu, okay, is equal to eta alpha beta. So these they go away, and we find that from here we get that epsilon beta alpha plus epsilon alpha beta has to be equal to 0. That means that okay, that means that epsilon beta alpha is equal to minus epsilon alpha beta, and so this means that epsilon 0 1 is equal to minus epsilon 1 0, while epsilon 0 0 has to be equal to 0 and epsilon 1 1 has to be equal to 0. Okay, and so what we got is that xi mu is equal to epsilon mu nu x nu as we said earlier, and so xi 0 is equal to epsilon 0 1 x1, that is capital X. We can lower the index without changing the sign because the index is 0. Okay, and so we say that this is epsilon x, while xi1 it will be equal to epsilon 1 0 times x0, which is capital T. This time we lower the index and we get the minus. Okay, but minus epsilon 1 0 is equal to epsilon 0 1 that we called epsilon, and so we found epsilon T. And finally we had that xi mu is equal to epsilon xt. That is exactly what we found in here. In here we had just two components. As in here we had just two components. Here in the left 2D. Okay. And so we have that the scaling vector in the Minkowski spacetime, okay, that is associated to the invariance with respect to the boost is translated to the time symmetry in Rindler. Okay, we finished our discussion on the Rindler metric. That is probably the one of the I would say not boring, maybe a little bit difficult things of this whole discussion. And now we talk about the Penrose diagrams. So we talk about the Penrose diagrams. There are these really useful diagrams used to study the causal structures of the different spacetimes. The idea is that to send infinities in physical spacetime, in the physical spacetime, to finite quantities in an unphysical spacetime by some kind of transformation that we call conformal transformation. It is not a transformation of the coordinates, but it is just a transformation of the metric such that G mu nu bar, G mu nu is sent to G mu nu bar of x that is equal to omega squared of x G mu nu. So what we find is that after the conformal transformation, the s squared is equal to omega squared the s squared, and so if the s squared is greater than 0, the s bar squared is greater than 0. If the s squared is equal to 0, the s bar squared is equal to 0. Okay, and if the s squared is minor than 0, we have that the s bar squared is minor than 0. So we have that the causal structure it is preserved because if some vectors are time-like, null, or space-like, when performing a conformal transformation, this property won't be changed. Actually, what does change is that the geodesics, in principle, they won't go to geodesics in the new conformal spacetime. The only geodesics that will be preserved will be the null ones, since we have that as the s squared is equal to 0, the s bar squared is equal to 0, and this is what defines the null geodesics. Okay, so Einstein's theory is not invariant under conformal transformation. That's because the components of R mu nu, they do change after a conformal transformation, because they have the components of the Riemann tensor, they have the metric inside, and so we would have that the components would change and the vector and differential basis, they would not change under the conformal transformation, such that in the end the Riemann tensor would not be a good tensor quantity. But we can define the Weil tensor that is given by C mu nu alpha beta equal to R mu nu alpha beta plus some function of R mu nu and R, so the Ricci tensor and the Ricci scalar, that actually transforms well under the conformal transformations. So we have that R mu nu alpha beta, the Riemann tensor, it is defined in terms of the Weil tensor and in terms of Ricci tensor and Ricci scalar, and this makes sense because we have that R mu nu in four dimensions has 10 independent components, so the other 10 independent components, they come from the Weil tensor. Okay, so let's have a look at the different properties of the Weil tensor. First of all, we have that C mu nu alpha beta is equal to minus C nu mu alpha beta, that is equal to C nu mu beta alpha, that is equal to minus C mu nu beta alpha. Then we have that C mu nu alpha beta is equal to C alpha beta mu nu, okay, C mu alpha mu beta is equal to 0, and C mu nu alfa beta plus c mu alfa beta nu plus c mu beta nu alpha, it is equal to 0. These are the properties of the Weyl tensor. The Weyl tensor has 1 over 12 d squared times d plus 1, no, times d squared minus 1, okay, minus 1 over 2 d times d plus 1 independent components, where d is the dimension of the space, such that in 4 dimensions the Weyl tensor has 10 independent components. In 3 dimensions the Weyl tensor has 0 independent components, and so the Riemann tensor is all defined in terms of the Ricci tensor and Ricci scalar, and in 2 dimensions it has 0 components as well. In particular, we have that we say that a space is conformally flat if G mu nu bar, so G mu nu conformal, is equal to omega squared eta mu nu, because in this case we would have that before the conformal transformation r mu nu would be equal to 0, because the spacetime is flat, and so the Ricci scalar and the Ricci tensor, they would be equal to 0 as well, and so the Weyl tensor would be equal to 0. Then going to conformal, the Weyl tensor would be equal to 0, and this would mean that the Ricci tensor and all its contraptions have to be again equal to 0. And so we have that there is a theorem that states that in 2 dimensions in 2 dimensions the metric is always conformally flat, and so the Weyl tensor is always 0. Okay, so now we want to see how the Christoffel symbol would transform under conformal transformation in order to be able to study the null geodesics in the conformal space-time. Okay, and so we have that gamma alpha mu nu, it is defined as, or maybe even better, we have that gamma mu alpha beta, it is defined as 1 over 2 g mu nu derivative times g alpha nu derivative with respect to beta plus g beta nu derivative with respect to alpha minus g alpha beta derivative with respect to nu. Okay, we have that g mu nu bar it is equal to omega squared g mu nu, such that g mu nu with I indices bar is equal to omega to the minus 2 g mu nu with I indices. And what else? We have that g mu nu, of course, is equal to omega to the minus 2 g mu nu bar, such that g mu nu with I indices, it is equal to omega squared g mu nu bar. Okay, and so this translates into 1 over 2 omega squared g mu nu bar. Okay, and then the derivative of g alpha nu with respect to beta, we have that g alpha nu, we can see it from here, it is the product of omega to the minus 2, where omega is a function of x, and g bar, there is a function of x as well, and so we use the Leibniz rule, and we find that this would be omega to the minus 2 g bar alpha nu derived with respect to beta plus g bar beta nu derived with respect to alpha minus g bar alpha beta derived with respect to nu. Okay, plus, okay, and we have the derivative of omega to the minus 2, okay, that is minus 2 omega to the minus 3, then the derivative of omega with respect to b, the derivative of omega with respect to beta times g alpha nu, plus the derivative of omega with respect to alpha times g beta nu, minus the derivative of omega with respect to nu times g alpha beta. Okay, so we plug this inside of the geodesic equation in the conformal metric. So we have something like this. It is equal to the second derivative of x mu with respect to s squared plus gamma mu alpha beta dx alpha in ds times dx beta in ds, okay, plus that goes okay here, omega to the minus 1, and then we have the derivative of omega with respect to beta times dx beta in ds dx mu in ds plus the derivative of omega with respect to alpha times dx alpha in ds times dx mu in ds, okay, minus the derivative of omega with respect to nu times g bar mu nu g bar alpha beta dx alpha in ds times dx beta in ds, and so we have that this is 0 by hypothesis, because we want to consider we start and consider a geodesic in the physical space-time, so before the conformal transformation, but in general this term is non-vanishing, so we do not recover the geodesic equation, and in the conformal space-time we do not have find a geodesic. In the case of an algeodesic, we have that this is equal to 0, okay, because it would be u mu mu, u alpha, you can call it as you want, okay, and we would find that the second derivative of x mu with respect to s plus gamma mu bar alpha beta dx alpha in ds times dx beta in ds is equal to omega to the minus 1 omega to 2 omega derived with respect to beta dx beta in ds times dx mu in ds. So this is an interesting result, because we have that this is not the usual geodesic equation that we know, but it still is a geodesic equation, because we have that these two that beta is contracted, so this is a scalar, and so this means that the vector is still being transported parallelly to itself along the geodesic, because we have that the x mu in ds, it would correspond to the tangent vector to the geodesic, so it is still being transported parallelly, okay, but s is no more defined parameter because we don't get 0 in here. So this still describes a geodesic, but S is no more the affine parameter, and we want to be able to recover S as the affine parameter, or let me say it again. Actually, we want to find the new affine parameter. Of course, we don't want this S to be the affine parameter, but we have that there has to be some relation between this parameter and the affine parameter, such that in the end this geodesic equation will look as the regular one. Okay, and so we have that U alpha can be written, that is equal to dx alpha in d lambda, can be written as dx alpha in d lambda bar d lambda, and we say that d lambda bar in d lambda is equal to some constant c times some function omega of x. Okay, and now we go and plug everything inside of here. So we have that this would be the covariant derivative in the conformal metric of U mu with respect to U alpha equals to okay, we say that this would be 2 times the derivative with respect to beta of the logarithm of omega, okay, times U beta U mu. Okay, so this can be written as U alpha times the covariant derivative of U mu, that can be expressed as the derivative of x mu with respect to lambda bar times the derivative of lambda bar or lambda prime? Lambda bar. The derivative of lambda bar with respect to lambda, okay, times 2 times the derivative with respect to beta of the logarithm of omega times the derivative of x mu with respect to lambda bar times the derivative of lambda bar with respect to lambda. Okay, this is the derivative of x beta, but then we do the same for x mu, and we find this. Okay, U alpha can be written as the derivative of x alpha with respect to lambda bar times the lambda bar in the lambda. Okay, so this the lambda bar in the lambda goes away with this one. Okay, and so we use the Leibniz rule, and we find that the derivative of x alpha with respect to lambda bar times the covariant derivative of the x mu in the lambda bar times the lambda bar in the lambda plus the derivative of x alpha with respect to lambda bar times the derivative of x mu with respect to lambda bar, okay, times the covariant derivative of CW, okay, has to be equal to 2 times the derivative with respect to alpha of the logarithm of omega times the derivative of x alpha with respect to lambda bar times the derivative of x mu with respect to lambda bar times the lambda bar in the lambda. Okay, and so we have that this is 0 because we want lambda bar to be the affine parameter of this null geodesic, and so this is the geodesic equation, and this has to be equal to 0. and we find that, let me write it again, do I need something else from here? No, I don't think so. I think I can erase everything here. Okay. So I would find that the derivative, the x alpha in the lambda bar and the x mu in the lambda bar, they just go away. Okay. And so we have that this was the covariant derivative with respect to alpha of c omega. So the covariant derivative of a function, it is just a partial derivative. So we have c, there is a constant, it is not derived, times the derivative with respect to alpha of omega, little omega, it is equal to 2 times the derivative with respect to alpha of the logarithm of omega times c w. But now c, it goes away, so we find 1 over over omega times the derivative with respect to alpha of omega equal to this stuff, but this means that the partial derivative with respect to alpha of the logarithm of little omega is equal to 2 times the logarithm, the derivative with respect to alpha of the logarithm of omega, which is the derivative with respect to alpha of the logarithm of omega squared, such that in the end we find that little omega is equal to omega squared. And so as d lambda bar in d lambda is equal to c omega squared, we find that null geodesics are conserved by conformal transformations, and their new affine parameter lambda has this kind of relation with the old affine parameter. Okay, so Penrose's idea was to send points at infinite distance in physical spacetime to finite distance in unphysical spacetime by sending omega to 0 as lambda diverges. Okay, so here we are. I forgot to to switch on the microphone. Okay, I talked about the 5 different infinities in Minkowski. Then I said that from the double null metric we could define this u and v as the tangent of u bar and the tangent of v bar. Then doing some algebra, I'm able to find ds squared in this way, and so we go to conformal, multiplying by 4 cos squared of u bar cos squared of v bar, and find this for du bar dv bar minus the sin squared of v bar minus u bar d omega squared. Okay, and so at this point we can define t prime as v plus u and v bar plus u bar, and r prime as v bar minus u bar, to get ds squared equal to dt prime squared minus dr prime squared minus the sin squared of v bar minus u bar, that is r prime d omega squared. So what we just found, it is the static Einstein solution. That was the solution Einstein found for a static universe, adding the cosmological constant to its equations. And actually we will talk better about the cosmological constant later, but I can already say that Einstein then regretted the add-on of the cosmological constant and actually removed it from its equations. But we will see that we will need that to describe an expanding universe, and a universe that actually has an accelerated expansion. That's the point. Okay, and so now we're finally able to draw the Penrose diagram, because we have that as v and u they go to minus infinity, v bar and u bar they are equal to minus pi over 2. Here we have that v bar and u bar they equal to pi over 2. Here we have that v bar is equal to pi over 2 and u bar is equal to minus pi over 2. Here we have that v bar would be different from plus or minus pi over 2, while u bar would be equal to minus pi over 2, and here we would have v bar equal to pi over 2 and u bar different from plus or minus pi over 2, such that in here we will find t prime equals to minus pi and r prime equals to 0. In here t prime equals to pi and r prime equals to 0. Then in here we would find t prime equals to 0 and r prime equals to pi. Then we will find t prime okay, so t prime plus r prime equal to because we would have the t prime plus r prime, we can see it from here, it is equal to no, okay, I'm sorry, this is t prime minus r prime. Okay, this is equal to pi, and in here we have t prime plus r prime equal to pi. Okay, so here we have t prime minus r prime equal to minus pi, and here t prime plus r prime equal to pi. Okay, and so we have that the Penrose diagram. It will be given by, let's say that this is our r prime, this is our t prime. Okay, is minus pi, this is pi, this is pi, and so we will get something like this. 1 and 2, this is E0, this is E plus, this is E minus, this is I minus, and this is I plus. Okay, and so this is what we find for the Penrose diagram. And of course, for example, our const trajectories, they're given by some curves like this. Okay, because we have that now the infinities, they are bounded into this triangle in Minkowski. Okay, now we go to Schwarzschild and we do the same stuff. We want to find the conformal metric in the Kruskal case, and then we want to be able to find the Penrose diagram in the case of Schwarzschild. So the procedure is the same. Maybe we have just some more complicated calcul, I would say. So we start from d squared equal to 2m over r e to the minus r over 2m du dv minus r squared d omega squared. So this is the Kruskal metric. This is our starting point over r. Okay, so nothing is missing. Now I define v as 4m times the tangent of v bar and u as 4m times the tangent of u bar. So from here I get that dv is equal to 4m times 1 over the cos squared of v bar times dv bar, and from here I get that du is equal to 4m times 1 over the cos squared of u bar times du bar. Okay, so I plug this in here and I find ds squared equal to 2m over r times e to the minus r over 2m times 16m squared. So this would become 32m to the third. Okay, 1 over the cos squared of v bar times the cos squared of u bar times dv bar du bar. Okay, minus r squared d omega squared. Then we go conformal. Okay, with omega squared that is equal to the inverse of this stuff, but we keep a 4 in front of dv du. So we have that this squared is equal to conformal, it is equal to 4 dv bar du bar minus r times e to the r over 2m over 8m, okay, times cos squared of v times cos squared of u bar times r squared d omega squared. So here we would have r to the third. Okay, this is the conformal metric that we found in the u bar and v bar coordinates, that can be expressed as if we define t prime equal to v bar plus u bar and x prime as v bar minus u bar, as ds squared bar equal to dt prime squared minus dx prime squared minus r to the third times e to the r over 2m over 8m to the third times the cos, this had to be squared, so the cos of u, it is equal to t minus x over 2, t prime minus x prime over 2, times the cos of t prime plus x prime over 2 squared d omega squared. Okay, so finally we found that this is the form that we want to use as the for the conformal metric. Okay, so since we have since the transformation is conformal, of course the light cons they are preserved, and so we have that as in Kruskal-Zekers, the light cons they are 45 degrees they are 45 degrees inclined lines. Okay, so we find that they still look like this, and then we have that we know that r over 2m minus 1 times e to the minus r over 2m, if I'm not wrong, okay, is equal to e to the v minus u over 4m. Okay, that is equal to minus uv over 16m squared. That is just equal to minus the tangent of u bar times the tangent of v bar. Okay, so we have that when r is equal to 2m, the tangent of u bar times the tangent of v bar has to be equal to 0, and so we get that u bar is equal to 0, v bar takes all the values between minus pi over 2 and pi over 2, and vice versa. When r is equal to 0, we have that the tangent of u bar is equal to 1 over the tangent of v bar. Okay, that is equal to the tangent of pi of plus minus pi over 2 minus v bar, such that in the end we would find that u bar is equal to plus minus pi over 2 minus v bar. Okay, and so now I'm able to draw the Kruskal-Zekers diagram in its Penrose representation. So as this is t prime and this is x prime. Okay, we have that these are u prime and v prime. Okay, so this is pi over 2, this is pi over 2, this is minus pi over 2, and this is minus pi over 2 in here. Okay, we have that as r is equal to 0, as I have just shown, we find this kind of lines. Okay, well, these diagonals between these values, they define the r equal to 2m condition, so they would be the two horizons, h plus and h minus, and asymptotically the metric would recover the Schwarzschild metric, so asymptotically we find the Penrose structure, the Minkowski-Penrose structure. So we have E0, E plus, E minus, I minus, I plus, and same stuff in here, I plus, I minus, E0, E minus, and E plus. This describes very well in a very compact form the causal structure of the Schwarzschild black hole. We have that this is of the Schwarzschild solution, sorry. We have that this is the black hole, this is the white hole, this is our universe, this is a parallel universe, and so once inside of the black hole everything has to go towards the r equals 0, the singularity, and once inside and from the white hole everything just has to leave, because the light cons they do, the future light cons they do they do allow just to leave this region. Okay, and in here we have that one can move to increasing, decreasing values of r, or can stay at r const, so it doesn't matter, and in here as well. So now we are able to go and look at another kind of black hole. There is the black hole that has a mass and an electric charge. The starting point is the same as Schwarzschild. We want to solve the metric outside of a spherical symmetrical source, but this time we have that outside of the source T mu nu is not equal to 0, but actually it is non-vanishing because there is some electric field. So we have that we need to solve the Einstein equation R mu nu minus 1 over 2 R G mu nu equal to 8 pi G T mu nu when T mu nu is not vanishing. Okay. Moreover, since we are dealing with an electric charge, of course, we have to use Maxwell equations, because at this point we are dealing with some electromagnetic field, and so we want to impose the so-called Einstein-Maxwell system that is given by the Einstein equation and the Maxwell equations in covariant form. So the Maxwell equation in curved spacetime. Okay, so this is the system that we need to solve in order to find the solution for the metric outside of a charged object. So let's look for the Maxwell equations in the curved spacetime. We have that in special relativity Maxwell equations would be derivative with respect to mu of f mu nu equal to 4 pi j nu, where this is the these are the inhomogeneous equations, where f mu nu is equal to the derivative with respect to mu of a nu minus the derivative with respect to nu of a mu, where this a nu or a mu, it is for potential that that has a gauge symmetry such that a mu can be sent to a mu prime equals to a mu plus the for gradient of some function alpha, and still f mu nu would be left invariant. Okay, and so these are the inhomogeneous equations, and then we have the homogeneous equations that are f mu nu derived with respect to lambda plus f nu lambda derived with respect to mu plus f lambda mu derived with respect to nu equals to 0. Okay, then we have that the Maxwell tensor that appears in here. It would be empty mu nu equals to minus f mu alpha f nu alpha plus 1 over 4 eta mu nu f alpha beta f alpha beta. Okay, so this is what we have in special relativity. We want to go covariant. We need these equations in their covariant form. To do so, we apply the principle of general covariance, and we have that in order to find these equations in curved space, then we just need to send the partial derivative to the covariant derivative, and of course in here as well we need to send all the Lorentz indices to the indices of the spacetime manifold, and the Minkowski metric to the general metric G mu nu. Okay, and so we have that going covariant. We find f mu nu covariant derivative with respect to mu equal to 4 pi j nu. Here we have that these are all covariant derivatives, and in here we have G mu nu. Very easy. Okay, so now let's go and develop all of these different terms. So we start from we start from this. Yeah, I think we could start from the homogeneous equations. We have that f mu nu covariant derivative with respect to lambda, it is equal to f mu nu derived with respect to lambda minus gamma f alpha nu, and so we have that in here we would have alpha, then mu lambda, okay, minus gamma f mu alpha nu lambda. Okay, of course in here I have my method to be fast. So f nu lambda derived with respect to mu, it is equal to f nu lambda derived with respect partial derivative with respect to mu minus gamma f alpha lambda nu mu alpha minus gamma f nu alpha lambda mu, okay, and finally f lambda mu derived with respect to nu, covariant derivative with respect to nu, it is equal to f lambda mu partial derivative with respect to nu minus gamma alpha f alpha mu lambda nu minus gamma alpha f lambda alpha 1. Okay, so what do we see from here? We have that then we have to add these three terms and set them equal to 0 to find the homogeneous Maxwell equations. And so we have that the f tensor, there is the strength tensor, it is antisymmetric, we can see it from here. And so we have that as the Christoffel symbols, they are symmetric, and the strength tensor f is antisymmetric, terms like this and this, they would cancel off, okay, because this would switch sign. So in the end we would be left with just the partial derivative. So this when imposed equal to 0 is equal to the same equation but without the covariant derivative. So this is the first thing that we found. So we go on with the discussion, and we have that f mu nu covariant derivative with respect to mu, it is equal to f mu nu covariant derivative partial derivative with respect to mu plus gamma f, then gamma f alpha nu alpha mu plus gamma nu alpha mu f mu alpha. Okay, so we have that this is antisymmetric, this is symmetric under the exchange of alpha and mu, and so this goes to 0. Okay, and then we look at this, and we have that this is equal to 1 over 2 g mu nu, g alpha nu derived with respect to mu plus g mu nu derived with respect to alpha minus g alpha mu derived with respect to nu. Then we have that mu and nu can be switched in here and in here, of course. This is symmetric under the exchange of the two indices. So this would be equal to this one, okay. They cancel, and we get that this is just equal to 1 over 2 g mu nu times g mu nu derived with respect to alpha, but this is equal to 1 over 2 the derivative with respect to alpha of the logarithm of g, where g is the determinant of the metric, and this is found as g mu nu would be the inverse of this metric, of this matrix, and so it is possible to show that this is true. It's quite intuitive, because this is as I said, this is the inverse of this, so we have that as we have the inverse of a function times the derived function, we get the logarithm of the function, but in this case with the matrix, so we have that we get the logarithm of the determinant of the matrix. Okay, and so this can be written as the derivative with respect to alpha of the logarithm of the square root of j, that can be expressed as 1 over the square root of j times the derivative with respect to alpha of the square root of j. And so in the end this is just, and I will write it here, or maybe here. Okay, anyways, it will be equal to 1 over the square root of g times the partial derivative with respect to mu of f mu nu times the square root of g. Okay, so let me write my Einstein-Maxwell system here. We have that 1 over the square root of g times the derivative with respect to mu of f mu nu times the square root of g is equal to 4 pi j nu. Then we have that f mu nu derived with respect to lambda plus f nu lambda derived with respect to mu plus f lambda mu derived with respect to nu is equal to 0. And finally we have that we have that the tensor, the energy momentum tensor, the Maxwell energy momentum tensor, it would be mt mu nu equal to minus f mu alpha f nu alpha plus 1 over 4 g mu nu f alpha beta f alpha beta. And we have that these are vanishing trace, and I will show that. Since if I consider m t mu mu, okay, I get that this is equal to minus f, mi sono spaventato, minus f mu alpha times f mu alpha, okay, minus, no, plus 1 over 4 the delta mu mu, that is equal to 4, times f alpha beta, so of course this is equal to 0, and this means that the if I take the trace of the Einstein equation, I will get that the Ricci scalar has to be equal to 0, because the trace of the t tensor, it is equal to 0. So in the end I have that these are the Maxwell equations in curved spacetime, while the Einstein equation that I need to solve it is r mu nu equal to 8 pi g mt mu nu. Okay, and so now I can proceed. I have that I have a lot of pages to go. I will stop here. Okay, so still 4 pages. Okay, so I have that I start considering an electric radial field such that the only non-vanishing term in f mu nu, it would be the 0, 1 term that would correspond to ER, while f 1, 0 of course is equal to minus ER. So this is my starting point. I have only a radial electrical field. Okay, and I have that f01, it is defined as the derivative with respect to 0 of a1 minus the derivative with respect to 1 of a0. Okay, and of course I can impose some gauge condition to have that the derivative with respect to 0 of a1 is equal to 0, such that in the end we have that ER is just equal to minus the gradient of phi, where phi is some scalar function that is equal to a0. Okay, so this is our starting point, f01 equal to ER. To ER, okay. Then, the most general solution, the most general ansatz, the ansatz that we have for the spherical for a spherical symmetrical source, it is ds squared equal e to the nu of r and t dt squared minus e to the mu of r and t dr squared minus r squared d omega squared. Okay, so how do I proceed? First of all, I go and look for F01. Okay, F01 is given by G00, G11, F01. Okay, and it is equal to E to the minus nu plus mu ER with the minus in front. Okay, minus E to the minus nu plus mu ER. Okay, then I have that from the metric I find that that G, or the square root of G, because I will need that, yes, the square root of G is equal to nu times mu times r squared sin theta squared. So it is e to the nu plus mu over 2 times r squared sin of theta. Without any loss of generality, I can impose theta equal to pi over 2, as always, because we have spherical symmetry, and find that the square root of G is equal to this. Okay, then I go and work on this equation, I would say, yes, and I have that the derivative with respect to mu of f mu nu times the square root of G has to be equal to 4 pi j nu. We have that outside of the source j nu is equal to 0. There are no charge. There is no current. Okay, because we are in the void. Of course, we have an electromagnetic field, but there are no sources, no currents. Okay, and so we have that this equation, the non-trivial equations that we can get from here, they are that one in mu equal 0 and mu equal 1. So the derivative with respect to 0 of f01 times the square root of G has to be equal to 0, and the derivative with respect to 1 of f10 times the square root of G has to be equal to 0. Okay, so from here we get the derivative with respect to 0 of e to the minus nu plus mu ER has to be equal to 0, and from here I get that the derivative with respect to 1 of e to the ER times e to the nu plus mu over 2 times r squared. Okay, and again in here I find the same stuff. Okay, so what does this mean? That this argument, it does not depend either on the time or it does not depend on time and on the space, and so we find that e to the minus nu plus mu over 2 ER r squared has to be equal to some constant that I call E, such that I find ER equal to E over r squared times e to the nu plus mu over 2. Okay, I chose E because in the limit for r that goes to infinity we want e nu and e mu to go to 1, because we want to find Minkowski, and so in that case we would have that ER is equal to E over r squared. That is exactly the Coulombian electrical field. Okay, so we have we found ER, and it looks like this. I could write it here maybe. With the minus? No. Okay, it is fine. It should be right. Let me see. Okay. So now we go to the Einstein equations. Okay. And we have that the 0, 1 equation would show that minus mu dot over r is equal to 0. That means that mu is a function of r. The 0, 0 plus 1, 1 equations, they show that mu prime plus nu prime has to be equal to 0, and so mu of r plus nu of r and t, it is equal to some function of the time. And the two equation, it would give that e to the minus mu times r minus r minus r minus 4 pi g e squared over r prime is equal to 0. This means that e to the minus mu is equal to, so this means that this is equal to some constant, because in here we don't have any dependence on the time. So if this, when derived with respect to r, is equal to 0, this means that of course this has to be constant. And so we will get that e to the minus mu has to be equal to, we have that the constant could be minus 2m, then we divide everything by r, and we have that it is equal to 1 minus 2m over r plus 4 pi g e squared over r squared. We can call 4 pi g squared equal to q squared, and finally we have that e to the minus mu is equal to 1 minus 2m over r plus q squared over r squared, while e to the nu, from this relation, we find that it is equal to e to the minus mu times e to the ft, but e to the ft can be reabsorbed inside of the time into the metric, okay. And so we finally found the solution, the Reissner-Nostrom solution for the metric. That is the squared equal to 1 minus 2m over r plus q squared over r squared times dt squared, because as I said I could define t prime as the square root of e to the ft over 2 times dt prime, such that times dt, sorry, such that dt prime is equal to dt prime squared is equal to e to the ft dt squared, and so I could just plug it in here, okay, and still it will be a good time coordinate. So we go on and we have that ds squared, as I said, is equal to this minus 1 minus 2m over r plus, this is impossible, q over r squared times dr squared minus r squared d omega squared. So sorry, of course it's impossible to read, but it is there. Here I have to the minus 1, okay, and so this is the so-called Reissner-Nostrom solution. Okay, so the reason why we chose the 2m in here as the constant is that when q is equal to 0 we want to recover Schwarzschild, and we do. Okay, so now we study the singularities of this metric as we did in Schwarzschild, because again we have some physical singularity, real singularities, and actually one real physical singularity, and some coordinate singularities. So let me write again the metric very fast. Okay. And so let's have a look at the singularity. So of course we have one in r equals 0, and then the other one would occur in 1 minus 2m over r plus q squared over r squared equals 0. And so we have that this singularity appears when r squared minus 2m r plus q squared is equal to 0, and so when r plus and so in r plus minus equal to m plus minus the square root of m squared minus q squared. Okay, so this singularity, the singularity that would make this metric element equal to 0 exists if m squared is greater than q squared, or if m squared is equal to q squared, but when m squared is minor than q squared, it does not exist. Okay, so did I finish with this? I think so. Okay. And so now we have a look at all the different possibilities. So we start from the m squared minus then q squared case. In this case we have that r plus minus they do not exist, and so we have just one singularity that is given by r equal to 0. Okay, we have that 1 minus 2m over r plus q squared over r squared, it is always greater than 0 in this case, and this means that the time is a time everywhere and the space is a space everywhere. Moreover, there is no killing horizon for the time killing vector xi alpha equal to 1 0 0 0, so all looks fine. Actually there is some problem with this kind of solution. In fact, we have that in Schwarzschild the Penrose diagram, it looked like this. This is r equal to 0, this is r equal to 0, this is r equal to 2m. So what do we see in here? We have that we have the r equal to 0 singularity that is physical, it is a real singularity, okay? And the r equal to 0 singularity is a space-like singularity, and it cannot be avoided once inside of the black hole, okay? But it is hidden by the horizon, okay? In the case of the Reissner-Nordström solution, when m squared is minor than q squared, what one finds is that the Penrose diagram would look like this, because asymptotically we have Schwarzschild as always. So this is E0, this is E plus, this is E minus, this is I minus, and this is I plus. Okay, and then we have that the r equal to 0 surface would be a time-like surface, so it can be reached from every point inside of this diagram. And of course this is a problem, because if I take a point and then I draw the light cone, I can see that physical trajectories can end up in the r equal to 0 singularity, but moreover the singularity is included into the past light cone. So it means that we should be able to make some physics in a singularity, but actually, of course, we're not able to do so. So there is some problem with this. Moreover, if I define a Cauchy surface as a surface at constant time that has some conditions on it, such that if I take a point in the future and I consider all the physical trajectories going from that point to the past, all the trajectories they go to the Cauchy surface. If I have some no, I'm sorry, I will repeat it because I know that it was impossible to understand. I say that a Cauchy surface is defined as a surface at constant time, such that if I take a point in the future, all the physical trajectories going backwards in the past from that point to the surface, they do intersect the surface. And so if I give some conditions, some boundary conditions on the Cauchy surface, I'm able to predict the future. In this case, I'm not able to find the Cauchy surfaces because let's say I take Cauchy surface like this in here. Okay. I get that one branch of the light cone intersects the Cauchy surface, sigma, but the other, it doesn't, because it falls into the singularity, so I lose predictability. This is, of course, a problem. And here it comes the cosmic censorship hypothesis by Penrose that states that it is just a conjecture, but it states that in nature all the singularities have to be hidden by an horizon. Okay, so let's have a look at the geodesics in this particular case. So I have that u0 is equal to e signed, u3 is equal to minus L signed, as always. Then I have that u mu has to be equal to 1, so e signed squared over f minus r dot squared over f minus L signed squared over r squared has to be equal to 1, such that r dot squared plus v effective is equal to e signed squared, where v effective is defined as 1 plus L signed squared over r squared times 1 minus 2m over r plus q squared over r squared. And here something very weird happens, because I have that differently from the Schwarzschild case. Okay, when L signed is equal to 0, okay, I get that I have one term in 1 over r squared, and so asymptotically this is equal to 1. I get something like this. So let me show all the weird things that come with this kind of potential. First of all, we have that particles coming from infinity cannot reach the singularity; they bounce back. And so this is already weird, because this looks like a black hole, I would say, okay, but it is not. It comes from the Reissner solution, but the Reissner-Nostrom solution, actually it is not a black hole, because the singularity is naked and it has to be avoided. No particles can fall into the singularity. But moreover, we have that as L is equal to 0, there is some circular orbit that is stable in here. And we also have bounded orbits. This is something that did not occur in Schwarzschild. This kind of behavior is really weird, because the repulsion, it is not given by the electrical charge. It is not a consequence of some repulsion between the electrical charge, because the particle that we are considering, it is neutral. So it is something that comes, of course, from the presence of the electrical charge, because that's the reason why the metric is different from Schwarzschild, but it is related to how the electric charge changes the metric, the shape of the space-time. Okay, so now I want to have a look at the null geodesics. Okay, so now null geodesics, they would be given by okay, no worries. I would have liked to keep that, but I will probably draw it later if I need it. Okay, so this I don't need it anymore. I will keep the singularities on the board. Okay, so in the case of light, we have u0 equal to e, u3 equal to minus L, and u mu equal to 0. Okay, so in this case, I find that e squared over f, I find the same stuff, e squared over f minus r dot squared, minus pr squared over f minus L squared over r squared is equal to 0, and so I find pr squared plus v effective equal to e squared. So in principle I could study this equation given these two constraints and find the form of PR, but there is another way to proceed, of course, and it is that to consider, as always, ds squared equal to 0 and theta and phi const. It is quicker. Okay, and I get that dt in dr is equal to plus minus 1 minus 2m over r plus q squared over r squared to the minus 1, but we have that this is always positive, and so if we have to picture the geodesics, in geodesics we will find that they go like this. And so, as I already said, we have that the light cones, they do include the r equals 0 singularity in their past and in their future. Okay, and so of course this is weird. Moreover, we can show that weird stuff happens close to the horizon. Some blue shift occurs if light is emitted under a value of radius that is called r Minkowski. R Minkowski, it would correspond to q squared over 2m, okay, because and we call it r Minkowski because in this value of radius we find that gtt and grr, they are equal to 1 and minus 1. So we have that in Schwarzschild, as we get close to the horizon, the static observer, so at r, theta and phi const for the static observer, ds squared is equal to 1 minus 2m over r dt squared, that of course is minor than dt squared. Okay, but in this case, in the Reissner-Nostrum case, when m squared is minor than q squared, one finds that ds squared for the static observer are at r, theta and phi const, okay, it is equal to 1 minus 2m over r plus q squared over r squared dt squared, that is greater than dt squared as r is greater than r, as r is minor than rn, because we could see it from the shape of the potential. We had something like this. Let's say that this is the, okay, so this is the one, this would be the r Minkowski, okay, and so okay, from r Minkowski down to 0 we have that this is greater than 1, and so while we have that time ticks faster near the singularity in the Schwarzschild case, in here time ticks slower. Moreover, we can show that blue shift occurs, as I already said, for values of radius that are minor than rm, since we have that if this is the singularity, if this is rm, I consider a static observer that emits a photon, the static observer that receives it. We have that this has some velocity, there is mu 1, and this has some velocity, there is mu 2. So the two observers, they are both static, so we have that mu I, it is equal to u0 I 0, okay, with u0i that is given by 1 over the square root of g00 in ri, and then we have that the p0 of the photon, it will be equal to E, such that the local energy, it will be equal to p mu I, okay. So we have that E1, maybe I write it here. So E1 local, it will be equal to E over the square root of G00 R1, while E2 local is equal to E over the square root of G00 R2, and so this is equal to H nu 1, this is equal to H nu 2. Okay, I have that nu 1 it is equal to nu 2 times the square root of G00 R2 over G00 R1. Okay, and I have that if I consider the second observer, the one in R2, as the observer that is static at infinity, we get that G00 R2 it is equal to 1, and so we have that nu 2 it is equal to nu 1 times the square root of G00 R1, but we have that G00 R1, as R1 is minor than Rm, it would be greater than 1, and so nu 2 would be greater than nu 1, and so blue shift would occur. And so we expect this object, the naked singularity, to be unphysical, because weird stuff happens as we just showed. So okay, I will stop and have dinner because I eat. Now I discuss the case in which m squared is greater than q squared, and so r plus minus they exist and they are equal to m plus minus the square root of m squared minus q squared. Okay, and we have that f in r plus minus is equal to 0, so we have that if we draw f as a function of r, this is what we find. This is 1. Okay, and so we find one region, that is this one, in which the space is a space, the r coordinate is a space coordinate and the t coordinate is a time coordinate. In here we have that f is minor than 0, so the two switch, and we have that t becomes a space coordinate and r becomes a time coordinate. And in the third region, this one, we find that again everything gets back to normal. Okay, so we have that r plus minus, they are singularities of the metric, and we've seen that we said before that we are coordinate singularities, not physical singularities, since we have that there is no divergence of the invariant scalars such as r mu nu or r alpha beta mu nu r alpha beta mu nu, and so we want to be able to remove them in some appropriate coordinate chose. And so we as we did in Schwarzschild, we look for the radial null geodesics such that ds squared is equal to 0, theta and phi are constant. Okay, and so one finds that tt in dr is equal to plus minus the square root of 1 minus 2n over r plus q squared over r squared to the minus 1. Okay, and if I define the tortoise coordinate r star as r plus 1 over 2k plus times the logarithm of r plus minus r over r plus times plus 1 over 2k minus the logarithm of r minus minus r over r minus, where k plus minus are defined as r plus minus minus r minus plus over 2 r plus minus squared. Okay, so we have that if I define this tortoise coordinate, then I can find dt in dr star equal to plus minus 1, and so t minus r star const and t plus r star const. I call this v, I call this u, and this would be the retarded Eddington-Finkelstein coordinate, and this would be the advanced Eddington-Finkelstein coordinate, such that we're able, of course, to find, as always, the advanced Eddington-Finkelstein metric, the retarded Eddington-Finkelstein metric, and the double null Eddington-Finkelstein metric. So now let me look at the advanced metric. We have that ds squared is equal to 1 minus 2 m over r plus q squared over r squared dv squared minus 2 dp dr minus r squared d omega squared. Okay, then I look for the radial null geodesics in this case, so in this metric, which is the advanced one, so ds squared equal to 0 and theta and phi const, and find that dv times 1 minus 2 m over r plus q squared over r squared times dv minus 2 dr has to be equal to 0. So from here we have that one solution would be dv equal to 0, so v equal const, and the other one it would be dv over dr equal to 2 over 1 minus 2 m over r plus q squared over r squared. So now I can draw the graph in the Eddington-Finkelstein time. Okay, I have that this would be r plus, I don't know if, yes, okay, so this would be at r plus, this would be r minus. Okay, so let me start drawing these geodesics. So we have that in r plus and r minus we have just two straight lines going up, since we have that this is equal to 0 in r plus and r minus, the denominator is equal to 0 in r plus and r minus. Then we have that outside of r plus, the geodesics, they are very similar to the Schwarzschild case outside of the r equal to m. They look like this. Yes, let's say that they shouldn't stick in this way in here, but they would look something like this. Then in the region between r plus and r minus, we have that, find something like this. Okay, and this in this region for r minor than r minus, we find these geodesics, and we go on like this. Then the v const geodesics, they would correspond to something like this. Okay, so what do we see from here? We have that outside of the r plus region, this region r minor than r plus, it is in the future of the light cones. Okay, so the physical trajectories, they can go towards r plus, but it is not in the past. Inside of the r plus region, there is just one possible way to proceed, and it is to go towards r minus. Okay, or either go towards r minus to stay in r minus, or fall into r minor than r minus. We say that we see that the light cones, they all go to the left. Okay, while in the r minor than r minus region, we find that the light cones, they do not fall into the singularity. They of course include the singularity, but it is possible to move avoiding the singularity and going to r minus. So we have that in the region 1 we should have our universe. In the region 2 we already would have a black hole, because this would be causally disconnected from this region, from the region 1, and in the region 3 we wouldn't be able to escape such a region, but it is possible to avoid the singularity. So the main difference with Schwarzschild is that once the r plus horizon, which is the black hole horizon, is crossed, the observer can avoid falling into the singularity. So let me recap the main points about this discussion. We have that in the Eddington Finkelstein time, one finds that as this is R plus and this is R minus, three regions are found. Outside of R plus, the geodesics, the outgoing ones, they look like this, and inside of the R plus R minus region, they look like this, and in here again they look like this. While these are the V const geodesics, okay? And so we find that the one region is our universe, the two region already describes a black hole, because it is not possible to escape this region. And then in the third region, it is not possible to leave such region, but it is possible to avoid crashing into the singularity. So the main difference with Schwarzschild would be this. Then, if we have a look at the effective potential in the case of m squared greater than q squared, what we have is that, as always, E sign is equal to u0, L sign is equal to minus u3, and mu has to be equal to 1, such that E sign squared over f minus r dot squared over f minus L sign squared over r squared is equal to 1, and so r dot squared plus v efficient is equal v effective is equal to E sign squared. So v effective is equal to 1 plus 2m over r plus q squared over r squared. Here I add a minus, of course. Okay, times L sign squared over r squared plus 1. So as I have in the case of a radial time-like geodesic, I have that L sign is equal to 0 and the V effective would just be equal to F. Okay, so now we can compare the things that we found in here with the things that we found in here. We have that a particle coming from infinity with energy greater than 1, it looks like it wouldn't be able to reach the singularity, and it should bounce back. Okay, but in here what we find is that actually the particle that falls can crash into the singularity, can avoid the singularity, but it can also crash. So there is already something that that is off. Before going to Kruskal, let me show the other way to proceed, and it is that to consider Penlevé, as we did in Schwarzschild case. And so we have that we start from E signed, as I am just erased, E signed equal to 0, L signed equal to minus u3, and umu equal to 1, okay, such that in the end one finds that r dot squared plus v effective is equal to E signed squared, okay, where v effective is equal to L signed squared over r squared plus 1 times 1 minus 2m over r plus q squared over r squared, okay. So we have that, from here I get that r plus r dot is equal to minus the square root of E sign squared minus f when L sign is equal to 0, okay, if I consider the infalling time-like trajectory. Then Teresa.
Oggi c'è la luna fragola e una volta ogni 18 anni.
Vieni a dirlo alla telecamera.
Che cos'è quello?
Sto registrando.
Che registri?
Me che faccio la lezione.
Ciao.
Ok, we go and look at the strawberry moon.
Albano qua.
Okay, now we want to find some constraint on E sign. In particular, we have that u0 is equal to E sign over f, and as r tends to infinity, we find that u0 is equal to E sign. But as r tends to infinity, one also finds that umu is equal to gamma 1v. So we have that in this case u0 would be equal to gamma that is equal to 1 if we consider the initial velocity equal to 0, and so E sign would be equal to 1, and so umu is equal to 1 over f minus the square root of 1 minus f, and then 0 and 0, we can lower the index and find that umu is equal to 1 square root of 1 minus f over f 0 and 0, and then umu equal to the foregradient of capital T, where t is equal to little t plus the integral of the square root of 1 minus f over f in the r, okay, such that dt is equal to dt plus the square root of 1 minus f over f in the r, and we can invert the relation to find that dt is equal to d capital T minus the square root of 1 minus f over f times dr, and so plug this inside of the metric and finally find that the line level metric would look like ds squared equal to dtp squared. I'm going by memory because it is the same thing that we found in the case of Schwarzschild, minus dr plus the square root of 1 minus f dtp squared minus r squared d omega squared. But this time we have that this holds just when 1 minus f is greater than 0, so when f is greater than 1, and so for when f is 1 minus f greater than 0, so when f is minor than 1, okay, and so for r greater than rm, because as r is lower than rm, one finds that f is greater than 1. We could see that from the graph of f that we plotted before. Okay, and so this means that of course the level metric is not a complete metric. It is not the right way to proceed. Moreover, we have that if we look at this, okay, considering L sign equal to 0, we get that as E sign squared is equal to 1, r dot squared is equal to 1 minus f. That means that the turning point that would correspond to r dot equal 0 would correspond to rm. Okay, and this means that there is a problem because rm is minor than r minus, and so it would be in the region 3. But from this we found that as the particle gets to rm from infinity with energy with initial velocity equal to 0, and so is E signed equal to 1. Okay, as it comes from infinity, it gets to Rm and then it bounces back. But as Rm is in the third region, the particle should not be able to leave the region. So something is missing. The picture, of course, is incomplete. We need to furthermore on the extension of the metric as we did in Schwarzschild. Okay, to do that, let me go to double null coordinates and then let me find Kruskal, of course, looking for the surface gravity and then for the Kruskal coordinates. So, going to double null, we just have to keep in mind that t is equal to v plus u over 2 and r star is equal to v minus over 2, such that in the end this s squared would be equal to 1 minus 2m over r plus q squared over r squared du dv minus r squared d omega squared. Okay, with r that at this point is just a function of u and v, of course. Then we want to find the surface gravity, so we say that we have a time killing vector c alpha that is equal to 1 0 0 0. Okay, and we know that to be able to find the surface gravity we have to define L as the square root of xi alpha, so it is the square root of f. Okay, then L mu, it is the derivative of it is the gradient of this, and it would be 0 1 over 2 f to the minus 1 over 2 times the derivative of f with respect to r, so f prime, then 0 0, Then L mu, it would be equal to minus f 1 over 4 f to the minus 1 f prime squared. So we get minus 1 over 4 f prime squared, and so in the end k is equal to the square root of L mu modulus in h, and so it would be equal to 1 over 2 f prime in h. F prime is equal to it will be equal to 1 over 2 m over r squared plus, no minus, 2 q squared over r to the third. And so this is m over in h. Okay, so it will be equal to m over r squared minus q squared over r to the third in h, that is equal to 1 over r plus minus squared times okay, so maybe I should stop here and compute the two different k at this point. Yes, okay, so we have that this is our starting point. Okay, we have that k would be found as m over r squared minus q squared over r to the third on the horizon. So we have that k plus, it is given by 1 over r plus squared times m minus q squared over r plus, but r plus it is equal to m plus the square root of m squared minus q squared, so I can multiply and divide by m minus the square root of m squared minus q squared. Okay, and so this will be 1 over r plus squared. Okay, I get q squared from here, that goes away with that. Okay, and so m minus m plus the square root of m squared minus q squared, it is just r plus minus r minus over 2. And so we found that k plus is equal to r plus minus r minus over 2 r plus squared. In the same way we find that k minus is equal to r minus minus r plus over 2 r minus squared. Okay, so at this point, when we want to go to Kruskal for the double null metric, we have two different possibilities, because we can build Kruskal coordinates out of k plus or out of k minus. And so let's try the first approach. We have that u plus is defined as 1 over k plus minus 1 over k plus e to the minus k plus u, and b plus is defined as 1 over k plus e to the k plus v, such that du plus is equal to e to the minus k plus u du, and dv plus it is equal to e to the k plus v times dv, such that dp du that we want to replace in here, it is equal to e to the k plus u minus v times dv plus du plus. But we have that this can be expressed as e to the minus 2k plus r star, that is equal to e to the minus 2k plus r. Then we find that r star is defined as r plus 1 over 2k plus times the logarithm of r minus r plus over r plus, blah blah, the same stuff in k minus. And so in the end we get r minus r plus over r plus to the minus 1 times r minus over r minus to the minus k plus over k minus. Okay, we plug this inside of the metric and find that ds squared is equal to r plus times r minus over r squared, because the metric could be, because this could be expressed as r minus r plus times r minus r minus over r squared, e to the minus 2 k plus r times r minus r minus over r minus times 1 minus k plus over k minus, okay, times du plus dv plus minus r squared d omega squared. Okay, so this is the Kruskal metric in this is the Kruskal metric for the Reisner-Nordstrom solution in the Kruskal coordinates built on the k plus surface gravity. Okay, that it is perfectly regular in r plus, but it is singular in r minus, so it does not cover the entire space-time. And we have that we can see that minus uv times k plus squared, it is equal to e to the 2k plus r times r minus r plus over r plus times r minus over r minus k plus over k minus. This is negative because k minus is negative and k plus is positive. Okay, so we have that as r is equal to r minus, this diverge. Okay, this goes to infinity, so uv is equal to infinity, and we find that this to minus infinity, I would say so. Anyways, we find that from this equation we're able to find all the elements that we need to draw the Kruskal diagram. In fact, we have that as r is equal to 0, no, as r is equal to r plus, we have that uv is equal to 0. And so this means that u is equal to 0 and v takes all values, or v is equal to 0 and u takes all values. And so this would be u, this would be v. And we already start with these two 45 degree lines. Okay, then we have that as r is equal to r minus, we get this kind of hyperbole. Okay, so this is r equal to r minus, this would be r equal to r plus. Okay, and what else? We have that all the hyperbole in here, they would correspond to some r constant for r that is greater than r minus and minor than r plus, while in this region this hyperbole would correspond to r constant but for r greater than r plus. So then by conformal we can go to Kruskal, and we have that r plus would be r plus and r minus, they are null surfaces, because as r is equal constant, yes, we say that the r const surface is a null surface in r plus and r minus. That can be shown just by looking at the induced metric on the hypersurface. So, for example, considering a static observer. Okay, and so going to Kruskal, to Penrose, we find that this would be represented by something like that, like this. Okay, this is 1, this is 2, this is our universe, yes, for r greater than r plus, this is a parallel universe. then we have that this region would be a black hole, and this region would be a white hole, because in here one has to go from one has to move up, because the light quantity still look like Minkowski in these critical coordinates, and so one has to move up from values of r equal to r plus to decreasing values to r equal to r minus, and in here we would have a white hole, because we should have to move from r equal to r minus up to r equal to r plus. Okay, in the other case, when we go and look at critical coordinates in the k minus case, we find that things are quite similar. Maybe I should write everything again. Okay. Okay, or at least yes, let me just write the new things in here. I have that u minus would be defined as minus 1 over k minus times e to the minus k minus u. V minus would be equal to minus 1 over k minus e to the k minus v. Okay, such that du dv would be equal to e to the k minus u minus v dv minus du minus. Okay, and then we would have that this would be equal to e to the minus 2 k minus r times r minus over r minus times r plus minus to the minus 1 r minus r plus over r plus to the minus k minus over k plus. Okay, and so we would find that the metric, it will be equal to ds squared equal to r plus r minus over r squared e to the minus 2k minus r times r minus r plus over r plus 1 minus k minus over k plus dv minus du minus r squared d omega squared. Okay, and so we see that this is perfectly regular in r minus and it is singular in r plus. So again, we found that this metric does not cover the entire space-time, but actually we have that. If you look at this relation, we get that minus v k minus squared is equal to e to the 2k minus r times r minus over r minus times r minus r plus over r plus k minus over k plus. And so in r equal to r minus we have that uv is equal to 0, and so we find again the 45 degrees lines. This is u minus and this is v minus. Okay, then as r is equal to r plus, we find that this would be equal to 0. This would be equal to yes, this would be equal to 0, but k minus over k plus it is negative, so of course this diverges, and this time we find that we would find some yes, we will find two branch of hyperbole in here, in these two regions. So let me draw them like this, with these dotted lines. Okay, this would correspond to r plus, while these two lines they would correspond to r minus. Okay, while r equal to 0, from here we get that it is drawn in this region, and we find we find this hyperbole. Okay, so going to Penrose, we have that r equal to 0 is a time-like surface, because we have that in r minus f is greater than 0, so the time acts as a time, while we have that dr plus equal const, the r equal const equal to r plus surface, it would correspond to a null surface. Okay, and so going to Penrose, we would find that our diagram, it would look like this. Okay, with this being r equal to 0, this being r minus, and this being r plus, these are minus, these are minus, these are plus, and this is r plus. Okay, so we see that the two metrics, they do not cover the entire manifold, but we are able to join the patches to find one complete description of the spacetime, because we have that in the Kruskal plus case, we found that the Penrose diagrams, they looked like this, with this being a black hole and this being a white hole. Well, this was our universe and this is a parallel universe, where this is r minus, this is r minus, this is r plus. Okay, these are plus, these are plus, and this is r minus and r minus. Okay, and so we see that something very similar is found in here. The two things can be attached, because we have that this part, it would correspond, this part of the diagram, it would correspond to a white hole, while this part, it would correspond to a black hole. Okay, and we have that in here we have r minus, in here we have r plus, as we find in this case. So we can join the patches and finally have that the complete description of the Reisner-Nostrom solution in the case when m squared is greater than q squared is given by this kind of Penrose diagram. Okay, and so we could go on forever. Okay, so we found that we can join infinite patches. Okay, and starting from a point in our universe, there is this one, from r equal infinity, we can move towards the r plus, get inside of the black hole, then we leave, we cross r minus and we get inside of this region, where this is r equal to 0, avoiding the singularity, going back into r minus, into the white hole, and then crossing r plus to get back to r equal to infinity, but in another universe. So we finally understood what we found in the effective potential. It is true that we are able to move from r equal to infinity and bounce back to r equal infinity, but we end up in another universe. The Reisner-Nostrom solution describes a wormhole. And so now, of course, we have to understand if this kind of solution is actually possible, if it is physical, and we will see that it is not, because some blue shift would occur approaching the r minus horizon. To find the Reisner-Nostrom solution, we imposed the Einstein-Maxwell system, the Maxwell-Einstein system. We used the Maxwell tensor as the energy momentum tensor, and we used the hypothesis of spherical symmetry. So we were able to plug the usual ansatz inside of the Einstein Maxwell system and finally find the Reisner-Nostrum solution. But there was another way to proceed, and it is that to use the mass function parameterization. So the idea is that it is possible to use these ansatz ds squared equal to e to the 2 phi of r and t, psi of r and t, times 1 minus 2 m of r and t over r times dt squared minus 1 minus 2 m of r and t over r to the minus 1 dr squared minus r squared d omega squared. So this is the ansatz that we're going to use. Now, Einstein's equations in these parameters, they read as the derivative of m with respect to r equal to 4 pi g r squared t t t, derivative of m with respect to t equal to minus 4 pi g r squared t r t, and derivative of psi with respect to r equal to 4 pi g r over 1 minus 2 m of r and t over r times t t t minus t t r minus t r r. Okay, so I have that t t t. Okay, t t t in this way. It is equal to minus ft alpha plus 1 over 4 delta tt, which is 1, f alpha beta. But we know that the only non-vanishing component for the Maxwell tensor, it is that one in alpha alpha equal 0 and beta equal 1, or vice versa. So in here we have that alpha has to be equal to 1 to have this non-vanishing, and in here we would find that that this term would correspond to 1 over 2 f10. So in the end, from here we would find minus 1 over 2 f10 or f01 is the same, of course, because we have the scalar product. So f01 that of course is the same as f10 because f10 is just equal to minus f01. Then we have that trr, okay, would be the same. We would have minus 1 over 2 f01, okay, and trt, it is equal to minus f r alpha f t alpha plus 1 over 4 the delta of rt that is equal to 0, f alpha beta. So this is 0 and this is 0 as well, because to have the first strength tensor the first component in here not vanishing, we want alpha to be equal to t, but as alpha is equal to t, in here we have ftt that of course is equal to 0, and the same holds if we consider alpha equal to r, and so this would be equal to 0. This means that psi is a function of the time, and so it can be reabsorbed into the time coordinate. This is equal to 0, and so m is just a function of the radius, and this is the only equation that we need to solve. Okay, now let me go on. Let me write in here what TTT looks like. It is equal to minus 1 over 2 f01, okay, and now we go and look for f01. We want to express f01 to plug it in here and find the function m of r and t. And so first of all we have that f01 with low index, okay, it is equal to er by hypothesis. Okay, then we have that f01 I indices, it is equal to g00 g11 f01. So g00 it is equal to this, because we can set psi equal to 0 without any problem, since we have that it can be reabsorbed into the time coordinate. So this would be g00, this would be g11, so we get a minus, and in the end we just have that f01 is equal to minus er. Okay, then we have that the square root of the determinant of the metric, it is equal to this times r squared times r squared sin squared of theta, and so the square root it is equal to r squared sin of theta, but we can impose theta equal to pi over 2 without any loss of generality, and finally found that delta g is equal to r squared, such that from the Einstein equation that I wrote earlier in the covariant form, one has that the derivative with respect to mu of f mu nu square root of g has to be equal to 0 if we consider that outside of the source there is no current, no charges. Okay, and so we have that the only non-vanishing, the only non-trivial equations from here, they would be the derivative with respect to 0 of f01 times the square root of g, that is r squared, and the derivative with respect to 1 of f10, that is f01, because we can change the sign, of course, r squared equal to 0. Okay, such that in the end what we find is that f01 r squared has to be constant, and so we say that this constant is e, little e, and so f01 it is equal to e squared to e over r squared. Now we say that f10 is equal to e over r squared in such a way that er it is equal to e over r squared. Okay, so we say that f10 is equal to e over r squared. Let me see if I'm right. Okay, and so this would be equal to er, as I said. Now we're able to plug this inside of this equation using this form for TTT, and so we find that the derivative of m with respect to r it is equal to 4 pi g r squared. Then we would have the minus sign 1 over 2 f01, so we would have er squared, but er squared it is equal to e squared over r to the fourth, and so we find that in the end should there be a minus? I think so. No, okay, of course the minus drops, perfect, because we have that f01 it is equal to minus er. Okay, so we have that this looks like this, and finally we find 4 pi g e squared over 2 r squared, where 4 pi g squared it is equal to q squared, so we find q over 2 r squared. Okay, and now we have that m as a function of r, it is equal to a constant that we call m, okay, minus q squared over 2 r. Okay, so we found the expression for r and for m, and we can see that if we plug this in here, we get we get the Reissner-Nostrom metric. We get the 1 minus 2m over r plus q squared over r squared in here and in here as well. And so we have that in Reissner-Nostrom the mass that we were using is the mass at infinity, as r tends to as r goes to infinity. And moreover, we're able to find the mass of the electromagnetical field just by looking at what would be the mass outside of the source. And so we have that the mass of the electromagnetic field, it is equal to m at infinity minus m in r, where r is the radius of the source. And so m at infinity it is just equal to m minus m plus q squared over 2r. So we have that the mass of the electromagnetic field, so the energy that is related to the electromagnetic field, it is given by q squared over 2r. Okay, moreover we can say that m in rm, where rm is equal to q squared over 2m, it is equal to 0, and m for r minor than rm, it is minor than 0. And so this would explain the weird behavior that we find approaching the singularity, because as we approach the singularity, the mass gets negative, this mass parameter, it gets negative, and so there would be some kind of anti-gravity approaching the singularity, and so of course there would be a repulsion. Okay, now I want to show that R minus is not stable. Okay, I don't need this. Okay, I want to show that R minus is not stable, and blue shift occurs in R minus, to then conclude that this kind of objects they should not exist, even because we're able to determine the Schwinger effect that would suggest that these black holes cannot exist. Okay, so now I want to show that R minus is not stable, so I will consider something like this. I have that this is R plus, this is R minus. Okay, I have an observer that falls inside of the R minus region. Okay, and a photon that comes from our universe and that is measured by the observer. So the observer that is falling is free falling along a geodesic, and so for him we find that E sign is equal to U0, L sign is equal to minus U3, but we can set it to be equal to 0 because we're considering the radial motion. And as always we get that from umu equal to 1, we get that E sign squared over F minus R dot squared over F has to be equal to 1. And so R dot, there is UR, it is equal to minus the square root of E sine squared minus F. Okay, while U0, it is equal to E signed over F. While for the photon we have that P0 is equal to E, and P mu, again we would have P3 equal to L, but we can set it to 0 because the motion is radial. So we have that P mu is equal to 0, is the condition for the photon, and so we find that P r squared is equal to PR is equal to minus E, because we will find E squared over F minus PR squared over F equal to 0. So PR equal to minus e as we're considering the photon that is going inwards. Now from here we get that PR with low index it is equal to E over F, okay, and now we're able to determine the local energy that would be equal to P mu and it is equal to E over F times E signed minus the square root of E signed squared minus F, and we have that that a divergence occurs in r equal to r minus, because this would be equal to 0, and so there would be an infinite blue shift on the r minus region, and so we have some kind of blue shift singularity, and it is not possible to reach r minus, because in principle one would be, it's like energy would burst, I would say, in the r minus region. Okay, so the r minus is an infinite blue shift surface, and every small perturbation would get an infinite blue shift. Okay, now another important thing I want to say about this kind of black holes is that actually we expect that they do not exist, so we have no problems with these divergences that we found, because there is an effect that is called Schwinger effect that says that the rate of production of Schwinger couples is proportional to some constant times an infinite series, so from n that goes from 1 to infinity, of some e to the minus m squared times some other terms. We're interested in this. We have that the Schwinger couples, they are these couples of positive and negative charge that are produced outside of a electrically charged source, and we have that the production rate of the Schwinger couple, it would be such to actually annihilate the charge of the black hole, because charges would be produced outside of the black hole. The ones with the same charge of the black hole, they would fall into the black hole and annihilate its charge, while the other charges, they would just leave the black hole and they would travel towards infinity. Okay, and so we expect these charged black holes not to exist because of the Schwinger effect. But there is something interesting that occurs in the case of magnetic charges, because in that case we have that the Schwinger effect would be negligible. So let me go and see what a magnetically charged black hole would look like. First of all, let me say that magnetic monopoles should exist. There is a very strong suggestion that comes from our theories that these magnetic monopoles, they should exist, because if we say that the symmetry in the early universe was SO5, and then it broke into SO3 colors times SO2 parity times U1 hypercharge, it would look like in the symmetry breaking the monopoles should have played a major role. So there is the strong suggestion of this of their existence. Now, if we say that magnetic monopoles exist, some things have to be changed, such as the Maxwell equations, for example, and so we want to find the Reissner-Nostrom solution considering the magnetic charge, solving, as we did before, the Maxwell-Einstein system, but this time we have to work with different Maxwell equations that are related to the fact that, of course, as we're saying, magnetic monopoles, they would exist. And so in special relativity we have that the divergence of E, it is equal to 4 pi rho E. The divergence of B, it would be equal to 0, but now we write it as 4 pi rho m. The rotor of E, it would be equal to 4 pi jm vector minus the derivative of b with respect to t, and the rotor of b, it would be equal to 4 pi je minus plus the derivative of e with respect to t. Okay, and this would be coded by the derivative with respect to mu of f mu nu equal to 4 pi j nu, and the derivative with respect to mu of f mu nu tilde equal to 4 pi, and this would be je, okay, 4 pi j m nu. Okay, now we have that f mu nu tilde, it is defined as 1 over 2 epsilon mu nu alpha beta f alpha beta over the square root of g. We have to divide by the square root of g, because otherwise this would be a tensor density. In fact, we have that epsilon mu nu transforms as epsilon prime mu nu alpha beta equal to the determinant of lambda times lambda mu lambda nu lambda alpha lambda beta rho sigma delta and gamma, epsilon rho sigma delta and gamma. Okay, so it does not transform as a tensor, because we have this determinant of lambda, but we know that determinant of lambda is equal to the square root of g, because if I consider some g mu nu, if I consider g mu nu equal to lambda alpha mu lambda beta nu of eta alpha beta, and it is always possible, because it is always possible to find local inertial reference frame in some point of the space-time, in a point of the space-time. So we would have that from here we would get the determinant of g, it is equal to the determinant of lambda squared times the determinant of eta alpha beta, that is equal to -1. Okay, and so the determinant of lambda, it would be equal to the square root of the absolute value of the determinant of g mu nu, that we call g. Okay, and so this is what we find in here. We have that this would be equal to the square root of g, and so we have to divide by the square root of g in order to have that this quantity transforms as a tensor. Okay, we have that f mu nu tilde defined in this way. It would be the equivalent of the field strength tensor, but with e and b that are switched. So for example, the 0, 1 component, it would be with I indices, it would be minus BR, not minus ER. So I just flip E and B. Okay, so then I go to covariant, as I did before, where we have just to switch the partial derivatives with the covariant derivatives. And yes, now we can go with our discussion. So let's say that the source that we are considering, it is just a magnetic charge, so we would have that minus BR is equal to F01 tilde. Okay, but F01 tilde is equal to 1 over 2 epsilon 01 alpha beta F alpha beta over the square root of G. Okay, so alpha and beta, they have to be equal to 2 and 3, or either 3 and 2, or otherwise 3 and 2. And so we have that this would be F23. This would we know that epsilon, this is the Levi-Civita symbol, so we know that epsilon 0, 1, 2, 3 is equal to 1, but epsilon 0, 1, 3, 2 it is equal to -1. So it will be equal to F23 minus F32. But we know that F32, that this tensor is antisymmetric, so F32 is equal to minus F23. So in the end, we would get that this is equal to F2 times F23, and the 2's they go away, so that we have F theta phi over the square root of G. This is our starting point, and this means that as in here we have in the f tilde tensor we have that the only non-vanishing components are f01 and f10. This is translated into the fact that in the f tensor the only non-vanishing components are f theta phi and f phi theta. Okay, so now we go on. We have that we consider the ansatz with the mass parametrization. Okay, so the usual one, ds squared equal to e to the 2 psi of Rnt times 1 minus 2 m of Rnt over r times dt squared minus 1 minus 2 m of Rnt over r to the minus 1 dr squared minus r squared d omega squared. Okay, and I have that the Einstein's equation. Yes, I plug the ansatz inside of the Einstein equation, and in this new parameterization I would find that the derivative of m with respect to r it is equal to, as I said before, 4 pi g r squared t t t. The derivative of m with respect to t it is equal to minus 4 pi g r squared t r t. The derivative of psi with respect to r it is equal to 4 pi g r over 1 minus 2m of Rnt over r times t t minus t r. Okay, so at this point I have that t it would be equal to minus f t alpha plus 1 over 4 delta tt there is 1 times f alpha beta. But we have that this is different from 0, this is non-vanishing just in the case when alpha is equal to theta, beta is equal to phi, or vice versa, while in here we would have that for every value of alpha we would get that this term is vanishing, so that t is equal to 1 over 2 f theta phi f theta phi. Same stuff for TRR. Okay, while TRT it is equal to 0. It is easy to show. Where the delta would be equal to 0, and here we would have that everything is 0. So we have that psi is just a function of the time, so it can be reabsorbed as we said before. This would be equal to 0, so the mass is a function of r, and this is the only question that we need to solve. So we go on with our discussion, and we have that okay, this will be TTT, this is not a plus. Okay, and we have that I consider, where is it? Okay, I consider f theta phi I indices as g theta theta, g phi phi, f theta phi. Okay, g theta theta is equal to minus r squared, g phi phi is equal to minus r squared sin theta squared, so it would be r to the fourth sin squared of theta times f theta phi, that is equal to minus br the square root of g. Okay, we have that the square root of g, it would be, we set psi equal to 0, and so we get that this times this it would be equal to 1 times r squared sin squared of theta, so the square root it would be r squared sin squared of theta. Okay, so I plug this in here. Okay, sorry, in here it was, because we're taking the inverse, so it is 1 over r to the fourth sin squared of theta, and in here I have br r squared sin of theta. Okay, such that f theta phi, and I will write it here, f theta phi low index, it is equal to minus the square root of g b r. F theta phi I indices, it is equal to minus br over r squared sin theta. Okay, and in here we would have that the square root of g can be replaced by r squared sin theta. So we would have that f theta phi low indices, it would be minus br r squared sin theta. Okay, and then what else do we need? Okay, we look at the Maxwell equations in their covariant form and find that the derivative with respect to mu, as we consider j nu equal to 0 outside of the source, of f mu nu times the square root of g has to be equal to 0, okay, such that the derivative with respect to theta of f theta phi times r squared sin theta equal to 0, okay, and the derivative with respect to phi of f theta phi r squared sin theta equal to 0. Okay, so this means that f theta phi r squared sin theta, of course we can set sin theta equal to pi over 2 without any loss of generality, as we always do, because we have spherical symmetry. So this means that f theta phi does not depend either on theta and on phi, and this makes sense with the fact that that br it is just a radial magnetic field, so it does not depend on the angle. So we have a look at the other Maxwell equations. We have that f mu nu derived with respect to lambda plus f nu lambda derived with respect to mu plus f lambda mu derived with respect to nu equal to 0, and I get that as mu is equal to t and nu and lambda they are equal to theta and phi, I get that f theta derived with respect to phi plus f theta phi derived with respect to time plus f phi t derived with respect to theta is equal to 0. Okay, and so from here I get that f theta phi derived with respect to t has to be equal to 0. Okay, while when mu is equal to r, I get that f theta phi derived with respect to r is equal to 0, and that's because all of the other derivatives, these two derivatives, they would be equal to 0 because I just found it. Okay, and so now we can finally solve our system, because we have that if f theta phi derived with respect to t is equal to 0, and if derived with respect to r it is equal to 0 as well, this means that f theta phi is equal to a constant, okay, and in particular this means that minus br times r squared, it is equal to a constant that I say is p minus p. Yes, because I take, oh no, okay, yes, it is like that, such that br is equal to p over r squared. Okay, so we found that the magnetic field, the radial magnetic field, it looks like p over r squared. let me write it here, where P is a constant and it is the magnetic charge. Now we're finally able to plug this inside of this and find that the derivative of m with respect to r, it is equal to 4 pi g r squared. TTT would be 1 over 2 f theta phi, so br squared, that is p squared over r to the fourth, and so we find 4 pi g p squared, that we say it is equal to some capital P squared over 2 r squared, and so we find that m of r, it is equal to some constant m minus p squared over 2r, and we can make the same consideration that we made in the case of the electrically charged black hole. We find the same metric, but this time in another charge. We will find ds squared equal to 1 minus 2 m over r plus p squared over r squared times dt squared minus 1 minus 2 m over r plus p squared over r squared to the minus 1 dr squared minus r squared d omega squared. Okay, but this time the Schwinger effect would be negligible because we have that gamma. There is the rate of production of Schwinger couples. It is proportional to some constant times an infinite series of sampling times e to the minus m squared times other stuff, and we have that this m squared now it is huge because we have that m is equal to 120 gigaelectron volt in the case of the magnetic monopoles, and so the Schwinger effect is negligible, and these black holes they would look stable. Okay, now we talk about extremal black holes. We finished our discussion on the magnetically charged black holes. So we talk about extremal black holes, and then we are going to care. Okay, so let's say that we have m equal to q. We're still in the Reissner-Nordström metric, so we are studying the extremal black hole, the extremal case in which m is equal to q. What happens in this case? We have that the metric it would look like ds squared equal to 1 minus m over r squared dt squared minus 1 minus m over r to the minus 2 dr squared minus r squared d omega squared. Okay, we would have that 1 minus m over r squared, it would be always greater or equal than 0. It would be equal to 0 just when r is equal to m. Okay, and we have that if I define a Killing vector xi alpha 1 0 0 0 associated to the time symmetry, the xi alpha product it would be equal to 0 just in r equal to m, but it would be always positive. So there is a Killing horizon here in r equal to m where the Killing vector it is null, but there is no region in which the Killing vector is space-like. Okay, so let me consider a time like geodesic, such that E sine is equal to u0 and sine is equal to minus u3 and mu is equal to 1, and so we find the usual stuff. In the end we find r dot squared plus v effective equal to E sine squared, where v effective it is equal to 1 minus m over r squared times L sine squared over r squared plus 1. Okay, we have that in this case the shape of the potential it would look like this. This is v effective, this is r. Okay, we would have that this is m and this is 1, so asymptotically it goes to 1. So we find that the particles with energy greater than 1, again they should not be able to reach the singularity, they should bounce back. Okay, and so we want to see this kind of description. We want to find this kind of description in a metric that is regular in R equal to m, because R equal to m at this point it is a singularity, and it is a coordinate singularity because the scalar quantities, they do not diverge in R equal to 0. Okay, and so as always, to remove the singularity I look for the null coordinates. Okay, so let me define the first of all I have that looking for the radial null geodesics, that squared is equal to 0, theta and phi are constant. One finds that dt in dr it is equal to plus minus 1 minus let me think, okay, 1 minus m over r to the minus 2. Okay, yes, it should be to the minus 2. Perfect. I define that our to us coordinate r star that is equal to the logarithm, it is equal to 2m times the logarithm of r over n minus 1 minus m squared over r minus m, but I think I'm forgetting something. There should be some r in front, in fact. Vabbè. Yes, it was r star equal to r plus 2m times the logarithm of r over m minus 1 minus m squared over r minus m. And so in this way we find that dt in dr star it is equal to plus minus 1, where t minus r star is constant, and it is defined as u, which is the retarded coordinate, and t plus r star is constant and defined as v, advanced coordinate. So in this way we go to double null and we find that ds squared is equal to 1 minus m over r squared du dv minus r squared d omega squared, where r of course is a function of u and v. In the advanced metric we have that d s squared is equal to 1 minus m over r squared dv squared minus 2 dv dr minus r squared d omega squared. I can find the radial null geodesics, imposing that d squared equal to 0 and theta and phi are constant. Okay, and I get that dv is equal to 0 and dv it is equal to 2, dv in dr it is equal to 2 over 1 minus m over r squared. So if I have to draw the graph in the r t prime, where t prime is the Finkelstein time, I get that as this is m, these geodesics, they would look like this. Okay, while in here we would have something like this. Okay, so it looks like the case of m squared greater than q squared without the second region. So it looks like this is the one region and this is the free region. Again, if we draw the v const, we can find the light cons, and we have that light cones in the universe, they include this region in their future, but once inside of the r minus the m region, the light cones, they do not include this the outer region in their future, and so this would be a black hole. Okay. The problem is that again we cannot describe what we found in the what we found for the effective potential, because once r equal to m is crossed, it is not possible to bounce back. But rm, it would be at a value of r that is actually minor than r equal to m, and we have that rm, it would be the, for a particle that comes from infinity with zero velocity, it would be the turning point, as we saw earlier. So again we have some problem. There is something that is missing, and we need to work on the extension of the metric. So we would like to go to Kruskal from the double null metric that I wrote in here. The problem is that in this case, in the extremal black hole case, the surface gravity is equal to 0. In fact, I have that k would be equal to 1 over 2 f prime of h. That is something that is found okay, for this kind of metric in the diagonal form with f yes, with f that would be equal to this. Okay, and so we have that this is 1 over 2 f prime, it would be 2 times 1 minus m over r, m over r squared. No, yes, m over r squared. And so in r equal to m, we would find that this is equal to 0. So if the surface gravity is equal to 0, we cannot define the Kruskal coordinates in the usual way. But we need to find another way to define these coordinates. In particular, we remember that the Kruskal coordinates, they were local inertial on the h plus and h minus horizon in the case of Schwarzschild, and so now we want to do this stuff. We want to find the local inertial coordinates on the horizon, on the future and past horizon, and then we want to take those coordinates as the Kruskal ones. Okay, and so let me just erase everything, we don't need this. Okay, let's say that we take, this is n. Okay, we want to build our local inertial coordinate system in here where x mu is equal to, this is in the advanced metric, so we in here we have that x mu would be equal to v0 times v0 n theta 0 phi 0. Okay, the advanced metric, it would be ds squared equal to 1 minus m over r squared times dv squared minus 2 dv dr minus r squared d omega squared. Okay, and the local inertial metric, it would be ds squared equal to dx0 squared minus minus dx1 squared, but let me just check for a thing. Yes, we have that, we want to write 0r. I know this is just notation, but I still want to be clear. So dx0 squared minus dx1 squared, okay, then in null coordinates, going to double null, it would be dx plus dx minus. Okay, and so we have that eta plus plus is equal to 0, eta minus minus is equal to 0, eta plus minus is equal to 1 over 2. We proceed as we did for Schwarzschild, when we wanted to see what would be the local inertial coordinates on the h plus and h minus horizon. So we have that grr is equal to 0, gvv is equal to 1 minus m over r squared, and vr, it is equal to minus 1. Okay, I'm only considering the 2D metric, so not the angular part, and then I have that G mu nu is equal to B alpha mu B beta nu eta alpha beta. We have that the only non-vanishing component for eta alpha beta is that one in plus and minus, or minus and plus, and so this would be 1 over 2 b mu plus b nu minus plus b mu minus b nu plus. Okay, and then we have that maybe I write it here. That 0 is equal to GRR in X, it is equal to BR plus BR minus, and so from here we get that BR plus is equal to 0. Then we have that 0 is equal to GBV in X, it is equal to V minus BV plus BV minus, and so from here we get that BV minus is equal to 0, and minus 1 that is equal to GVR in X, it would be equal to 1 over 2 BV plus BR minus plus V minus BR plus. Okay, but we have that this would be equal to 0 because of this, and so finally we would find that BV plus BR minus is equal to minus 2. Okay, then we look at the Christoffel symbols because we will need them in the expansion of the metric of the local inertial coordinate, and we find that all the Christoffel symbols, they are equal to 0 because we have that the Christoffel symbol would be gamma mu alpha beta equal to 1 over 2 G mu nu G alpha nu beta plus G beta nu alpha minus G alpha beta derived with respect to nu. Okay, and we have that if I compute this in X, okay, all the derivatives when computed in X in here, they are equal to 0, where X would correspond to R equal to M. So all the Christoffel symbols, they are equal to 0, and finally we have that C beta is defined as A beta plus B beta mu x mu minus capital X mu plus 1 over 2 B beta lambda gamma lambda mu nu x mu minus capital X mu times x nu minus capital X nu plus terms of the third order, and so we get that C plus, so we are on the H plus horizon because we are working on the advanced metric. H plus, it will be equal to, we can set A beta equal to 0 because it is a constant. B plus, the only one that does not vanish in the plus, it is BV plus times V minus V0. Okay, then we have that this vanishes, so plus little o of 3, and C minus, it is equal to B R minus M. Okay, so we have that the null coordinate V, it looks like it is local inertial on the H plus horizon, and in here we can define U as this C minus, so the Kruskal U as BR minus R minus M. We can fix BR minus to be equal to minus 1, okay, such that U is equal to minus R minus M. In this way we would find that BV plus has to be equal to 2. We can set V0 equal to 0 because it is a constant, and we have that C plus, it is equal to 2V, and U is equal to minus R minus M. Then we have that R star is equal to R plus 2M times the logarithm of r over n minus 1 minus m squared times r minus n. Okay, we have that little u is defined as let me think, it is okay, we have that v is defined as t plus r star and u is defined as t minus r star, such that u would be equal to v minus 2r star. Okay, sorry, I'm a little bit lazy, so u minus v. Okay, yes, it would be u equal to v minus 2r star. Okay, and so this would mean that if I plug this inside of u is equal to v minus 2r minus 4m, the logarithm of r over m minus 1 minus plus 2m squared over r minus m. Okay, but I have that v as I approach r equal to m, we have that this is finite, this is finite, this diverges, and so we can approximate u as minus 4m times the logarithm of, we would have r minus m over m, but r minus m, it is just equal to u. Of course, in the logarithm we take the modulus of u, of capital U. Because the argument of the logarithm would be positive. Okay, so we would have the logarithm of u over m, if I'm not wrong, okay, minus 2m squared over u. Okay, so I can invert this relation to find the Kruskal coordinate u in terms of this little u. And so what I found is that on the h plus horizon, the local coordinates, they are given by 2v and Kruskal u, that is found inverting this relation. And on the h minus I would find Kruskal v and 2, where Kruskal v is found in a very similar way. We have that v would be equal to minus r minus n. We would find the same stuff, but here I would have a plus sign, if I'm not wrong, or here maybe. But it is the same calcula. Okay, and so now I am able to draw a graph, because I have that. Okay, I have that as r is equal to m, u and v, they are equal to 0. Okay, so I have, because u is defined in this way and v as well. Okay, so I have that in Kruskal coordinates, this would be u and this would be v. Okay, u equal to 0 would correspond to r equals m, and v equal to 0 it would correspond to r equal m. Okay, and then I would have that as okay, of course I have to plug this inside of the metric at this point. Okay, so maybe let me go from here. So on h plus we have that 2v, the local inertial coordinates, they are 2v and u, and on h minus they are v and Kruskal v and 2. So now we are able to plug the Kruskal coordinates inside of the double null metric and find that ds squared is equal to 1 minus m over r squared, du in capital Du, because it only depends on that, dv in capital DV times du dv minus r squared d omega squared. This metric it is perfectly regular on the h plus and h minus horizon, so we were able to remove the coordinate singularity r equal to m that defines the two horizons. And then what else can we do? We have that the future horizon would correspond to u equal to 0, and the past horizon it would correspond to v equal to 0. Moreover, we have that we have that r equals 0. It is time-like surface, because we have that that f is greater than 0 in r equals 0. Am I right? Yes. And so okay, so now I want to draw the advanced solution and the retarded solution in the Penrose way. And in particular, I have that the advanced solution it would be something like this. Where this is E0, this is E plus, this is I plus, this is I minus, and this is E minus, while this is the H plus horizon, so this would be the H minus 1, this is H minus, and this is R equals 0, because it is a time-like singularity. In the other case we would have something very similar, but in this case we would have that R equals 0, it would be going down, and then we would have E0, E plus, E minus, I minus, and I plus. This would be the H minus, this would be H plus, and this would be H plus. So what we see is that, again, as we did in the case when m squared is greater than q squared, we can join the patches to have a complete description of the spacetime, and in particular we would find that in the end, joining the patches, this would be the Penrose diagram that we would find. In principle, we could go on, we could join infinite patches, and so we have that this is r equal to 0. Okay, so we have that again the extremal black hole describes a wormhole, because it is possible to move from some r equal infinity in our universe to r equal infinity, but going to another universe, moving. We have the light cones, they are Minkowski in the critical coordinates, so they look like in the Minkowski case as 45-degree lines. So we move inside of the light cones, we get to this region, and we have to move up. We move along physical trajectories, we go back in r equal infinity, but in another universe, and that of course would explain what we found for the effective potential. It is true that it is possible to go from r equal infinity to r equal infinity bouncing at some values of radius, but it is not possible to bounce back in your own universe. You have to go to another universe. Okay, and so with this we finished our discussion on the electrically charged black hole, and finally we go to the rotating ones that are described by the Kerr solution. So we want to study the solution outside of a rotating source. We have that in this case we don't have the spherical symmetry anymore, and so there is no more the Birkhoff's theorem saying that that the solution has to be static outside of the source because there is spherical symmetry. And so things are more complicated. The ansatz would be much complicated, and of course we would not be able to solve the Einstein equations in that ansatz. So the solution came from Kerr, that in 1963, just for mathematical purposes, so it was not looking for some physical solution. So he was studying a metric of this kind, ds squared equal to g mu nu dx mu dx nu equals to eta mu nu dx mu dx nu minus h L mu L nu times dx mu dx nu, with the relation eta mu nu L mu L nu equals to 0, equal to g mu nu L mu L nu. Okay, and so with L being a null vector, and he actually found a form for H and one for L, such that this kind of metric would solve the Einstein equations. If I'm not wrong, it should be H equal to 2m times r to the third over r squared plus a squared. Okay, let me see if this is H. No, r to the fourth a squared zeta squared. Okay, but the 2m times r to the third, it was right. And L mu, it is much more complicated. It is 1 a x plus r plus a y. Okay, doesn't matter. Or maybe it does. I don't know. Okay, let's say that there are some h and L mu that make this metric a solution for the Einstein equation. So actually Kerr just casually he found the solution for the axial symmetrical problem. Okay, then Boyer and Lindquist found different coordinates to describe the same kind of metric. And in the Boyer-Lindquist coordinates, the Kerr metric would read as 1 minus 2mr over rho squared times dt squared plus 4mar sin squared of theta over rho squared times dt d phi minus rho squared over delta times dr squared minus rho squared times d theta squared minus r squared plus a squared plus 2m a squared r sin squared of theta over rho squared times sin squared of theta d phi squared. So this is the metric in the Boyer-Lindquist coordinates. Okay, such that the rho squared is equal to r squared plus a squared cos squared of theta, and delta is equal to r squared minus 2 mr plus a squared. The relation between the Kerr coordinates and the Boyer-Lindquist coordinates, it is given by t signed equal to t minus r, x equal to r sin theta cos phi minus plus a sin theta sin theta sin phi, y equal to r sin theta sin phi minus a sin theta cos phi, and zeta equal to r cos theta, such that x squared plus y squared it is equal to r squared minus a squared sin squared of theta. Okay. No, r squared plus a squared, I'm sorry. And x squared plus y squared plus zeta squared. Yes, of course it is plus because we are just taking the square of everything. So in here we have a plus sign, and then we have the double products, they would cancel off. Okay, and then we have x squared plus y squared plus zeta squared equal to r squared plus a squared the sin squared of theta. So we have that capital R that is defined as the square root of this stuff, it is equal to r times the square root of 1 plus a squared over r squared sin squared of theta. So we can see that r, the letter r, it is not a radius, but it is just a label. It does not have any geometrical meaning, and we will see that it can be minor than 0 as well. It is just a label. Okay, so the Kerr metric, it has two limiting cases. The first one would be that one of a equal to 0 and non-vanishing mass. In that case we would find that rho, it would be rho squared, it would be equal to r squared when a is equal to 0, and delta it would be equal to r squared minus 2mr. In this case we would find that ts squared is equal to 1 minus 2m over r rho squared, dt squared, sorry, minus 1 minus 2m over r to the minus 1 dr squared. It is easy to show this, so you just have to make the computation. Minus r squared d omega squared. This is the metric and this is the Schwarzschild metric. So we have that as a is equal to 0, the Schwarzschild metric is recovered. Okay. While in the other case, the other limiting case, when m is equal to 0, we get that rho squared is equal to r squared plus a squared cos squared of theta, and delta it is equal to r squared plus a squared, such that ds squared it is equal to 1 minus 2mr over r squared plus a squared cos squared of theta dt squared. Then this would be 0 minus rho squared over r squared plus a squared dr squared minus, and in here I would have r squared plus a squared cos squared of theta minus r squared plus a squared cos squared of theta d theta squared minus r squared plus a squared sin squared of theta d phi squared. And this is just Minkowski flat space-time in spherical coordinates. So when a is equal to 0 we find Schwarzschild, when m is equal to 0 we find Minkowski, so no gravitational field. We already have a suggestion of the fact that a should be related to a rotation, and m it will be related to the mass, because in the absence of mass there is no gravitational field. Okay, then we can look at the symmetries of this metric, and we find that there is a time symmetry that is associated to the stationarity, not staticity. We can see that as we define we can define a Killing time vector that is associated to stationarity, and one that is associated to the axial symmetry. Okay, so the first one would be T alpha equal to 1, 0, 0, 0, and the second one would be phi alpha equal to 0, 0, 1, 0, 0, 0, 1. And we can see that our metric it is invariant under dt that goes to under t that goes to t plus epsilon, and when t goes to minus t, the metric is left invariant just if phi is sent to minus phi. In that case, we would find that that the metric is left invariant, and that is as well a huge hint of the fact that our metric describes some rotating source. Okay, so now we have that in 1918, Tyring and Lenz they found a metric that could describe the weak gravitational field far away from a rotating source, and it looked like ds squared equal to 1 minus 2 mg over r, where m is a function of the mass, times dt squared, plus for j for j over r sin squared of theta, plus in here as well, okay, plus terms of the order of the second order in the denominator for the r, again plus little o 1 over r squared d theta and d phi, okay, minus 1 plus 2 mg over r plus little o 1 over r squared plus dr squared plus r squared d omega squared. Okay, so this is exactly what Tyring and Lenz found, and if we confront this with the Kerr metric in Boyer-Lindquist coordinates, we find that that little m has to be equal to capital Mg, and j it has to be equal to little m times a. So the angular momentum j, it is related to the a parameter. We cannot say that the Kerr metric is the solution outside of a rotating source, but we can say that it is far away from the rotating source. We will see that we will find some theorem in that is called the Carter-Thompson's theorem, that ensures that the metric just outside of a rotating black hole, it has to be Kerr. But that's the only thing that we can say for sure. We cannot say that the metric outside of a rotating star, it is Kerr. We can say that it is far away from it. Okay, so now we have a look at the singularities in Kerr. We have that the first one, let me write again the Kerr metric. It is ds squared equal to 1 minus 2mr over rho squared times dt squared minus plus 4mar sin squared of theta over rho squared times dt in d phi minus rho squared over delta times dr squared minus rho squared times d theta squared minus r squared plus a squared plus 2m a squared r over rho squared sin squared of theta times sin squared of theta times d phi squared. So this is the Kerr metric. Now we have that the singularities, they are given in rho squared equal to 0 and delta equal to 0. Rho squared equal to 0, it would correspond to r squared plus first of all let me show the delta equals 0 singularity, because the rho equals 0 singularity, it has some it is a physical one, and it is quite peculiar. We have that delta equals 0, it would correspond to r squared minus 2mr plus a squared equal to 0, and so we would find that r plus minus, it is given, the solution for this equation, it would be given by m minus the square root of m squared minus a squared. Okay, so the delta equals 0, the solution for this equation exists as m squared is greater than a squared, or m squared equal to a squared. When m squared is minor than a squared, we have that there is no solution for this equation, and we would find that in that case, when m squared is minor than a squared, delta is always positive. Yes, it would be always positive. Now, these are the first singularities, and we will see that these are coordinate singularities because they do not diverge in the scalar invariance, while rho squared equals 0 would correspond to r squared plus a squared cos squared of theta equals 0, and so we have to have r equals 0 and theta equal to pi over 2 at the same time. Okay, but we have seen that in care coordinates x squared plus y squared is equal to r squared plus a squared sin squared of theta, and zeta squared is equal to r squared cos squared of theta, for zeta is equal to r cos theta. I don't know why I put the square. Okay, and so we would find that zeta is equal to 0 and x squared plus y squared is equal to a squared, given these two conditions. And so we would find that in the care coordinates, the rho squared equals 0 singularity would correspond to a ring. That can be, of course, avoided. It's just that you have to travel through the ring. And moreover, we have that the disk inside of this region, it is completely regular, and it is defined in r minus than 0. In particular, let me show that if I take some curve gamma that is defined as t const r const minor than 0 such that r is minor than the modulus of a and n, then theta const and phi that is defined between 0 and 2 pi. Okay, I have that the tangent vector would be given by m mu equal to 0, 0, 0 the phi in the S. Okay, we want to see if there is some we want to study the modulus of this, and we have that m mu it would be equal to g phi phi times the phi in the S squared. So g phi phi it is equal to minus r squared plus a squared plus 2 m a squared r sin squared of theta over rho squared times sin squared of theta times d phi in ds squared. But we have that this is minor than 0 with this given r much less than a and m. So as this is minor than 0, there is a minus sign, this is positive, so this is of course positive as well, because it is the square of this of the phi in ds, and so we found that the m mu would be a time-like vector, and so we found time-like trajectories that are closed inside of this r minus than 0 region. This is quite weird, but it is something that is found from the coordinates. Okay, now I want to study the geodesics in care, as I always do, and then I want to be able to remove the coordinate singularities. Okay, so the discussion on care is going to finish in 3 pages. Perfect. And we are still going. So let me look at geodesics in care. We have that. We have one vector t mu that is associated to the stationarity, and it is equal to 1, 0, 0, 0. And another vector phi mu that is associated to the axial symmetry, that is 0, 0, 0, 1. So we have that there is one killing energy defined as t mu mu, and one killing energy L that is defined as phi mu mu. This would be u0 and this would be u3 minus u3. Okay, now what's the difference with the other cases that we already studied? It is that u0 it is equal to g00 u0 up plus g03 u3, because this time we have a diagonal term in the a non-diagonal term in the metric, and then in here we would find minus g30 u0 minus, this is a plus, g33 u3. So if L sign is equal to 0, it does not mean that u3 is equal to 0. This is the thing that we find now. So in principle we have that if the initial angular momentum, that this time it is defined as L zeta because we have axis symmetry, so it refers to one of the axes, to just one of the axes. We have that in principle, if the angular momentum is equal to 0 far away from the source, then the angular momentum approaching the source it has not to be equal to 0, because asymptotically we do agree with the fact that L zeta is equal to u3, because asymptotically g30 is equal to 0. But as we approach the source, g30 is not equal to 0 anymore. So u3 is not 0 at that point. Okay, in particular, okay, I will talk about Zamo in some minutes. Before, let me just go on with this discussion. I define E sign, L sign. Now I want to find the geodesics. So I ask umu to be equal to 1, because I want the trajectory to be physical. And now I have 3 equations and 4 variables. So of course the problem is not solvable. I need one more variable. And so here it comes the so-called one more equation. So here it comes the so-called Carter constant that was found by Carter, and it is related to deeper symmetries, in particular the separability of the Jacobi equations, of the Hamilton-Jacobi equations. And I have that the Carter constant, it is associated to a killing tensor k mu nu, that is defined as 2 rho squared L mu n nu, with the with the brackets that would suggest the permutations. This means L mu n nu plus n mu L nu, okay? And we have that this killing tensor would satisfy k mu nu covariant derivative with respect to alpha with the brackets equal to 0. So this means that we have to consider all the permutations of indices. Okay, so we have that the Carter constant, it will be given by k mu nu. It will be given by k mu nu u mu 1, okay, and we have that L mu is defined as r squared plus a squared over delta, then 1 0 a over delta, and n mu, it is defined as r squared plus a squared over 2 rho squared minus minus delta over 2 rho squared 0 a over 2 rho squared. Okay, and so in this way our system, it is solvable, and we can find the equation that describes the angular motion and the radial motion, because now we have 4 variables and 4 equations. Okay, so going back to this discussion, let's talk about the ZAMO, that would be the zero angular momentum observer. It would correspond to the observer that has Lz equal to 0. Okay, and in that case we find that 0 is equal to minus g free 0 u0 minus g free free u free. So we have that u free over u0, it is equal to minus free over minus g free 0 over g free free. We call this ZAMO frequency, and we have that u free over u0, it would be an angular velocity defined in the t, because it would be defined in ds over dt in ds. So what we have is that as an observer starts with some zero angular momentum from infinity, approaching the source, it has to move with some angular velocity that is not equal to 0. So it gets some angular momentum. It is not possible to fall radially without any acceleration. The geodesics, they all rotate approaching the source. So it looks like the source that rotates drags the geodesics with it. Okay, so now let me compute the ZAMO frequency. Okay, I have that omega h, it is equal to minus g free 0, it would be this one, so 2, okay, because g free 0 is half of this, so minus 2 mar sin squared of theta over rho squared over g free free, we take the minus sign from here, and so r squared plus a squared plus 2 ma squared r sin squared of theta over rho squared times sin squared of theta. Okay, so we can already remove the sin squared of theta. Okay, then the denominator can be expressed as 1 over rho squared in such a way that this and this, they do go away, and we're left with 2 mar. Okay, rho squared times r squared plus a squared, that would be r to the fourth plus r squared a squared cos squared of theta plus r squared a squared plus a to the fourth cos squared of theta plus 2m a squared r sin squared of theta. Now this is equal to r to the fourth plus 2 r squared a squared minus r squared a squared sin squared of theta. I use the relation cos squared plus sin squared equal to 1. Okay. Plus a to the fourth minus a squared sin squared of theta plus 2m a squared r sin squared of theta. Now I factorize a squared sin squared of theta in there. In here I find that this is r squared plus a squared squared. Then I factorize a squared sin squared of minus a squared sin squared of theta and find that this is just delta. And so in the end I get that this is the omega h, which is equal to 2mar over r squared plus a squared squared minus a squared times the sin squared of theta times delta. This is the sum of frequency. Okay. We will use it later. Now, I want to remove the singularities from the metric, the coordinate singularities from the metric, so the delta equals 0, but this time I cannot proceed as always just by looking at the radial null geodesics, because there are no radial null geodesics. All the geodesics, as I said, they have to be dragged in some rotation. So I will go by some different, I will proceed in a different way. And I will use the so-called principal null congruence. We know that a congruence is defined as a family of curves that is defined that is tangent to some vector field, defined starting from some curve sigma that covers all the space-time, all of the manifold. And so I say that my congruence, it is defined starting from some vector L mu that is equal to r squared plus a squared over delta plus minus 1 0 a over delta. Okay, so I say that this defines my principal null congruence. Now I have that L mu would be equal to I have that it is a null vector such that L mu is equal to 0. Okay, so I have that all the curves that are tangent, all the trajectories that are tangent to L mu, they would define null geodesics. And in particular, L mu can be expressed as dt in the S, dx in the S, d theta in the S, and phi in the S. So we have that dt in the R, it is equal to this divided by this, and so it is equal to plus minus this object. I take the ingoing trajectory, and so I take the minus r squared plus a squared over delta. And in the same way I find that d phi in the R is equal to minus a over delta. Now if I define v as t plus some function capital T, and phi bar as phi plus some capital Phi, I have that dv, I define dv in the R and the phi bar in the R equal to 0 by imposing that dt in the R has to be equal to r squared plus a squared over delta, because t is arbitrary and phi and capital Phi as well, so I can do this. I have that d capital phi in dr has to be equal to a over delta, and in this way we can define v and phi such that dv in dr is equal to 0 and d phi bar in dr is equal to 0. Okay, and so I have that dv, it would be equal to dt plus r squared plus a squared over delta times dr, and d phi bar equal to d phi plus a over delta dr. Okay, so we chose these coordinates because in this way we would have something that is similar to what we had in the Schwarzschild and Reisner-Nostrom cases. It looks like this could define some radial null motion. It is not, but still it looks like. Okay, and so now we plug these two inside of our metric, and we find, I won't do the calcula because that is very long, but it would be ds squared equal to 1 minus 2mr over rho squared dv squared plus, or no, minus rho squared over delta dr squared minus rho squared d theta squared minus r squared plus a squared squared minus a squared sin squared of theta delta d phi bar squared. Okay, and then I have plus 2 a sin squared of theta, if I'm not wrong, dr d phi bar, let me see, yes, plus 4 mar sin squared of theta over rho squared dv d phi bar. Okay, and so this would be the null metric that is not singular in delta equal to 0. Okay, now let's talk about the Kerr horizon. Let me erase everything. This relation we will have to keep it in mind. Okay, this is not very difficult. So now we talk about the Kerr horizon. While in the Schwarzschild case the horizon was defined by the G00 equal to 0, in Kerr it is not the same. In particular, we had that in the Schwarzschild case the sigma for r const, it was a time-like surface outside of the event horizon. It was a null surface on the event horizon, and then a space-like surface for r minor than 2m, so inside of the event horizon. In the Kerr case, what we find is that the sigma tar constant is given by, it has some normal vector umu that is defined as lambda of x 0 1 0 0. Okay, so we have that umu it is equal to minus delta over rho squared lambda squared. Okay, and so we have that this is equal to 0 as delta is equal to 0. In particular, we have that this product, it would be negative for r between r minus and r plus, and positive for r minus than r minus and r greater than r plus. Okay. So we found that our observer cannot stay at r equal constant in this region, while okay, so we say that in here sigma is space like, and in here sigma is time like, where sigma is the hypersurface at constant r. Okay, so we have that r plus would look like the horizon of our black hole, because once r plus is crossed, r has to decrease. Okay, but it is also possible to have a look at the static observers and define what would be the radius at which the observer cannot be static. And so if I say that my static observer has some velocity that is given by mu equal to u0, 0, 0, 0, I find that mu is equal to 1 minus 2mr over rho squared times u0 squared, and we know that this is negative. Okay, we have that in order for this to be negative, so we find that when this is negative, the observer cannot be static. Okay, we have that this has to be equal to 1 minus 2m over r equal to over rho squared no, I'm sorry. So, pause. Okay, so if I consider the static observer, I have that mu is equal to u0, 0, 0, 0, while mu is equal to this stuff, to 1 minus 2m over 1 minus 2m r over rho squared times u0 squared. So, we want to see what would be the sign of this scalar product, and we can see that it depends on this term. So we have that 1 minus 2mr over rho squared is equal to 0 when rho squared is equal to 2mr. But rho squared, we know that it is equal to r squared plus a squared cos squared of theta, and so this would mean r squared minus 2mr minus plus a squared cos squared of theta equal to 0. That would correspond to rs plus minus equal to m plus minus the square root of m squared minus a squared cos squared of theta. That coincides with r plus minus just when cos of theta is equal to 1. So we found that the observer can be static in the hermetic outside of r s plus and inside of rs minus, and it cannot be static in the region between rs plus and rs minus. With rs plus there is greater than r plus. So we are able to define a region that is called ergosphere. There is this one. This would be rs plus and this would be r plus. So this is the ergosphere. We have that in here the radius they do coincide, and inside of the ergosphere we are still not inside of the black hole, because the r plus horizon is much deeper, I would say, while while it is not possible to be static. So in this region it is not possible to be static, but it is possible to escape the black hole because the R plus horizon has not been crossed. So R can increase, decrease, or stay constant inside of the ergosphere. We want to talk about stationary observers. We have that stationary observers are observers that move at R and theta constant. So if I have a Killing vector associated to the stationarity that is defined as 1, 0, 0, 0, and another that is associated to the axial symmetry that is defined as 0, 0, 0, 1, okay, the stationary observer, it is proportional to T mu plus W phi mu, so to some linear combination of these two Killing vectors that is equal to 1, 0, 0, W that I define as xi mu, that is of course a Killing vector because it is given by the linear combination of two Killing vectors. Now we have that if U mu is defined for R and theta constant, it means that U mu is equal to U0, 0, 0, U free, okay, and so this means that U0, this can be written as U0, 1, 0, 0, U free over U0. That means that U free over U0 is equal to W, with U free over U0 that is equal to d phi in the t, angular velocity. Now we want to show that the trajectories of the stationary observer they exist, so that the stationary observers they can exist, and to do so I want to impose U mu greater or equal than 0, so that I can find time-like trajectories or null trajectories. By doing so, what I'm asking is U0 squared times G00 plus 2W G0 free plus W squared G free free greater or equal than 0. But we have that the metric, it all depends on just on R and theta, it does not depend on theta and phi, on t and phi, and so these terms they are all constant. This is just an equation in W. So I get the W plus minus, it is equal to minus minus G0 free minus plus the square root of G0 free squared minus G free free G00 all divided by G free free. Okay, and I have that this admits two solutions, or this admits solutions, they can be either 2 or 1, when G0 free squared minus G free free G00 that is equal to delta times the sin squared of theta is greater or equal than 0. As delta is greater or equal than 0, R has to be minor than R minus and greater than R plus. So we have that inside and outside of the ergosphere one can have stationary observers, but for R minus than R plus and greater than R minus, the stationary observers they cannot exist. And so for R greater than R plus, the for velocity for the stationary observer would be given by this kind of relation with a value of W that is bounded between W minus and W plus. As R is equal to R plus, so when delta is equal to 0, one finds that W plus and minus they do coincide in just one value, that is equal to minus G0 free over G free free, that is equal to the sum of frequency. Okay, when R is minor than R plus and greater than R minus, and we have that the stationary observer doesn't exist. So now let me concentrate on this. We have that the stationary observer on the delta equals 0 r plus horizon has to move with the sum of frequency, but we have that as delta is equal to 0 in yes, as delta is equal to 0, this is equal to 0, and so we have that in this case we would have that UMU would describe an geodesic, would be associated to an geodesic, and so the stationary observer on the horizon, on the r plus horizon, it is the light that moves with the sum of frequency omega h. So we found that the dragging on the horizon, it is so strong that even light is dragged with the horizon, with the omega h, that would be the angular velocity of the r plus horizon. Okay, moreover, we have that as w plus it is always greater than 0, while w minus it is equal to 0 when g00 is equal to 0, and g00 is equal to 0 for r there is bound between rs minus and rs plus. So we have that w minus is equal to 0 on the ergosphere. Okay, then we have that w minus it is greater than 0 inside of the ergosphere, so for r minus then rs minus rs plus, and it is minor than 0 outside of the ergosphere for r greater than rs plus. And so this means that the dragging going to the ergosphere becomes stronger and stronger, such that in the end observers, particles that went into the ergosphere counter-rotating, they eventually have to flip their rotation, and then of course they fall into the r plus horizon and they just go into the black hole. Okay, finally I have to talk about the Penrose process, and then we will move on and talk about the uniqueness theorem and the laws of the black hole mechanics. So this last part I didn't like it very much, so maybe I should repeat it again. Okay, so what the picture I get from here is that, as I said, the photons, they are the only stationary observers on the r plus horizon, so on the black hole horizon, and they have to move with angular velocity that is that one of the sum of frequency. While talking about w minus, we have that it is equal to 0 when g0 is equal to 0, so in r equal to rs minus. It is greater than 0 as rs plus, sorry, as r is minor than rs plus, and it is minor than 0 as r is greater than rs plus. So that this means that if an observer, a particle, falls towards the ergosphere counter-rotating, eventually in the ergosphere it has to it has to flip its rotation, and falling inside of the ergosphere, it starts to co-rotate. Okay, with this I finished this discussion. Now I go with the Penrose process, and I should have finished with the Kerr black holes. So yes, let me talk about the Penrose process. What I have is that in the ergosphere, in the ergosphere, the T mu Killing vector, it is space-like, because we have the T mu it would be equal to 1 minus 2 m r over rho squared, okay, that we know is negative for r greater than r s minus but minor than r s plus. Okay, and we know that the ergosphere is defined between r plus and r s plus. So we have that. Let's say this is the ergosphere, as we said before. Okay. Let's say that a particle comes with positive killing energy associated to the T-mu killing vector. Okay. Let's say this particle enters the ergosphere, the ergo region, and then in here it decays into two particles. So one goes out and the other one goes towards the black hole. So the particle that goes out has to have a positive killing energy, E1, because going out, the killing energy outside of the ergosphere is positive, the killing energy is conserved along the geodesics, and so that's the only possibility. The particle that is going towards the R plus horizon, it can either have positive or negative killing energy because it is because the energy would be given by the product of a space-like vector, there is the killing time vector, and the velocity that is associated to the particle. So we already said some hours ago, yesterday, that in that case the scalar product can be either positive or negative. So let's take into account the case in which E2 is negative. We would have that due to the energy conservation, we would expect E to be equal to E1 plus E2. But this means that E1 is equal to E minus E2. E2 is negative, so this is E plus the modulus of E2. And this means that energy has been created. E1, there is the particle that is leaving, has more energy than the particle that came inside of the ergosphere. So now we want to understand, this is the so-called Penrose process that would create energy. So we want to understand what happens to the black hole as it absorbs the particle with killing energy E2. We have that if we consider the Ximu killing vector, this vector, it is time-like inside of the ergosphere, it is space-like inside of the R plus region. Okay, so the killing energy that is associated to the Ximu vector, it is given by Ximu umu, and it is equal to okay, if I define Ximu, yes, if I choose, wait, so let me choose this killing vector Ximu as Tmu plus omega h sum of frequency phi mu. Okay, so you have that the killing energy that is associated to Ximu, it would be given by Ximu umu. So Tmu umu, we know that it is equal to E2. Okay, and phi mu umu, it is equal to L. Okay, we want this to be greater than 0 because we have that Ximu, it is a time-like vector inside of the ergosphere, and umu of course has to be time-like because the trajectory has to be physical. So this means that L is minor than E2 over omega h, and so it is negative as E2 is negative. We are considering the case in which E2 is negative. Now we have that as the particle is absorbed by the black hole, the energy and the momentum of the particle become part of the energy and the angular momentum of the black hole. So we have that delta m is equal to E2 and delta j it is equal to L. We plug this inside of this and we flip the sign by putting the absolute value, the modulus. So we have that delta m in modulus it is minus, no, plus omega h delta j in modulus, it is minor than 0. That means that the modulus of delta n it is minor than omega h the modulus of delta j, and so the variation in the angular momentum will always be greater than the variation in the mass. That means that the Penrose process cannot bring a black hole with m squared greater than a squared to the extremal black hole with m squared equal to a squared. This process is not allowed by this kind of process. What I want to say now, I want to talk a little bit about the theorems that are related to the metric solution for black holes. In fact, we have that in all the different cases, that one of the Schwarzschild black hole and that one of the Reissner-Nordstrom black hole, we started considering some spherical symmetrical source that collapsed, and we found that the metric outside of the spherical symmetrical source had to be static because of the Birkhoff's theorem. But of course, the fact that the solution for the Einstein equations in the vacuum outside of a spherical symmetrical source has to be static is not invertible. We don't have that a static solution in the vacuum always corresponds to spherical symmetry. So we saw that in the Kerr case, the fact that the spherical symmetry didn't hold anymore made the hypothesis of the staticity fall. Okay, now we have that there are some theorems that define in a unique way what will be the solution for the metric outside of a black hole. So we have that the solution for the metric solution for a space that is asymptotically flat, static, in the vacuum, regular on and outside of the horizon, it has to be Schwarzschild, and this is Israel's theorem. And then we have Carter-Robinson's theorem that says that the solution for a space-time that is asymptotically flat, stationary, axial symmetrical in the vacuum, and regular on and outside of the horizon, it has to be Kerr. And so we find the uniqueness theorem that says that as a star with some axial symmetry collapses into a black hole, the solution has to be Kerr. So this star can have the most complex shape and characteristics. When it collapses, the metric will be Kerr, and the most general black hole will be the Kerr-Newman black hole that is described as there has a Kerr solution with the addition of some elements in the metric that depend on the charge, that can be either electric or magnetic, because we have that in the presence of electric or magnetic charge, the tensor, the T-Munu tensor outside of the source would not be equal to 0 anymore. Okay, and so with this we finished our discussion on the different kind of black holes. We have the most general black hole. It is described by just 3 parameters: mass, charge, and angular momentum. Okay, now we talk about the black holes, the laws of black holes mechanics. That is a very interesting argument. Okay, so as a rotating star collapses into a black hole, we said that in the vacuum, we said that the solution, it has to be Kerr. The R plus horizon of a black hole, okay, in the Kerr case, defines a Killing horizon for Xi alpha that is equal to T alpha plus omega h phi alpha, such that Xi alpha in R plus is equal to 0. So we have that the surface gravity is given by L equal to the square root of Xi alpha per mu equal to the 4 gradient of L, and K equal to the square root of L mu in H. In the case of Hacker black hole, we have that that the surface gravity would be equal to R plus minus M over R plus squared plus A squared. Okay, and we have that R plus minus M, of course, it is equal to the square root of M squared minus A squared over R plus squared plus A squared. Okay, so just let me just recap, because I was going a little bit slow in that part. We have that. Now we want to talk about the laws of the mechanical laws of a black hole. Okay, and so we're going to find the first law. To do so, first of all, we want to define the surface gravity for a Kerr black hole. That is the, as I said, since the Kermatic is the most general solution for a black hole that doesn't have any electric charge. We have that in this case the surface gravity would be computed in R plus, considering the Xi alpha killing vector, since we have that the killing horizon for Xi alpha it is in R equal R plus. Okay, and so we find that the surface gravity, it looks like this. Now, okay, so now let me have a look at the, okay, let me consider a surface at constant t and r. Okay, we have that the induced metric the induced metric on this constant, it would be ds squared induced equal to g theta theta d theta squared g phi phi g phi phi d phi squared. Okay, that can be written as sigma a b times d theta a d theta b. Okay, so sigma a b would be a matrix as that is G00, no, I'm sorry, G theta theta 0 0 G phi phi, it would be diagonal. Okay, so now we have that by definition the surface for these hypersurfaces, it will be measured as the integral of the square root of the determinant of the induced metric, so determinant of sigma, times the theta times the phi. We have that this is r squared, this is r squared c squared, and so we find that okay, let me see. No, I'm sorry. We have that g theta theta is equal to rho squared, and g phi phi is equal to, let me write that, maybe I will write it in here. So we have that g theta theta it is equal to minus rho squared, and g phi phi it is equal to minus r squared plus a squared squared minus a squared sin squared of theta times delta sin squared of theta over rho squared. Okay, and so from here I get that this rho and rho, they go away, the minus and the minus, they go away. Okay, then we have that if this surface is measured in delta equals 0, so in r plus. If we want to measure the area of this surface in r plus, we get that delta is equal to 0, and so the square root of the determinant would be r squared plus a squared times the sin of theta. Okay, times d theta d phi. Yes, before I was considering the spherical symmetry. I just went automatically. Okay, and so we have that r squared plus a squared does not depend either on theta or phi, so this is r squared plus a squared, and the integral of sin theta in the theta d phi, it is equal to 4 pi. Okay, so we get that the area, it looks like this. Okay, this means that this is r plus, of course. Okay, so this means that, let me erase everything. That delta A over 8 pi, it is equal to r plus times delta r plus plus a times delta A. I will go and find a form for delta r plus and one for delta A. In particular, I have that delta, it is equal to in r plus it is equal to 0, and it is r plus squared minus 2m r plus plus a squared. So this is equal to 0. This means that 2r plus the delta r plus minus 2m delta r plus minus 2r plus delta m plus 2a delta a, it is equal to 0. So delta r plus, it is equal to r plus, this is a plus, so r plus minus a over r plus minus m. Okay, while okay, I can erase this. While j is equal to ma, and so a, it is equal to j over m, such that delta a, it is equal to delta j over m. Okay, minus and we will find j over minus j over m squared delta m, so minus a over m delta m. Okay, and so now I'm able to work on this, and I find that this is r plus delta, okay, I plug delta r plus in here, and so I get r plus squared minus, okay, of course I forgot something. I have that in here, I have r plus delta m minus a delta a. Okay, so now we have r plus delta m minus a r plus delta a over r plus minus m. Okay, so plus a r plus delta a here minus m a delta a. So these, they go away, and I'm left with r plus squared delta m. Then I have that delta a, I can replace it with delta jm, so minus a delta j, if I'm not wrong, a delta j, okay, minus plus a squared delta m over r plus minus m. So in here I have r plus squared plus a squared delta m over r plus minus m minus a over r plus squared plus a squared times r plus squared plus a squared over r plus minus m times delta j. Okay, and so we find that this is the surface gravity, the inverse of the surface gravity, we saw it before, and so this would be delta m over k minus a over r plus squared plus a squared 1 over k delta j. Okay, but we have that this, it is omega h. Let me show why. We have that as the sum of frequency was given by 2mar over r plus squared plus a squared minus a squared sin squared of theta delta in delta equals 0, that will correspond to the horizon. This calcula I should yes, this computation I should have made it before, but I didn't. I don't know why. Because anyway, this would be the sum of frequency, so of course we can we can see what the sum of frequency would be on the horizon to get the omega h that I used into the previous discussions. Okay, I forgot to do this calcula, but actually we have that we would find that as delta is equal to 0, this would be equal to 0, and then we have that r plus would be equal to m minus plus the square root of m squared minus a squared. So r plus minus m squared, it would be equal to m squared minus a squared. So r plus squared plus m squared minus 2m r plus, it will be equal to m squared minus a squared. And so we have that this they go away, and we get r plus squared minus 2mr plus. Now we get that r plus squared plus a squared is equal to 2. Okay, so this is not r plus, this is just r. Yes, you should be just r. So we have that r plus squared plus a squared is equal to 2mr plus, such that 2mr plus in here it can go away with r plus a squared, and so in the end we get that omega h, it is equal to a over, because in here we had the square, a over r plus squared plus a squared. Okay, I'm sorry, this is very confusing, but this is in my notes. So we have that this is equal to delta m over k minus omega h delta minus omega h over k delta j. Okay. So this would be the sum of frequency, so the zero angular momentum observer frequency on the h horizon. It would correspond to the angular velocity it would correspond to the angular velocity of the horizon, and light would be dragged with this angular velocity. Okay, and so we found the first law, that would be delta m equal to delta a over 8 pi k over 8 pi delta a plus omega h delta j. Okay, this is the first law of the black hole mechanics. Let me see if I did it right. Yes, exactly. So I have that the first law of black hole mechanics, it is given by this kind of relation between m, a, and j. So these three parameters, they are related. The other laws we won't be computing them, but they are quite important to announce. And we have that the first one, so the zero law, would be that the surface gravity is constant on the horizon. Okay, and we can see it from here. If this is the surface gravity, we have that all the quantities, they are constant on the horizon, and so we have that the first law would be k constant. Okay, then we have this is the zero law. Then we have the first law, that is this one, that relates the mass variation with the area and angular momentum variation. Then we have the second law that states that the variation of A is always greater or equal than 0. And then the last law, the third law, says that K tends to 0 as M tends to A. Okay, since we have that R plus minus M, it is equal to the square root of M squared minus A squared. So, of course, we find this. So, in the beginning, the paper that was published with these four laws, it was entitled the four laws of thermodynamics of black holes, because making a really simple analogy, one finds that these laws, they are equal to the four laws of thermodynamics. In fact, we have that. I can send delta M to E to delta E. Then I can send delta A to delta S, K to T, and omega H delta J to PDV, and I find the laws of thermodynamics. But the title was not accepted because it didn't make sense to talk about temperature and entropy in the case of a black hole, because as people knew at those days, we're talking about the late 20th century. People didn't know very much about quantum mechanics, and so it didn't make sense to talk about temperature and entropy for a black hole, because it would not radiate, since it doesn't make possible for particle to escape its horizon, and moreover it can be the result of infinite different collapsing. One single black hole can be the result of infinite different collapsed stars, so the entropy would be infinite. Okay, then quantum mechanics came, and things changed, because with the quantum mechanics it was able to find that black holes actually they do radiate in terms of the so-called Hawking radiation. That is an effect given by the fact that the vacuum has a very complex structure, and there are some fluctuations such that in the end particles are created out of the black hole horizon, and they can escape as the black hole loses energy and mass and reduces its area. Okay, and in the same way it was also found that associated to this temperature one finds an entropy that of course is not the usual entropy. It's still we don't still know what kind of interpretation we should give, but but it's some quantity that we can consider as an entropy. In particular, we have that T is proportional to HK, and S, it is proportional to A over H bar, if I'm not mistaken, if I'm not wrong. Okay, so we find that black holes, they are thermodynamical objects. Okay, so let me show a simple example, a simple application of the second law. We have that in the case of the Penrose process, we found that delta n minus omega h delta j was greater than 0, and if we plug this inside of this equation, we find that delta a has to be greater than 0, and so the area law, it is conserved. Okay, then let me show another application of the second law. Okay, and let me show why a black hole cannot collapse into two different black holes, but two black holes can merge into one. Starting from I want to keep where is it? Yes, I want to keep the four laws. Okay, so let me consider the case of a black hole with mass m that collapses into m1 and m2. Of course, I have that m has to be greater or equal than m1 plus m2 due to energy mass conservation. Okay, and if we consider Schwarzschild black holes, so with no angular momentum and no charge, we have that the area, we have the delta j would be equal to 0, so delta a would be equal to 8 pi over k delta m, but k would be 1 over 4m, the surface gravity it is 1 over 4m in the case of a Schwarzschild black hole, and so we would find wait, let me do the calculus. Delta A equal to 8 pi over 1k delta m, but 1 over k it is equal to 4m. Okay, so from here I get that A it is equal to to 16 pi m squared. Perfect. So I have that the A1 plus A2 has to be greater or equal than A. Okay, because of the area law, and so 16 pi m1 squared plus m2 squared, it has to be greater or equal than 16 pi m squared, but we have that m that this would be greater than 16 pi m1 plus m2 squared, and of course this equation this equation is not verified, it is false, so this process cannot occur in nature. Now we see the other case when m1 plus m2 they merge into m, and so in this case we have that m1 plus m2 it has to be greater or equal than capital M, and so a1 plus a2 it has to be minor or equal than a. Okay, so we invert the relation and we find that this is verified, and so this process can occur. In fact, two black holes, we observed two black holes merging into one, but the opposite process, it is not physical. Okay. Finally, we have that in the demonstration of the second law of the RL law, there is a strong hypothesis that is that one of the positivity of energy, such that in that way one finds that delta is always it is always greater or equal than zero. But actually, in processes like that of the Hawking radiation, delta A it is minor than zero. The black hole loses mass, and it also loses surface, loses area, and that's because the law that holds it is the one that would say that it is the total entropy, that the variation of the total entropy that is greater or equal than zero, where the variation of the total entropy is given by the variation of the black hole plus the variation of the entropy of the universe outside of the black hole. So during in every physical process, the generalized second law it is always true. As in the thermodynamical case, where we had that the entropy of the fridge it decreased, but the entropy of the room it increased in such a way that in the end the total variation it was positive. Okay. Expanding universe, the Sitter solution. We're almost to the end. So the Friedmann-Lemaitre-Robertson-Walker solution describes a black hole that is homogeneous and isotropic. This is our hypothesis on the universe, and so we find that this kind of universe and its evolution it would be described by the Friedmann-Lemaitre-Robertson-Walker solution. So we want to be able to find black holes in this kind of universe, and so we should consider, for example, a Schwarzschild bubble, and we should be able to have that on the boundaries of this bubble, the Schwarzschild metric and the Friedmann-Lemaitre-Robertson-Walker metric, they should coincide, but actually this problem is quite difficult. There is just one case in which we are able to do so, and it is that of an exponentially expanding universe. So it would be the De Sitter case. Okay, just a moment. Okay, so before I go, let me talk a little bit about the cosmological constant. This constant, there is lambda, was added by Einstein in principle to find a static solution for the universe, because he thought that the universe had to be static, and he couldn't find any static solution for the universe in its normal Einstein equations. So the fact is that he had to find some term inside of the Einstein equation that would make it possible to find a static solution, but would not change the fact that the right hand side, and so the left hand side, is such that the covariant derivative of the right or left hand side it has to be equal to 0, and so the most the easiest thing to do it was just to add a constant, and so the Einstein equation with the cosmological constant, they would look like this: r mu nu minus 1 over 2 r g mu nu minus lambda g mu nu equal to 8 pi g t mu nu. The problem is that adding this constant, a lot of the symmetries that we already talked about, they are broken. For example, we have that Minkowski is no longer the solution for the flat spacetime. Moreover, Hubble discovered some years after the general relativity that and the addition of the cosmological constant, that the universe was expanding because he was able to observe uh, the, the galaxies redshifting in all the directions, and so Einstein had to remove the lambda constant, the cosmological constant, because at that point he understood that the universe could not be described by a static solution. Then, studying the Einstein's equation in considering the evolution of the universe as that one of a universe that expands, it was not possible to find the right description, the right solution, because it was not possible to find an accelerated expansion. That is what we actually observed looking at the sky, and so we had to reintroduce again the lambda constant, because in the presence of this lambda it is possible to find that kind of solution. The difference is that now we do not consider this as a term related to the geometry of the space-time, but as a term that is related to the source. In particular, we relate it to the dark energy, that would be the energy of the vacuum, since we now know that the vacuum has some peculiar and quite complicated structure. Okay, and so let's see how we would get to the lambda constant. So we consider the content of the universe at large scale as a perfect fluid, such that T mu nu would be equal to rho plus p times u mu times u nu minus p g mu nu, where rho and p, they are the density and the pressure in measured by an observer that commoves with the fluid. Okay, so this is what we have for the content of the universe. Then we have that for the vacuum, some equation of state like this. That's what we impose. Rho vacuum equal to minus p equal to lambda over 8 pi g. So we say that some equation like this should hold, okay, such that if we plug this inside of the T mu nu, we find that T mu nu vacuum, it is equal to lambda over 8 pi g mu nu, so that the Einstein equation, they would read as r mu nu minus 1 over 2 r g mu nu equal to lambda g mu nu. Okay, now we have that when lambda is greater than 0 we find the de Sitter solution, when lambda is minor than 0 we find the anti-de Sitter solution. Now we want to study a solution for these Einstein's equations, okay, outside of a spherical symmetrical source. So as always we consider, because we want to find a black hole in the universe that in the universe with a vacuum with this kind of equation of state, okay, and so we have that outside of the black hole of the source. Okay, maybe I will say this again. Okay, so we find this Einstein's equation. So now we want to be able to solve this Einstein's equation outside of a spherical symmetrical source, because we want to find the solution for a black hole in this kind of universe with a vacuum with this equation of state. Okay, and so we consider the ansatz as always ds squared equal to e to the nu of r and t dt squared plus e to the mu of r and t dr squared minus r squared d omega squared. Okay, I plug these ansatz inside of these equations, and I have that let me see, Yeah, I have that. I'm sorry. Before plugging the answers, of course, I can work on the Einstein equation, because I have that if I take the trace, I find that R, okay, I find that this would be R minus 1 over 2 for R, so R minus 2R, which would be minus R equal to, yes, minus R equal to for lambda, so R equal to minus for lambda. I plug this inside of this and find that R mu nu, so minus 4 over 2 lambda, okay, R mu nu is equal to minus lambda g mu nu. This is the Einstein equation that I have to solve if I was okay, if I didn't commit any error. Yes, R mu nu equal to minus lambda g mu nu. Perfect. Okay, so I plug the answers inside of the Einstein equation and find that R01 that is equal to minus mu dot over R is equal to 0, such that mu is just a function of R. Then from the 0, 0 and 1, 1 I get that mu nu plus nu prime is equal to 0, such that mu plus nu is equal to some function of t. With this there is a function of R, and that is a function of R and t. And then from the 2, 2 I find that e to the minus mu is equal to 1, okay, it is equal to 1 minus 2m over R minus lambda over 3 R squared. Okay, and so in the end the metric that we find, the de Sitter-Schwarzschild metric, is d squared equal to 1 minus 2m over R minus lambda over 3 R squared dt squared, because the e to the ft, it would be reabsorbed into the time inside of the time coordinate, minus 1 minus 2m over R minus lambda over 3 R squared to the minus 1 d R squared minus R squared d omega squared. Okay, and this is, as I said, the Schwarzschild-Sitter metric. We have that as lambda is equal to 0, we find the Schwarzschild metric, and as m is equal to 0, we find the Sitter metric when lambda is greater than 0, and the Sitter when lambda is minor than 0. Okay, of course there was another way to proceed, and it was to consider the mass parameterization. That yes, the mass function parameterization, and it was a faster way to proceed. In fact, I have that if I say that R mu nu is equal to minus lambda g mu nu, then I have that t mu nu is equal to lambda over 8 pi g mu nu. Okay, then let me show how I would proceed. I have that the answers, it would be d s squared equal to e to the 2 psi of R and t, 1 minus 2m of R and t over R dt squared minus 1 minus 2m of R and t over R in dr squared minus R squared d omega squared. Okay, so I have that. I plug this inside of the equations and find of the Einstein equations, and find that the derivative of m with respect to R, it is equal to 4 pi g R squared t t t. The derivative of m with respect to t, it is equal to minus 4 pi g r squared t rt, and the derivative of psi with respect to r, it is equal to 4 pi g r over 1 minus 2m of r and t over r times t t t minus t r r. Okay, and so I have that t t t, it is equal to, you can see it from here, gamma over 8 pi g as TRR, while TRT of course is equal to 0. So this means that this is equal to 0, and so psi is a function of the time and it can be reabsorbed into the time coordinate. This will be equal to 0, and so this is the only equation that we need to solve. But this is solved instantaneously. We have that this is 4 pi g r squared times lambda over 8 pi g, such that in the end we would find okay, r squared lambda over 2, okay, and so m of r, it is equal to m minus lambda over 6 r to the third, no, minus or plus lambda over 6 r to the third. So we plug this inside of the answers and we find the de Sitter or anti-de Sitter metric. Okay, so if we have a look at the de Sitter metric, we have that there is a manifest time symmetry and spherical symmetry, but actually we have a lot more than those two symmetries. We have 10 symmetries for the de Sitter space, and that's because this is a constant curvature spacetime. We have that for this kind of spacetimes, r mu nu alpha beta, it is given by some constant times g mu beta g nu alpha minus g mu alpha g nu beta, such that r mu alpha mu beta, it is equal to k, and we find for wait a moment. So this would be mu beta alpha nu. Okay, so wait, I'm getting a little bit confused now. It's because I was mistaken, of course. In that case we had that we had alpha and sigma and beta and gamma, so okay, yes, I was mistaken. Let me say it again. For the constant curvature spacetimes, we have that r mu nu alpha beta, it is equal to some constant times g mu alpha g nu beta minus g mu beta g nu alpha. So we have that the Ricci tensor is given by r mu alpha mu beta. It will be equal to k for g alpha beta minus g alpha beta. There will be 3k g alpha beta, and the Ricci scalar, it will be equal to 3k. So the Ricci scalar, it is constant, and this is what we found in this case. We have the Ricci scalar in here. Where is it? the Ricci scalar was equal to minus 4 lambda. Okay. So now we look for the null geodesics in the sitter. Yes, let's consider we have that in this case the number of symmetries it is maximum. See, the number of Killing vector it is maximum with respect to the dimension of the spacetime. So in 4 dimensions we have that the maximum number of Killing vector it is 10. Minkowski has the maximum number of Killing vector and symmetries because it is the case of the sitter with lambda equals 0. Okay, so now we study the sitter. We have that the metric it would be ds squared equal to 1 minus lambda over 3 r squared dt squared minus 1 minus lambda over 3 r squared to the minus 1 dr squared minus r squared d omega squared. Okay, so as always we can so we want to find the radial null geodesics. So ds squared equal to 0 and theta and phi constant. We find that dt in dr is equal to plus minus 1 minus lambda over 3 r squared to the minus 1. Okay, I define the Tartas coordinate r star as let me remember, it was 1 over 2 the square root of 3 over lambda. Then I remove the 1 over 2 because I can write 1 over 2 times the square root times the logarithm, or the square root of 3 over lambda times the hyperbolic tangent to the minus 1 of the square root of lambda over 3 r. This is the same stuff. And so in this way I find that dt in dr star is equal to plus minus 1. Okay, such that t minus r star it is constant and equal to u, that is the retarded coordinate, and t plus r star it is constant and equal to v, that is the advanced coordinate. So we're able to define, as always, the advanced, retarded and double null metric. There would be ds squared equal to 1 minus lambda over 3 r squared dv squared minus 2 dv dr minus r squared d omega squared, or 1 minus lambda over 3 r squared du squared minus 2 du dr minus r squared d omega squared, and finally 1 minus lambda over 3 r squared du dv minus r squared d omega squared. Okay, so advanced, retarded and double null. Looking at the original metric, we have that there is a singularity when r is equal to the square root of 3 over lambda. So for r greater than the square root of 3 over lambda, we have that the time becomes a space and the space becomes a time, and so no static observer exists, while for r equal to minor than the square root of 3 over lambda, everything is fine. So we call r equal to the square root of 3 over lambda cosmological horizon. Okay, so now we want to go from the double null metric to Kruskal, and to do so we want to compute the surface gravity. Okay, and then go to Kruskal. And so I have that the surface gravity k, in this case it would be given by 1 over 2 f prime in h, as we have already seen different times. Okay, and so it would be minus, of course, in modulus, so we don't have this minus sign. It will be 2 over 3 lambda r to the third. Okay, no, I'm sorry, r. Okay, and so we plug the cosmological times 1 over 2. Okay, now it makes sense on the cosmological horizon. So this 1 over 2 it goes away with this. The cosmological horizon, it is equal to the square root of 3 over lambda, and so this is equal to the square root of lambda over 3. This is the surface gravity. Now we can go to Kruskal and find that U is defined as 1 over k minus 1 over k e to the minus k u, and V is defined as 1 over k e to the kv. Okay, and the Kruskal metric will be ds squared equal to 3 over lambda times 1 plus lambda over 3 r squared du dv minus r squared d omega squared. So I have that this is the De Sitter metric in the Kruskal coordinates, and then we can write r as a function of u and v as the square root of 3 over lambda times 1 plus uv over 1 minus uv, such that when uv is equal to minus 1, r is equal to 0, uv equal to 1, r is equal to infinity, and uv equal to 0, r is equal to 0. So we go to Penrose and find that as this is U and this is V. In Penrose, of course, the light cones, they are Minkowski. We went to Kruskal where the light cones are Minkowski, and then in Penrose the shape of the light cones is preserved. And so we find that this would be our Penrose diagram, where this is r equal to 0, and in here as well, and this would be r equal infinity, while this would be the cosmological, these two, they would be the cosmological horizon. So we find a solution for a universe that is exponentially expanding, but also a solution for a universe that is exponentially contracting. In here we have a contraction, and in here we have an expansion. An hypersurface that yes, an hypersurface in some space-time with some symmetries has the same symmetries of the space-time it lives in, and moreover it has an induced metric, of course. So Schwarzschild's idea was that to consider the De Sitter solution, the De Sitter universe, as an hypersurface in Minkowski 5 dimensions. In particular, we would have that the surface that defines the De Sitter universe should be zeta 0 squared minus zeta 1 squared minus zeta 2 squared minus zeta 3 squared minus zeta 4 squared equal to minus alpha squared equal to minus 3 over lambda. Okay, now we can choose different parameterizations that would satisfy this equation, and of course based on the parameterization that we choose we find different solutions for different induced metrics. In particular, for example, one parameterization would give us the ds squared equal to 1 minus lambda over 3 r squared dt squared minus 1 minus lambda over 3 r squared to the minus 1 dr squared minus r squared d omega squared. I don't know why I wrote since it was here. Anyways, I did. And this parameterization, it would not cover the entire space-time, because we would have that zeta 0 plus zeta 4 would have to be greater than 0. Anyways, we would have that the parameterization would not be complete in the Minkowski 5D. Then there is another one that would give a metric like this: this squared equal to dt squared minus e to the 2t. In here we would have d capital T squared minus e to the 2t over alpha times dr squared minus r squared d omega squared, which looks like the Friedmann-Lemaitre-Robertson-Walker metric when k is equal to 0. This would be a flat space-time, a flat space. This would be the factor that determines the expansion, the exponential expansion. And this doesn't cover the entire Minkowski 5D as well. And finally, we would have a third parameterization that would cover the entire Minkowski 5D, such that ds squared would be equal to dt bar squared minus the cos h of t over alpha, if I'm not wrong. Let me see. Yes, with a alpha squared in front that I forgot. Okay, times dx squared minus sen squared of x times d omega squared. Okay, and this would correspond to the Friedmann-Lemaitre-Robertson-Walker metric when k is equal to 1 and r is equal to sen of x. Okay. So this would be different parameterization for the de Sitter hypersurface, and this would be the induced matrix on this the de Sitter hypersurface based on the choice that we made for the parameterization. Okay, so now we go back to the Schwarzschild de Sitter metric, and we see if it describes a black hole. So we have that the metric would be 1 minus 2m over r minus lambda over 3r squared dt squared minus 1 minus 2m over r minus lambda over 3r squared times dr squared to the minus 1, of course, minus r squared d omega squared. Okay, so we want to study this term that we call f and see what's the behavior of this term as a function of r, to determine the existence of singularities. Of course, we have that in r equal to 0 we have a singularity that is physical. Okay, we want to see if we find other singularities, and so first of all we study the derivative f prime. It will be equal to 2m over r squared minus 2 over 3 lambda r. Okay, we want it to be equal to 0 to find a local maximum or minimum, and we have that this is verified when r to the third is equal to 3m over lambda. So when r is equal to 3m over lambda to the 1 over 3. Okay, perfect. Then I have that the second derivative, it is equal to minus 4 m over r to the third minus 2 3 over lambda, and if I compute this in this r, I will find that the second derivative it is minor than 0, and so this is a local maximum. Okay, then I want to compute the function in this radius. They have that it will be equal to 1 minus 2m over 3m over lambda to the 1 over 3 minus lambda over 3m over lambda to the 2 over 3. Okay, and what I have is that fr equal to 0, fr is equal to 0 as solutions just when m is minor than 1 over 3 times the square root of lambda, if I'm not wrong. Exactly. So, moreover, we have that fr tends to minus infinity as r tends to 0 and infinity. Okay, and so we're finally able to draw a graph. We have that this would be f, this would be r. Okay, the function would be described by something like this. We have that as r tends to infinity, this goes to minus infinity. As r tends to 0, this goes to minus infinity. There is just one local maximum in this value that I call Rm, maybe. No, yes, Rm. Okay, and so as m is minor than 1 over 3 times the square root of lambda, this local maximum it is in the positive region, so it has a positive value of f. Okay, and so we find that f has two different solutions. F equal to 0 has two different solutions. This would be the R black hole, and this would be the cosmological horizon. So we have that for R minor than R black hole, we find that F is minor than 0, and so no static observer can exist, and for R greater than RC, we find that F is minor than 0, and so no static observer can exist. This means that this would be our physical universe, and then we would have the black hole for decreasing values of R from R black hole to R equal to 0, which is the physical singularity. And if one crosses the cosmological radius, the expansion is so fast that there is no possible way to stay still. Okay. And so we have that as r equal to 0 is a space-like singularity, because we have that r equal to 0 is a space-like hypersurface, and r equal to infinity is a space-like hypersurface. What we find is that the Bernoulli diagram that is associated to the Schwarzschild-de Sitter solution, it is given by something like this. We have that RC and R black hole, they are null surfaces, I don't know how to say it. At this point I'm just very tired. And so this is RC and this is RC. This is R black hole and this is R black hole. And we go on RC, RC, R black hole, R black hole. Okay. And so we find that in here R is equal to infinity. In here R is equal to 0, then R equal to infinity, R equal to 0. These are space-like singularities, and we have that we find the black hole in here, because one can only inside of this region can only move towards the R equals 0, because the light cones they are bounded inside of this region, and we find of course the white all as well, and once RC is crossed going to the future, okay, one finds that it is only possible to go to R equal infinity, and so it is not possible to stay still at a constant value of R, and moreover one finds also a contracting universe, an exponential contracting universe solution for symmetry reasons. Okay, so up to now we discussed the case where lambda is considered greater than 0. There is the de Sitter case, but there is also the anti-de Sitter case when lambda is minor than 0. So Schwarzschild idea is still valid. We have that we can consider the anti-de Sitter case as an hypersurface in 5D Minkowski, but this time we have that the signature of this 5D Minkowski will change. It will be a free 2, so we will have 2 positive signs and 3 negative signs. In particular, we have that the hypersurface will look like zeta 0 squared plus zeta 4 squared minus zeta 1 squared minus zeta 2 squared minus zeta 3 squared is equal to alpha squared. Okay, so as we said before, we can choose infinite types of parameterization such that this equation is satisfied. And for example, if in one parameterization we find that the s squared is equal to 1, so the symmetry that one has in this Minkowski 5D would be SO free 2, and so we would have that anti-de Sitter would have the same type of symmetry, while in the other case we had that the symmetry was SO for 1. Okay, so in one parameterization, in one appropriate parameterization, we can find that the s squared is equal to 1 minus r squared over alpha squared, 1 plus r squared over alpha squared dt squared minus 1 minus r squared over alpha squared dr squared to minus 1 minus r squared d omega squared. And there is another way, another parameterization that is interesting because it will appear in later discussions. That would be ds squared equal to zeta bar squared over alpha squared dt squared minus alpha squared over zeta bar squared d zeta bar squared minus zeta bar squared over alpha squared times r squared minus times dx squared plus dy squared. Okay, so this would be two anti-de Sitter metrics. Okay, no. If we do the same kind of consideration we did on Schwarzschild de Sitter on the Schwarzschild anti-de Sitter, we find that there is no cosmological horizon but just the black hole horizon. Okay, so because anti-de Sitter, I think it would describe decelerating expansion, not an accelerated expansion. Okay, so now we have looked at the near horizon approximation in Reisner-Nordstrom, and then we talk about the metric inside of a star, and we finished. So in okay, so we have that the Reisner-Nordstrom metric, it was 1 minus 2m over r plus q squared over r squared dt squared minus 1 minus 2m over r plus q squared over r squared times to the minus 1 times dr squared minus r squared d omega squared. Okay, we have that when m squared is greater than q squared, and so r plus minus exists. In the near horizon approximation, I say that r is defined as r plus x with x much less than r plus, and so I have that 1 minus 2m over r plus q squared over r squared, it will be equal to r minus r plus times r minus r minus over r squared. Okay, that would be x times r plus minus r minus over r plus squared. That is just equal to 2k plus x, because k plus is equal to r plus minus r minus over r plus squared. And so we have that the metric would be ds squared equal to 2k plus x times dt squared minus 1 over 2k plus x times dx squared minus r squared d omega squared. Then I define 2k plus x as k plus x bar squared. Okay, so I change coordinates, and I find that dx is equal to 1 over 2k plus, so 1 k plus over 2 2x bar dx, so k plus x times dx, and so dx squared is equal to k plus x bar squared times dx squared, and finally I will get that ds squared is equal to k plus x bar squared in dt squared minus dx squared minus r squared minus r plus squared d omega squared. I found a two sphere and Rindler coordinates as each Schwarzschild. Now we have a look at the case of the extremal black hole. Okay. So in this case we would have m squared equal to q squared, such that r is equal such that the singularity is given in r equal to m. So I define in the near horizon approximation r equal to m plus x, where x of course is much less than m, and so I get that 1 minus 2m over r plus q squared over r squared. Okay. No, I'm sorry, in the extremal case we have that since m squared is equal to q squared, the metric is ds squared equal to 1 minus m over r squared dt squared minus 1 minus m over r to the minus 2 dr squared minus r squared d omega squared. And so we have that as I plug r equal to 2m plus x, I find that this would be r minus m over r, so x over m, x squared over m squared dt squared minus m squared over x squared d x squared minus m squared d omega squared. So we found a two sphere and anti-de Sitter in the case of an extremal black hole in the Reissner-Nostrom metric. And this is interesting because we have that anti-de Sitter has a lot of symmetries, and so extremal black holes are objects that are that can be studied in theories of supersymmetries and much complicated theories where these symmetries that come from anti-de Sitter can be used in such a way to find some kind of relation between a theory of gravity and the quantum field theories. Okay, so with this we finished the discussion on we finished the discussion on the Sitter, anti-de Sitter, and the near horizon approximations, and now finally we go to the last argument, and it is the metric inside of a star. So we have that up until now we have always talked about the metric solution outside of some source. We talked about the star imploding, so we saw what would be the solution outside of this kind of star in the case of spherical symmetry or axial symmetry. But now we want to see what would be the metric solution inside of a star. In fact, we have that the Einstein equation they would read as R mu nu minus 1 over 2 R g mu nu equal to 8 pi g t mu nu, with t mu nu different from 0, of course. And we would have that the content of a star would be a perfect fluid such that t mu nu is equal to rho plus p times g mu nu minus p times g mu nu. We have that the covariant derivative of t mu nu with respect to mu has to be equal to 0, okay, due to the energy momentum conservation, and we have that this would be equal to 1 over the square root of g times the derivative with respect to mu of rho plus p I'm sorry, this was not g mu, of course, this was mu 1. Okay, now before I write this, okay, let me proceed in a different way. I have that this would be the energy momentum tensor that describes the content of a star. Okay, let's see what kind of equation we will get when t mu nu covariant derivative with respect to mu is equal to 0 with t mu nu that is defined in this way. But to do so, let me proceed in this way. Let me look at t mu nu covariant derivative with respect to mu, and let me just develop all the calculi in t mu nu. Then we will plug these inside of the equations. Okay, and so I have that t mu nu covariant derivative with respect to nu would be t mu nu partial derivative with respect to mu plus gamma t alpha nu mu alpha mu plus gamma t mu alpha nu alpha mu. Okay, so this object cannot, we do not work on this object because we can do nothing in here. Okay, but we can work on this, and we have that this is 1 over 2 g mu nu times g alpha nu derived with respect to mu plus g mu nu derived with respect to alpha minus g alpha mu derived with respect to nu. This and this they would cancel off as we can switch mu and nu. Okay, and so we find that this is equal to 1 over 2 g mu nu times g mu nu partial derivative with respect to alpha, that is just equal to 1 over the square root of g times the derivative with respect to alpha of the square root of g. We've seen that when we worked with the Maxwell covariant equations. Okay, So we have that in the end we would find that t mu nu covariant derivative with respect to mu it is equal to 1 over the square root of g times the derivative with respect to mu of t mu nu times the square root of g plus gamma nu alpha mu t mu alpha. Okay, and so we have that this is equal to 0 due to energy momentum conservation. Okay, so now we have a look at the energy momentum tensor expressed in this way as we consider the content of the star as a perfect fluid, and we have that in this way we would have that t mu nu covariant derivative with respect to nu would be equal to 1 over the square root of g times the partial derivative with respect to mu of rho plus p u mu u nu times the square root of g, okay, plus gamma nu alpha mu times rho plus p u mu u alpha, okay, minus the derivative of p with respect to mu times g mu nu, because we have that p is just a function, so its derivative is just the partial derivative, and g mu nu when derived with respect when covariantly derived with respect to mu is just equal to g mu nu. But we have the g mu nu, okay, we have that for g mu nu we have I indices. Yes. Okay, so then we have to make some assumptions to proceed. First of all, we assume hyperstaticity given by the equilibrium between the thermodynamical pressure and the self-gravity, and so we have that in this limit we have that u mu has some u0 0 form, so it is just the first non-vanishing component, and moreover the metric does not depend on the time, and so we have that as u mu has to be equal to 1, u0 is equal to 1 over the square root of g00. Okay, so the only non-vanishing looking at this term, the only non-vanishing components that would be those in mu different from 0, because the derivatives in 0 they are all equal to 0 due to the hyperstaticity, but we have that as mu is different from 0, y is equal to 0, and so this term just drops, it goes away. Okay, in here we have that u mu and u alpha they have to be equal to they both have to be equal to u0, so we have that the only non-vanishing Christoffel symbol it is given by gamma 00 nu, which is equal to 1 over 2 g nu mu g 0 mu derived with respect to 0 plus g 0 mu derived with respect to 0 minus g 0 0 derived with respect to mu. Okay, and so we have that these derivatives in the time they would be equal to 0, and we would have 1 over 2 g, let's say nu alpha times g 0 0 derived with respect to alpha. Okay, then I plug this inside of this, and I find that we know we have the t mu nu covariant derivative with respect to mu has to be equal to 0, so this is the equation that we're going to use. So we find 1 over 2 g nu alpha g 0 0 derived with respect to alpha times 1 over g0, because u0 squared it is 1 over g0, times rho plus p, it is equal to P derived with respect to mu times G mu nu. Okay, and so okay, let me see. This can be written as G mu nu, G00 derived with respect to mu. Okay, so the G mu nu drops, and we find that the derivative with respect to mu, it is equal to okay, the derivative of B with respect to x mu, it is equal to 1 over 2 times the derivative with respect to x mu of the logarithm of G00 from here times rho plus P. Okay, this should be the equation. And there is also a minus sign that I forgot in here. Okay, so this is the equation between P and G00 and rho. Okay, then I go on with my discussion, and I have that if I consider an ansatz a spherical symmetrical, considering spherical symmetry, so in the hypothesis of spherical symmetry, the ansatz is given by ds squared equal to e to the nu of rnt times dt squared minus e to the minus mu of minus e to the mu of rnt dr squared minus r squared d omega squared. Okay. As usual, I plug this inside of the Einstein equation and find that mu dot over r is equal to 0. Okay. Then I find that e to the minus mu, it is equal to 1 minus 2 g m of r over 2, where m of r is defined as 4 pi the integral of rho r squared in the r, such that m of 0 is equal to 0, and nu equal to 1 over r, yes, times 1 minus 2 g m of r over r times 2 gm of r over r plus 8 pi g rho squared r, no, rho r squared. Okay, and so now we have almost everything, because we found the form of the metric. Okay, we found that ds squared is given by this ansatz with e to the mu that comes from here, and e to the nu of r and t that comes from here. Okay, and we finally need just to solve this equation. Okay, plugging inside of G00 what we actually what we just found from the ansatz to completely determine our system. We in the hypothesis of some equation of state between P and rho, we have that the derivative between of P with respect to x mu is equal to minus 1 over 2 rho plus P times the derivative with respect to x mu of the logarithm of G00, which is just nu. So derivative with respect to x mu of nu. Okay, and so we finished. Now we have solved the metric of a star, and we also found the equation for its pressure as a function of r. Okay, what else can I say? I have that a star is in equilibrium if r is greater than rb, which is the Buchtal limit, that would be equal to 9 over 4 gm, there is greater than 2m, there is the Schwarzschild limit. And so someone thinks that black holes do not exist, but there should be these quasi-black holes that actually have some radius that is bounded between 2m and the Buchtal limit. Moreover, a lot of important studies on heavy objects such as neutron star and eventually black holes, just at a theoretical level, were made by Oppenheimer and Volkov that find that a neutron star cannot have a mass greater than 3 solar masses to be in equilibrium. So if during the collapse the mass is greater than 3 solar masses, the neutron star does not form, but one as a black hole. Chissà dove si buttano tutti i sogni rotti, lasciati ad annegare soli dentro l'età. Io volevo scoprire l'America o un'Australia, però c'erano già. Ma poi mi sono accorto, alzando al cielo gli occhi, che c'erano milioni di pianeti. Più gente conosco, più spero che un giorno arrivino gli alieni a portarmi via. A portarmi via. Fare il letto di morte dei cattolici per andare in paradiso al photo finish. Io però dormo nel letto dei cattivi che non si son pentiti, si svegliano infelici. Ma non c'è una luce che mi porti da te, che mi salvi da tutte le mie paranoie. Lo sai, gli alieni non arrivano mai. Ho lanciato aquiloni in un cielo nero e forse ho sbagliato col senno di poi, ma ora so che gli alieni esistono per davvero. Sono soltanto più umani di noi, sono soltanto più umani di noi. Poi mi sono accorto, alzando al cielo gli occhi, che c'erano milioni di pianeti. Più gente conosco, più spero che un giorno arrivino gli alieni